Yes.
It's Linux?
Yes.
Yes, I think this one.
Check, check. Handheld mic, check, check. Test, test, test. Check the handheld mic. Check, check. Check, check, check. Check, 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 yeah.
Check.
Oh. Il n'y a pas une touche là. Check, check. Check. Il y a une touche quelque part.
Pardon, 5 secondes.
Catch box. Check, check, handheld mic. Okay, we're back. Good morning, everybody, and welcome back. Welcome back to Embedded Recipes. We're going to kick off day number 2 here right away with our first speaker. Our first speaker is Annalena, and we'll just get right into it. Thank you. Welcome, Annalena.
Yeah, thank you. Nice you're all here after the party yesterday. I want today speak a bit about building trust, use cases and implementations of TPM 2.0 in embedded Linux systems. Why this talk? I had in the past, I think, around 2 years, several use cases and projects with TPM in there. And I learned that there's so much more to know about TPM and so much more deep dive. And a lot of people know there is a TPM, but what it actually is and how you can use it is not that spread. So I'm here to spread the word. I'm Anna. I'm an embedded systems engineer from Germany. I have a background in embedded systems, electrical engineering. I basically started my embedded career with embedded Android, and nowadays mostly focusing on Yocto. And now let's start with a bit 101 about TPM 2.0. And start with what is TPM. Basically, it's a trusted platform module as specified by the Trusted Computing Group, the TCG. And this definition or standard from them also made it to ISO IEC standard. Mostly if you think about TPM, it's referred as a cryptographic coprocessor, as a hardware security module, a hardware root of trust. Often the word hardware is called when thinking about TPM, but basically that's just part of the truth, because there is different ways to implement TPM. There are discrete TPM hardware implementations, but there are also integrated TPMs integrated in software, as they are used for the Intel platform trust technology, or when thinking about ARM in or area, it's most often firmware TPMs that are implemented in trust zone and used, for example, in smartphone applications a lot. But there are also software implementations for testing or hypervisor and all that stuff. So it's not always real hardware, with some pros and cons that are coming from that. So when you think about TPM, you can picture it a bit like that. It's a device providing cryptographic coprocessor functionality with random number generator, key generator, hash functions, and a ton of algorithms. with some permanent memory, storing some seeds, templates for key generation, slots for storing keys persistently, the platform configuration registers, something we will speak about later a bit in detail, and a lot of seeds, and also providing some volatile memory for handling active session keys and non-persistent data. And if you think about the capabilities of your TPM on your device, for example, you can just check it with TPM2 getcap command, which is part of the TPM2 tools software set. That's just an example how you can find out a bit more what is actually available in your platform. And when speaking about software and software implementations, let's dive into the software stack for a minute. The software implementation, the library, and the stack is also defined by the Trusted Computing Group. And it's defined as a stack you can see in there. There are basically 3 API levels in different I don't get a word right now. In different abstraction levels. There's a system API, basically mapping on the low-level TPM commands, an enhanced API and a feature API for more sophisticated use cases. In applications, there's a TPM command transmission interface, TCTI, which you can think of as a kind of hardware abstraction layer for TPMs, and a bit of functionality on the lower level, TPM access broker, resource manager, device driver, and how they implement it, if they're implemented as one thing or if they're even implemented is a bit up to the use case. And yeah, basically there are several implementations for the TPM software stack. There's a reference implementation done by Microsoft, a Microsoft implementation itself. But when working with Linux, it's mostly the TPM2 TSS implementation you will use. And I think it's quite good quality and proven software. So that's basically the thing that will be there most often if you're not in the Zephyr world, for example, or the microcontroller world. And I brought some really wild picture from the TPM2 software GitHub page. The GitHub page or organization also implementing the TPM2 TSS software stack. It's a bit wild. I don't know if you really see it from your perspective right now, but what I like from this picture is it clearly shows the HAL functionality of the TCTI implementations. There's a UEFI implementation, for example, simulator implementation, and several for the device in Linux. And it also makes clear that there are 2 TPM driver implementations and devices available in Linux, one with a resource manager available and one without. And yeah, let's continue with a bit more about TPM terms. Speaking of keys, I will speak mostly about the asymmetric keys because they're the most used in most use cases, but generally the most thing I say is valid for the symmetric ones as well. There are several algorithms available on the TPM, mostly ECC and RSA. You can generate primary keys, so-called primary keys, with the TPM based on a hopefully hardware-based random number generator. You can also import external keys, public and private. You can use the keys for the usual key functionality stuff, for encrypting, for decrypting, for signing, attestation tasks. And the one nice thing about TPM is the thing with primary keys and child keys. Primary keys are really part of the TPM. They're derived from a seed, the cryptographic root. And the primary keys, the private part of them, never can be extracted from the TPM. You can directly use primary keys, but it's more common to derive child keys from primary keys. And they can leave the TPM because they use a mechanism called key wrapping, which basically encrypts the child keys with the primary key, so they cannot be used at all without exactly that TPM, and make it safe and secure to store the keys outside. And speaking about key hierarchies, I showed one hierarchy, but there are indeed 4 hierarchy levels and hierarchy roots on TPMs. The endorsement hierarchy, which is controlled by the TPM manufacturer, also called privacy owner, which is intended for privacy-sensitive data, for validating the authenticity of the TPM, but it's also a bit of privacy concern, because with that hierarchy and that seed, you can really drag down keys to exactly one TPM. There's a platform hierarchy, a platform seed, which is used for the platform manufacturer, the OEM, for basically that instance that ships and controls the early boot code, like UEFI for secure boot, for example. There's an owner hierarchy that is basically the default one used if you work with the TPM from a user perspective on your own laptop. And there's a special one, the null hierarchy. This has no persistent seed. It's get a random seed from the random number generator each time you power cycle the TPM. And that's used, for example, for sessions. Sessions are something like, what's called a secured, what is the word? I don't remember. A secured set of operations bundled together that are encrypted, so all your TPM operations done in one session are encrypted with, for example, HMAC, using the seed from this null hierarchy. And generally, seeds act as the cryptographical root of the hierarchy. Keys based on the seeds can always be regenerated. And yeah, I think that's it for key hierarchies. And the next thing I want to talk about are the platform configuration registers. I think that's the most unique part of TPM, and I think also the most powerful. Platform configuration registers are 24 or more dedicated hardware-based registers holding a hash. You can see with the TPM2 getcap PCR commands what hash is used on your device. SHA-1 is basically for compatibility use cases. I think it's not used in TPM2 anymore at all. And the platform configuration registers are used to cryptographically measure and record software states. This can be done only with really strict conditions. For example, the most of the PCRs can only be set or reset on system boot power on, and on a really specific TPM locality level, which is a bit the same or similar concept as CPU run levels, the rings, the CPU rings. And one really interesting thing with the PCRs, it's they are not written once, but extended. So every state measured with one of the registers extends the already existing value in there. So if the ordering of the operation changes, the resulting hash also change, and the value is not the same anymore. You can detect this and use this to measure the integrity of your system and act and react. There are a lot of these registers. I think not all are used right now. The most interesting are the first, I think, 41, and one that's specifically interesting for use, for example, also for encrypting data, is the number 7, which measures the secure boot state. And I have a use case for that later in the presentation, where it can be used to encrypt a data partition as long as the secure boot is in place and correct. About the locality, there are 4 levels, 5 levels. The 0 level is basically the static root of that. In this level, directly if the system starts, the PCRs can be resetted, and the hash in the numbers 0 to 7 can be extended, and the operating system, Linux, runs in the locality level 4. So Linux would be able to modify the value, for example, for secure boot or all that early components. If you want to have a look on your PCRs on your platform, there are several commands to do that. Systemd analyze, for example, or TPM2 PCR read. And you can also try it out and check. The values shouldn't change normally between reboots. So even if you do an update, for example, the secure boot state must be the same. So yeah, short recap. We learned about how TPM looks like and about some of the major components and concepts in there. So let's go further with the question, how can we trust a TPM? Because here there are a lot of components and steps in the chain. You need to trust the manufacturer of a TPM, the manufacturing process, your system manufacturing process. You need to be sure no one interjects your PCB and sniffs something on the PCB. You need to trust a boot code and provisioning process. And in general, the most of them is not a cryptographical issue. It's rather an issue of trusting the process, controlling the process. And so it's not really solvable only with tech, but a really big issue in trusting your platform. But what you can do at least is verify a TPM's authenticity using the endorsement hierarchy, for example. As said, this hierarchy is controlled by the TPM manufacturer. And the primary keys in this hierarchy are really constrained to one specific TPM. And with that, you can verify it's authentic. You can really identify that machine. So if there are keys generated with this endorsement hierarchy, you can track it down. They're really were generated by that machine, which is also a bit of privacy concern, depending on your use case. And yeah, the endorsement key and key pair can be generated and regenerated using the seed and the specific key generation template. And there's also endorsement key certificate, which gets in there during the manufacturing step. So you can use both of that to validate it's authentic by first using the hierarchy level on the TPM to generate the key pair, read the public key, obtain the certificate, and then you go to your TPM vendor website. You should know which vendor and which model you have or you expect on your platform. And then you can do two steps. First, you can extract the public key and validate it matches the one in the e-key certificate. You extract also from the TPM to make sure your TPM itself is valid and not tampered as a platform. And in the second step, you can use the root or intermediate certificate or both you get from your vendor to verify the certificate and the public key is valid for that platform, and you really have the TPM you expect as part of your product. And yeah, last, some practical examples from some use cases I implemented with Yocto, for example. When you want to integrate TPM with Yocto, there are basically two layers providing the TPM functionality, Meta Security and Meta Secure Core. Basically, both do the same. If I would be asked, I would basically prefer a bit the Meta Security layer. I think it's a bit better from the quality and the maintenance. But depending on your use case, you can also mix and match what is needed. And the first use case I want to tell a bit about is establishing a chain of trust by implementing Secure Boot on an Intel platform with Meta Secure Core, Meta EFI Secure Boot, and Manda as an update client in place. The idea with that is a bit of ensuring your device runs a trusted, signed, and untampered bootloader, kernel, and whatever of binary blocks you want to validate in the first step. And it's about establishing a trusted environment for later application use for critical tasks. For example, to make sure only a trusted device with trusted software can access a cloud platform. And for that, you can also detect if secure boot is disabled during runtime and make sure only trusted platforms really can access your IP. And one thing about ARM platforms, maybe on ARM you rather use some special storage on the device that can be burned with fuses to deploy your secure or verified boot certificates instead of the TPM. That's also a valid use case, bit of another way to build up this initial root of trust, but also a valid use case, just another mechanism. And yeah, if you implement something with UEFI on Intel, it looks a bit like that. You boot into UEFI with secure boot enabled. Your bootloader, your first stage bootloader does check, are the certificates in place, checks the certificates with the TPM, and depending on the check, it either boots up or shows you a red blinking error screen telling you the certificates don't match, and yeah, you can't use the platform like that anymore. And about the implementation a bit, last time I really tested it was with Crockstone. Uses, as told, MetaEFI Secure Boot, which provides you already a lot of tools. Group EFI implementation, EFI tools, mock utils, shim, whatever. It provides also patches for grub, signing tasks in Yocto for kernel bootloader and all that stuff. And already it does the integration with TPM for storing keys, certificates, and looking them up in there. And also provides a grub entry that does the initial certificate provisioning step with TPM at booting up. One thing about that layer is it's mostly described for the use with initramfs. When booting up with Yocto and Manda as an update client, I don't want to have initramfs. I think Manda is also not really aware of using initramfs at all. And also I don't want to have that complexity level in there. So there are a bit of tasks needed to get that done without the initramfs that are not that much documented. And Manda is also not aware of using a boot partition, an EFI boot partition distinct from the rootfs. So you need some extra steps to update the kernels in there, but Manda with state scripts are perfectly prepared to do this task. It's just an extra step to implement. And basically from a Yocto perspective, it's rather simple if you once figured out how to do it. It's integrating the right tools and commands in there. You need to provision the signatures for the kernel images and the bootloader in the boot partition. There's also one trick when using Manda. They process the image boot files variable on their own afterwards and have some issues with multi-line parsing. So it's needed to write all the things you need to want to append to the image boot files in one line to make it happen. Otherwise, the whole thing will crash. And then one important step is also checking the group configuration to make sure the search path is correct. And afterwards, everything should boot up with secure boot enabled on this Intel example. And with Secure Boot in place, you can, for example, make use of the PCRs, especially of the PCR number 7, the Secure Boot state, for encrypting user data. When having embedded devices in field, I think you all know the situation. They're mostly unattended. You don't have a user in place that can type in a password to encrypt a partition. You also want to have really strong security per device in place. And the basic idea of this use case is utilizing the TPM PCR7, the Secure Boot one, or maybe even 0 to 7 or whatever, to measure the system state and make sure you run a trusted kernel in a trusted state, trusted software, and bind then the encryption task to this software state. So you don't need to have any user interaction, but still have a strong encryption in there. And if the device got tampered, for example, if the PCR state changes, or if Secure Boot is disabled, it's not possible anymore to unlock the partition. So, example, for a person wants to use your device in another context, wants to disable Secure Boot, that's perfectly fine from that use case. The data, the privacy relevant data is locked. So here it can't be used in the initial context anymore, but that's fine. And to implement this, one possible way is utilizing systemd and looks and crypt setup, for example. As you want really specific encryption for a device, I think it's easier to integrate it, the encryption part, in the initial boot up step. So you can utilize a systemd service that starts right before the partition.mount step, and then run a script utilizing crypt setup for writing looks headers in the first step and encrypting the partition afterwards. It's split into two parts because of encrypting an existing partition. And afterwards, after this initial encryption is done, you can bind the TPM PCR to your encrypted partition using, for example, systemd crypt enroll, which is basically just a wrapper around the pure TPM commands, which make it a bit easier to do it correctly and secure. And from a Yocto perspective, it's as well not that complicated. You need to enable some package config for crypt setup as well as for systemd. When running on Kirkstone, I think it's valid to speak about Kirkstone right now because it's still active and still supported. You also need to make sure some library implementations are correctly written to your device. There was a bug back in days which does not deploy some of the libraries. So this extra step was needed in there. With ScarfGap, for example, that's fixed. And then you can write a script as seen here on the right, for example. Really a basic example which uses a randomly generated one-time password for doing the encryption in the first place. This password can, for example, be saved afterwards to cloud to make sure you as a system manufacturer can restore the data if something happens to the system, but it can also be just deleted and do whatever you want with that. But yeah, after this initial encryption step, the magic happens with the command down right there, system decrypt enroll, which binds the partition, the Lux partition, to the TPM PCR number 7, utilizing the capability of Lux encrypted devices to have several keys deployed for one encrypted partition. And to open up the device without user interaction, you can, for example, utilize a crypt tab entry, also referencing to the TPM PCR register. A crypt tab entry is utilizes the system decrypt setup generator, which generates on runtime a task for encrypting that partition when the device boots up. And then you can just use the mapper device in the F-step entry. One hint also when using Mender as a client. Mender also modifies the F-step in the rootfs post-process command, so it's really needed to make sure the ordering of your operations is in a correct order to get the FS tab really written. And yeah, as the time becomes a bit limited, no more really use cases, but more ideas how to utilize TPM. For example, you can make more use of the Linux integrity measurement architecture, maybe also together with the Keylime project. You can store sensitive counters, read-only information or whatever in non-volatile RAM of the TPM. Or you can use TPM backkeys for SSH, SSL, your application use or whatever. Or maybe your software stack already utilizes the TPM without you already knowing, which is the place for example, Azure IoT Edge. And yeah, let's recap. When using TPM devices, it can help you with cryptographic operations, random number generation, with trusting kernels and your boot infrastructure. It can measure the system state and help you with integrity issues. You can store tamper-resistant information in the non-volatile RAM, and a lot of more use cases. Just get creative with the possibilities in there. But on the downside, TPMs are there, they're well supported, they're affordable, but when building up an embedded system, it's always an active decision to really take it in, really utilize it, maybe pay the additional cost for integrating one, or the additional cost for integrating a firmware one, and really use it, and really use it good and well. It's not a non-brainer task. There are still attacks on the TPM. For example, if you use a discrete one, there are sniffing attacks on the I2C or SPI bus. It's a thing about who owns and controls the platform. Think not so much for embedded devices down the field that are not really used as a computer, but as the device built with and around the computer. Maybe it's a bit a privacy concern of using TPM if the keys and key infrastructure is trackable down to 1 TPM. And one of the major points, you really need to trust the vendor, the device manufacturer, the PCB manufacturer, and the whole process. And this task, I think, cannot be solved really on a technical level. That's more process thing. And yeah, I think that is. Thank you for your time. Questions?
You touched on this a bit, but do you have any recommendations for when you have a hardware platform where you cannot retrofit a hardware module? For example, AMD EPYC servers, and then you are forced to use the AMD FTPM. Do you have any recommendations when you find yourself in such a situation, what you should do to get more trust in what you get?
That's a good question. Basically, I would try to find out what TPM should be in place and really validate it's the one that should be there. You maybe can also wire up an external TPM. But yeah, this trusting issue is really one of the main pain points in using a TPM.
Yeah, because our UEFI vendor offered to provide source for a significant amount of money, but source is only part of the way there, because then you need to verify that they do everything correctly. In the end, we went, like you said, with an external TPM, but I was curious if anyone actually is using firmware TPMs and is happy with them, because it seems like a huge risk, like a checkbox thing, like, oh, we have a TPM, but not really.
Yeah, I think firmware TPMs also have some pro points, because with this integrating directly on the chip, there's no attack vector like SPI or I2C bus sniffing, but it's always that, yeah, this, which one of the risks do you want to have?
Okay, thank you.
Thanks for the talk. Regarding containers, do you have any status on support for and accessing TPM through containers and sharing keys and so on? Any information on that?
Let me think about it. I never tried it on my own, but I think it's definitely possible to access TPM from containers. Maybe you can also use software TPMs for hypervisors, for example. But sharing the resource has also some risks. So this trusting matter is still an issue.
Hey, I wanted to ask about the PCRs. So when you power off your machine and power it on again, do the PCRs in the TPM survive, or is their state regenerated every boot?
They are regenerated at each boot. So it's really needed when they're regenerated, the same ordering happens to receive exactly the same value in the register. And that's basically the point of measuring the integrity. If they would survive in there, the whole trick of that won't be working.
Thank you.
So continuing to the PCR questions, a use case that I often meet is that if we want to include GPL3 in the firmware. We cannot really use secure boot because that would not allow the user of the device or the owner of the device to actually flash new firmware, modified firmware at least. So instead we want to use measured boot only and then unlock the data partition only if we boot something that we trust.
Yeah.
But how does that work with an AB update scheme? Can you have like multiple hashes bound, PCR hashes bound to a device, encrypted device? So that you can actually update the other partition and say this is also a valid boot sequence?
Yes, that should work. You can basically use several key slots for LUX encrypted devices, I think around 7, if I'm right. And you can basically use any PCR you want. 7 is the most common used, the secure boot state. But in fact, it will work with everything that really has a predictable value and will not change the value over time.
Okay, thank you.
One more question.
Great talk, I've enjoyed it. Thank you very much. So one of the things that I was facing is a problem. Actually, I mentioned it with a private conversation yesterday at the party with Lena. It's on boards like Raspberry Pi, where you don't have a built-in TPM, one of the options is to attach a TPM20 over SPI, but obviously there are some risks involved due to the option for men in the middle of attack, someone to listen to the communication going on the SPI bus. Obviously, there is probably not a perfect solution, but what are the best practices to avoid this or to minimize the risks?
That's really a good question and one of the important ones when working with TPM. I think one possibility would be really checking the TPM device is the one expected, the way I showed, for example. Or make the whole hardware inaccessible. That's not a really good solution. But yeah, basically that are the really hard questions when working with TPM. It's not really about the implementation. It's not about the cryptographical tasks. It's really about securing that process steps and make sure this path is not tampered on a physical level.
Thank you very much.
Okay, thank you. Okay, before we start the next speaker, I just wanted to make a couple announcements, some things that I forgot to mention yesterday, so I thank you for your forgiveness for us being newbie organizers. But for about lunch today, just a reminder, so here we have the menu today. All the bags will be the same. Everything will be vegan, vegetarian, so there's no options to pick from. And also yesterday, so if you go out to the park, there's a food vendor out in the park with some tables. Please do not sit there. They yelled at us yesterday. We took all their places and people that were actually buying food didn't have any place to sit. So keep walking a little bit. If you go out even farther around the lake, there's lots of benches, there's places to eat, so just please don't sit by the food vendor themselves. Also today, there's going to be, if you look at the schedule, there's a couple small slots. We're doing some lightning talks today, so there'll be some short 15-minute slots mixed in, and then a bunch of them at the end. And then I had to reshuffle the schedule a little bit because we had a speaker have to cancel because of illness yesterday. So we reshuffled things around and found ourselves with some extra room at the end of the day today. So we're going to do, because Tim Bird is here, has anybody been to Embedded Linux conference before? So we have, Tim is gonna do his closing game for us at the end of the day today to help close things out. And we have some, not sure I'll say prizes, we'll say surprises, because I don't know yet what they're going to be for the winners of the game. But we'll figure that out, as Tim always does. We figure things out on the fly. So we're going to end the day with our closing game after the round of lightning talks. So just a few little bits for today, and then we'll get going with our next speaker, who is Olivier, to tell us about SteamOS. Do you have HDMI?
Seeing it.
It's Windows. Huh?
No, it's
You are in extended. Ça marche quand tu fais ça?
All right, good morning. My name is Olivier, and I work at Igalia, and I'm going to discuss work on SteamOS and the impact it has on the broader Linux ecosystem. So in 1998, about 27 years ago, Valve released Half-Life, a game which had a lasting influence on the first-person shooter genre. Back then, I was 15 years old, and boy, how many sleepless nights did I spend fighting aliens to take Gordon Freeman through Black Mesa. and also countless hours designing and testing maps in the map editor that was called WorldCraft. Those were really good times. That game only ran on Windows, and at the time, I don't think I was particularly concerned by this limitation. In fact, my experience with Linux and other OSs was anecdotal back then. Fast forward 15 years, in 2013, Valve released the first version of SteamOS, which was based on Debian, followed by version 2 in 2015. Version 3 was initially based on Debian, but it was later rebased on Arch Linux during the development cycle. The latest stable release is 3.6, and 3.7, currently in the beta channel, is just around the corner. Making Linux work as well as possible for as many games as possible is a very large effort. For a few years now, we've had people at Igalia collaborating with Valve in the development of SteamOS. So we have a number of kernel developers, graphic drivers experts, multimedia hackers, CI wizards, and OS integrators, all contributing to the project, along with contractors from several other consultancies, all of this under the direction and coordination of Valve. I myself joined the project recently in December last year. And I'm going to try to give an overview of the contributions that my colleagues have made to SteamOS in the past, and those that we're working on today, and their impact on the broader Linux ecosystem. But before I dive into specific contributions, let's have a quick look at what the hardware side of things looks like. So the Steam Deck was made available in 2022. It sports an LCD display, an AMD Zen 2 CPU, and an RDNA 2 AMD GPU. At the end of 2023, an OLED version was released with newer Bluetooth and Wi-Fi support and a better battery. What's really interesting is that the development of SteamOS isn't constrained to one single device or family of devices. In many ways, SteamOS is designed as a general-purpose OS with a strong focus on gaming, of course. So one interesting example is that there's the default gaming session, of course, which is known as GameScope. That's also the name of the microcompositor that it runs. And there's also a fully featured KDE Plasma session. And switching from one to the other is a fully supported use case, not an afterthought. A lot of care is taken in making sure that the desktop session works well. And now there is a new Legion Go S made by Lenovo that's available with SteamOS pre-installed. So it's going to be interesting to see what new devices come out in the future with SteamOS as their base operating system. What's for sure is that the availability of several devices means that SteamOS becomes ever more relevant, and the contributions that I'm going to talk about as a consequence have a greater impact on the entire Linux ecosystem. I think I said it already, SteamOS is a huge effort, and there are many teams that contribute across the stack, including working on Mesa drivers, conformance testing for Vulkan, Vulkan Video, GStreamer maintenance, Proton maintenance, etc. I'm not going to talk about everything, that's a lot, but let me dive into some of the most interesting contributions that have happened lately. And let me start with contributions to the Linux kernel targeting various subsystems. With a big word of disclaimer, I'm not a kernel developer. So since version 6.6 of the kernel, the default scheduler is EEVDF, the earliest eligible virtual deadline first. And since version 6.12, we have the SCADEX framework, which allows writing custom schedulers using BPF. My colleague, Chang-Woo Min, has been working on a custom CPU scheduler designed specifically for gaming workloads. He calls it LAVD, which stands for Latency Criticality Aware Virtual Deadline. LAVD in many ways resembles EEVDF, but it puts more emphasis on latency-sensitive applications, like games. The core ideas behind this scheduler are, one, measuring how much a task is latency critical, and two, leveraging this information in making various scheduling decisions. One important factor to take into account is that while there are some Linux native games, a vast majority of the games that are being played today through Steam are Windows games running on top of Proton. So this makes it impractical for games, if they were able to share latency hints with the kernel. And there are critical tasks, such as wine server, when you run Proton, that would be penalized by a completely fair scheduler like EVDF. And that would result in an increased latency, the visible consequence of which might be a reduced FPS. And we know how FPS is an important metric in games. So one of the ideas in LAVD is to loosen the eligibility enforcement, which means it doesn't try to enforce short-term fairness, but it does try to guarantee eventual fairness. And they say a picture is worth 1,000 words. In this case, I think a video is worth even more. So let me show you a demo recorded by Changwoo a couple of months ago, which demonstrates the benefits of LAVD with gaming workloads. So this is Space Marine, a game that's available in Steam, and we're currently playing it with the default scheduler. As you can see, CPU usage is around 70%. We have a good solid 60 FPS. And the graph at the bottom represents the frame time, so the time it takes to render frames. It looks pretty good, pretty much a solid line. And now, wait for it, we're going to do something interesting. We're going to launch a CPU-intensive background job to see how well the game performs with that additional workload. As you can see, CPU usage bumps to 100%. The FPS drops to about 20-something, and the frame time is all over the place, and the values are not good. And the visible consequence is the game is lagging, terribly lagging, and it's not playable anymore, basically. And you can see even when idle, we're not actually moving in the game. That's not any better, or only marginally on the FPS side. Now, wait for it a little bit more. And we are going to launch the LAVD scheduler and see what happens. So what's pretty cool is that it's just replacing live the default scheduler. As you can see instantly, so CPU usage is still at 100%, but we regained a good number of frames per second. We're between 40 and 50 FPS. The frame time looks much saner, and the game becomes playable again. So there's a big improvement there. That's it for the demo. So there are many subtle details in LAVD, enough to fill an entire talk. So I'm not going to go into them. But if you're interested in the topic, I highly recommend watching the recording of Changwoo's presentation, which he gave at the OSPM summit that happened in Germany in March this year. In itself, that's already a very interesting improvement to have a more suitable scheduler for gaming. But Changwoo is taking it one step further. He's trying to identify how a general purpose scheduler can benefit from the work on LAVD. So in the future, we might see improvements to the default scheduler flowing in from there. Okay, let's have a look at another area, the DRM scheduler. So that's the component used by multiple GPU drivers to resolve dependencies between work submitted by user space, pick the most optimal GPU engine to execute those tasks, and also identify the best order of execution to balance interactivity and throughput. My colleague, Dvorko Ursulin, is working on improving that. So he's been working on alternative scheduling strategies which remove the current problems of priority starvation and improve fairness. The latest version of this work is the Fair DRM scheduler proposal, which borrows some of the concepts of the default CPU scheduler and applies them to GPU scheduling. I must note that there are certain limitations derived from the fact that GPUs generally do not allow for fine scheduling precision. And to allow more modern use cases, he's been working on a DRM scheduling C group proposal, which is broadly speaking aiming to allow for external control of the DRM scheduling decisions. Because despite the fact that a lot of the GPUs and their drivers are able to prioritize execution between different levels, there is currently no way to convey the importance of tasks from the outside in a manner similar to the Linux NICE levels or CPU or I/O C group controllers and their relative weights mechanism. So the DRM scheduling C group controller proposes to add such a mechanism by building on top of the Fair DRM scheduler proposal. That would enable interesting use cases, for instance, with window managers, which would be able to mark focused versus unfocused windows, and by doing so, improve the user experience by enabling lower latency rendering in the focused application. Or from the opposite angle, one could allow for deprioritizing background applications. Let's have a look at HDR support. So my colleague Melissa Wen has been working with the community to develop a generic kernel mode setting API. The goal is to allow user space to offload color transformations required for HDR and other tweaks that improve the overall user experience to the display hardware. This offloading is especially important in GPU-intensive scenarios, like gaming, as we can use dedicated display hardware blocks for advanced color management and save the GPU the work of performing such transformations through shaders. To support this discussion and provide experimental means of evaluating these capabilities on display hardware, we also exposed on the kernel side AMD hardware color capabilities through driver-specific properties. This work enabled the launch of the OLED Steam Deck, which I mentioned previously, with an integrated display with HDR support, and that provides Linux users with a better gaming experience. And this initial support in GameScope, in turn, served as a catalyst for HDR support in other parts of the stack. So the Plasma desktop, or GNOME, for instance, with the release of version 48 a couple of months ago with initial support for HDR. We also hosted last year the Display Next Hackfest that brought together different stakeholders in the Linux display stack to share knowledge and consensus. Our goal is to use all the resources available in complex and robust GPUs, like those manufactured by AMD, to provide the best experience and performance for the Linux user. All right, I'm changing topics, and we're going to have a look at a couple of interesting OS integration projects. My colleague, Alberto Garcia, has been working on enabling hard drive encryption, which is considered an important feature nowadays, especially for a portable device, which is more easily lost or stolen than a desktop computer. In fact, this is a feature that has been demanded quite vocally by users, and because it's not available out of the box, a number of tutorials and how-tos appeared on the internet with instructions on how to encrypt a Steam Deck. Not being official solutions, they're not necessarily future-proof, and they don't really offer guarantees. And the last thing you want is to lose your data because you're unable to decrypt it when you intended to protect that data in the first place. So Lux was considered, but there are several downsides to encrypting a whole block device, even though it is definitely the most secure option. Because encryption was not baked in from the start, one scenario that we're keen to support is encrypting an existing drive easily without requiring an extra backup. It should also be possible to remove the encryption if one wants to do that. So the approach that was chosen is to use FSCrypt to encrypt selected directories. It's not the most confidential option. In particular, metadata and extended attributes are not protected, and it's theoretically possible to tamper with files without the encryption key, but it was deemed a good compromise between security and user experience. And after pondering the options, it was decided to write a tool to provide the encryption and decryption features, both as a command line interface with a PAM module and as a dbus API. That tool is called DearLock. It is currently under active development. It is written in Rust, and it is expected to be announced publicly very soon. Very soon being a matter of days, I'm being told. Another interesting project, more specific to the gaming session, is desktop portals. So they're a standardized mechanism and a set of APIs for sandbox applications to gain access to functionality provided by the host system. A typical use case is gating access to certain hardware or files behind a user prompt, similar to permission prompts on mobile operating systems or in web browsers. Desktop environments such as KDE or GNOME have their own implementations of portal backends, but they're not suitable for a gaming session because that gaming session is a full screen surface and has no way to pop up prompts. And you don't want prompts to be popping up when you're playing anyway. So I'm currently working on a custom GameScope portal backend that implements among other things, the screenshot and screencast interfaces. In both cases, the actual functionality is delegated to the compositor, which takes a screenshot and saves it to disk, and also exposes a Pipewire stream to cast the contents of the screen. The custom backend differs from existing ones in that it doesn't prompt the user, and it doesn't offer extended options like selecting where to save the image file, or cropping the captured area, or selecting a different window, these kind of things. Another interesting difference with most existing portal backends that are written in C or C++ is that this one, as an experiment, is written in Rust, and it leverages a really cool project called ASHPD, which stands for Aperture Science Handheld Portal Device, which is, by a funny coincidence, a reference to another Valve game. All right, this was just a brief overview of some of the contributions that Igalia folks have made and are making to the greater Linux ecosystem through our contracting work with Valve. The benefits are many and go way beyond the gaming universe. One important thing to highlight is that Valve has a healthy upstream-first approach. So the work on SteamOS has a direct positive impact on many upstream projects. And please bear in mind that most of the work that I've presented isn't mine. So I couldn't go into all the savory details, but I hope I managed to catch your curiosity regardless. And now, if you have questions, I'll do my best to answer them. And if I can't, I'll be happy to put you in touch with my colleagues who are the respective experts in their fields. Thank you.
I'll take a chance if it's your domain or not. About the portal, have you considered trying to extend the existing basically screencast and screenshot portal that we have and basically give a full screen application a trust to actually implement its own UI?
That's not something that I considered. I mean, the game scope session already exposes Pipewire node that casts the contents of the screen. So it sounded quite trivial to implement a portal that just didn't prompt the user, basically. That's respecting the existing API.
I understand the simplicity. I'm just thinking about the other compositors that may run games in the.
All right. I didn't.
Just the big portrait I was thinking about here. Yeah.
That's not a use case that's been considered, but that's an interesting idea. Yeah.
Thank you.
Thanks.
So do you know anything about contributions to wine? Since it's so much dependent, maybe not by your company, but in general?
I'm not myself working on this. I'd swear we have people at Igalia working on this. There's also people outside contributing to wine, but I, you know.
Oh, well, that's good already.
Not my field.
Are you involved in replacing NVIDIA blob with open source driver? When can we ditch the blob?
I have no idea.
All right.
Sorry.
Nice talk, by the way. Can you expand a little bit on the Lovely scheduler? That was a wine game, so there was no control of Linux scheduler priorities. And what kind of background task did you run? It was CPU-based or IO-based?
That's a very good question. I didn't record that demo, and I should have done my homework and asked Changwoo what kind of task he used. I don't know. That's a very good point. It would be interesting to know exactly how exactly that task is stressing the system. Yeah.
Okay, thank you.
Since, in my understanding, that's an AMD device, so the GPU is AMD as well. Could you, I think, is it correct?
Sorry, I didn't get it.
Since the Valve deck is an AMD device,
Yeah.
the GPU is AMD as well,
Yeah.
right? Since I don't know much about that, could you brief us about what is the current upstreaming state of the support for the AMD GPUs in Linux kernel? If it runs blob, it's completely upstream. I know anything about that.
So that's not me personally working on this, but all the work is happening upstream. So all the again, sorry, I'm not the best person to answer that. I hope not much. if any at all. You know, it's been in the kernel for some time now. Hopefully by now, any overhead, any important overhead has been ironed out. But yeah.
Okay, thanks. One more, maybe?
As far as I understand, the SteamOS is reserved for the Steam Deck and the Lenovo Legion, if I recall correctly. Will we see a day where I could install SteamOS on my own desktop PC?
Oh yeah, it's totally doable today. It's that's one of the things that I was trying to convey. It's you can grab a SteamOS image and install it on any device, and it's that's one of the important things that we focus on, making sure that it works out of the box on as many devices, computers as possible.
Do you have any timeline for this release?
Which one? The
The
work that I
SteamOS
talked about,
available
or?
on any PC?
That's already available
that's already
today.
the case.
Yeah, you can download images and install them.
Okay.
And I mentioned 3.7 is just around the corner. I think the plan is to release it at the end of the month.
Thank you.
Is that only for devices with AMD GPUs, though, or is it generalized?
It's better supported on AMD GPUs, but there's no reason it wouldn't work on other hardware.
Okay.
Okay, in that case, how do you manage people pirating games and stuff if you're allowing open platforms to play the games?
Sorry, I didn't get that question.
Well, okay, so I work for Sony, and we had Linux on one of our platforms, and we had to stop because people were pirating games.
Oh.
And so it's an issue with like the GPL, and requires that you support reinstallation, or there's issues there. But I'm just wondering if you have an open platform where you're putting Linux on like an average desktop, how do you ensure the integrity of the gaming experience? Or have you, maybe this is out of your...
That's not my, my field, sorry.
I think we have one question from the online chat here.
All right, our first online question of the day. Is the Lenovo device using the exact same image as the Steam Deck?
The exact same?
Image as the Steam Deck.
Yes.
Thank you.
Okay, thank you very much, Olivier.
Thank you.
Great talk.
I had a last slide to say that we're hiring, but it's gone. So if you're interested or if you want to continue the conversation, please come and talk to me. And my colleague Martin was here.
Zim?
Just Zim, yes.
Okay. If you simplify it.
Yeah. I would have changed it in my, when I got a video.
Okay, let's get started again. I'm going to introduce our next speaker. Our next speaker is Zim from Google, who's going to tell us a little bit about using Perfetto tracing tools. Welcome, Zim.
Thank you for the intro, Kevin. All right, so my name is Zim, and I'm here to talk to you about Perfetto recipes for Linux kernel development, but also user space. I plan to make it a bit interactive, so I have some examples I've created, some traces. Hopefully you find it interesting. What do? I work at Google as a software engineer on Android OS. I'm not part of the Perfetto team, but I work very closely with them, and I contribute a fair amount to it. Most of my job is spent helping other engineers at the company on Android debug and build tooling to understand the performance bottlenecks. Right, that's enough about me. Here's what we'll be roughly covering today. Some introduction. It was good to chat with a bunch of folks yesterday, and I saw some people are familiar with Perfetto, so hopefully the introduction is helpful anyways. This is going to be a cyclic test demo. I have to say at this point that a lot of the examples here were contributed I was assisted heavily by my colleague John Stultz, who is a scheduler expert. I'm not a Linux kernel expert, but I think hopefully these examples are interesting. And then there's a instrument and user space demo, and hopefully time for questions. So yeah, let's get started. All right, so who's this talk for? Well, everyone. I really hope everyone can get something out of it. It's getting to lunchtime, so people are getting tired. But hopefully, at least you take something away, even if it's just how to set up Perfetto on your machine. If you're an expert user, hopefully some of the examples help you with your problems. And yeah, let's go on. So what is Perfetto? It's a bit of a difficult, it's an overloaded term, so hopefully this diagram helps. It's a much simplified diagram. They have a slightly more complicated one, which I would show at the end of this section. But it's all these things. It's a web UI, it's a SQL backend, it's a data format, and it's a bunch of Linux binaries. You can head over to perfetto.dev to see much more detailed and nice flashy website. And arrows are important because sort of conceptually, each of the things from right to left feed into the other. So Linux binaries provide data formats, and data formats allow the SQL backend something to query, and you visualize it with the web UI. But I will explain sort of these components very briefly from left to right. Okay, so here's a screenshot of a web UI. I will show a lot more detail about the UI and help you sort of get a grasp of how to navigate it. A lot of the navigation is WASD, so I'm sure a lot of you will be very comfortable with that. The web UI is accessible from ui.perfetto.dev, so you can capture data from any sources and just open a file on the web UI. It's important to note that the web UI doesn't have a server backend. So any data you upload is not, Google doesn't see it. No one sees it. It's completely on the client. You can turn off your internet and upload open traces with the web UI. It's a common question that we come across. And there is some Google Analytics, but besides that, just to know what pages you click, but none of your data leaves the web UI. So what does it do? It helps you, obviously, with a lot of embedded people here, so you probably have performance bottlenecks that you're debugging. I was interested in talk right before about the Steam OS. I'm actually curious if they use Perfetto. But it helps you organize and visualize time series events. That's sort of the simplest explanation of it. Those events that could be from anywhere, depending on your field. Could be CPU, IRQ, memory, running processes, all sorts of things. So there's some opinion in how things are laid out in the UI, but there's a lot of data that you can really investigate with it. And usually, the cycles I speak to people are not very big fans of SQL. I think it's actually one of the very powerful functionalities in Perfetto. This diagram is on the website as well, and it's sort of auto-generated from the doc, so it's as true as true as the documentation is in the code. This is a snapshot of some of the tables that exist. So, coming from our left to right, the web UI, all it does is a pretty dumb UI that just talks to a SQL database. And that SQL database, we will get to it. We'll get to how it's created, but you have a lot of tables in it. And some of these tables are opinionated based on common problems people have tried to solve, especially on Linux. And this is a snapshot of some of the tables that exist. So there's slices, which is the little rectangles, which you will see in a second. There's ftrace events, which you're all familiar with. There's SCED. There's spurious SCED wake-ups, which the details of these is not that important at the moment, but it's just to give you a flavor of the kinds of data that exists in the UI. And you can query all this data and join them in all sorts of interesting ways. And the arrows you see in this diagram is sort of describing some of the joins between different tables and the join columns between them. Speaking of data formats, so Perfetto supports a lot of data formats. There's the Perfetto native data format, which is if you sort of stay within the Perfetto ecosystem and use the tools on your machine, or which you can download and install on your machine to capture traces, you will be able to, obviously the Perfetto UI would be able to interpret it. But you can also capture data from multiple sources, and it supports a bunch of formats. There's the Android systrace format. There is the ftrace text output, so you can basically just dump whatever you get from your trace markers file as a file and open it in Perfetto. It opens JSON as well, and there's some interesting use cases of debugging stuff with massively nested JSON files. And I'm not going to go into that today, but if you're ever thinking of writing a JSON parser, maybe consider Perfetto. It also supports perf files. So if you capture perf record and capture a bunch of samples from CPUs or whatever trace points you have, you can open it directly in Perfetto. You don't actually have to. You can capture perf events with Perfetto, but you don't have to capture it with the Perfetto toolbox. You can take your perf files that have been generated from any machine and open them in Perfetto. It's actually not a very common, so it's not a very popular feature, but you would see why. I don't think we have time to get to that anyways, but it's a really powerful tool when you get to for visualizing flame graphs. Okay, so we're getting there. The richest format is the Perfetto native data format. How do you capture data with that? What does it really do? The bottom line is, it reads data from a lot of data sources on your device. So TraceFS, ProcFS, SysFS, and it manages, enabling data sources, and it gives you a nice configuration format to do that. And you can configure how much to read, what data sources to read, what's the buffer sizes to keep, what's the policy for the buffer sizes. It provides all this nice standardized format to access a plethora of data sources from on your Linux machine, and you can add more data sources. You can, a lot of people contribute things to it that are not even sort of Linux host machines. So there's all sorts of contributions even from VMs. So you can also trace things running in your VMs. And all of this is wrapped behind a nice, handy binary called tracebox. Behind this tracebox, there's a few tools, but this is a bit too much of implementation detail. But with the tracebox command, you can basically instantiate all of this and start a tracing session, capture data that you might be interested in. All right, so now you're an expert. Here is the website version of what is Perfetto. Obviously, I highlighted in red the things that hopefully may be a bit familiar from what the few minutes of this talk. So on the left, you see the system tracing. You can read data from Linux ftrace, proc pullers. There's some things that are Android specific, but the Perfetto tries to be quite useful also outside of the Android and Chrome OS ecosystem. In the middle box, you see the trace processor, which is really the brains behind the data format. So on system tracing, this is everything that happens on the device. And then you get into sort of how do you've captured some standardized nice data, how do you organize it? And that's what trace processor does. So it's a C++ library, which runs in WASM in the browser, and which is behind the UI. And that's what creates all the tables and allows the data to be easily queryable, because the format they write into is optimized for writing, and SQL is a much more optimized format for reading and querying. So this is sort of the brains of the whole thing. And Perfetto UI is what most people would interact with, and you can, that's sort of the high-level overview, but you can head over to perfetto.dev/docs to see a lot more information on this. All right, getting started. I'm not going to do all of this now, but you can download the release from the GitHub page. There's official build instructions here, and there's some unofficial instructions for some additional configurations you might want, written by John Stoltz in his gist on GitHub. Some of the things there are probably on by default in most machines, but obviously you need like config ftrace, kernel config. If you need function graph tracing, you need to have those enabled. So there's a bit more, some more detail there that you might be relevant to embedded folks. All right, so hello world. Let's start with a simple config. I've said a lot, mentioned the name config a lot. What does it look like? Config is really just two, for the most part, is two pieces of information: buffers and data sources. And the buffers is what sort of the tracing daemons manage. It's what the tracing daemons manage, and you specify how much size how to size those buffers, depending on your data and depending on the size of your machine. So in this case, this is really large buffer size for what it is, but you can have as small as a few kilobytes for data that's not frequent. For tracing things like SCED, you can usually overrun the buffer, and there's a few policy, in which case this is just overwrite the ring buffer. And on the data source side, this is where you would spend most of your time configuring things, and there's lots of examples on the internet also. So you can also try some AI generation for the Perfetto configs. I've heard it's not very good, but you might get 99% there. For the most part, there's Linux ftrace data source is the data source you would care about. You specify the buffer, which is this will be in the same file. I just separated it for the slides. So you specify the buffer. By default, it picks the first buffer. So if you don't specify any target buffer, it's just going to pick the first buffer. It's 0 indexed. And then you specify the ftrace config. And this is sort of the interesting stuff. Here, I've picked a very simple config, which I think, as a start, if you just really want to get things started, SCED switch and SCED waking events are pretty interesting configs to run just to get a sense of what's happening on your system. There's a lot more you can add, but let's start with that for the hello world. And here's a simple trace output, which I will now switch over to some actual traces to guide you through this. Okay, so this is the hello world config. So the slides will be shared, and there's an appendix with all the traces here, so if you want to look at them offline, you feel free to do so. The traces were either taken on a Raspberry Pi 4 or a Intel, like a x86 NUC device. and you can see the details of which device it was taken for. So the first thing I would recommend doing when you open a trace, it opens you to this sort of timeline page, because that's considered where you spend most of the time. But one of the first things I would probably do is to head over to Info and Stats. I can make this a bit wider because a bit, okay. So one of the first things I'll do is to go to Info and Stats. And this shows you a bunch of detail about what was collected on the devices. So it shows you the trace size, system machine, this is name, kernel version, and this is the config. So this is pretty handy because it means the traces in themselves are self-documenting of the configs that were used to capture them. And you can literally copy-paste this into a file and run it again, and you would get the same config running. There's a bunch of other things, debugging stats. I will show an example. One other thing to keep in mind, but it's not present in this trace. So if we go back to the show timeline view, note that the UI is also constantly changing. I'm currently on the auto push, which is the bleeding edge version. So you might get a slightly different UI from what I see, because there's a bunch of things like flags which you can enable, and you can change the version you are on, and plugins which you can enable. So there might be slight differences in what you see if you run this yourself. So the first thing you see is tracks for every CPU you have on your machine. I would see if I can hide this. No, I can't. Okay. The first thing you see is tracks for everything for every CPU you see on your machine. You can zoom in, so using WASD to navigate. So W zooms in, S zooms out, A D. So. You can click on any task at any point, and this tells you, what was running on that device, on that core at the time. In this case, this is a K-worker task. You can see the priority of the task. This is a normal task. There's a bunch of more detail, but I would try to highlight the things that I typically do. This is a pretty empty, the device is not doing much. It's pretty idle, and we'll see slightly more interesting traces, but just to give you a sense. In some cases, let's see if I can find an interesting task that was woken up by something else. Let's see. There's a lot of K-worker tasks running that are not particularly interesting. Okay, all right, this is a good one. So in this case, I clicked on a task, and the nice thing about it is you get by default in this view is it shows you the wake-up latency. So you click on a task, it tells you, well, the task ran for 34 microseconds. But it was woken up at this point, and you can see the details of the wake up. So it tells you, here's the wake up time, which was on CPU 3. Here's the task, the name of the task, and here's the scheduling latency. So you can do this for any task that was woken up by CPU. For IRQ tasks, it tells you it was woken up by an IRQ, but you need IRQ information to get a bit more detail about what happened there. You can also look at the process view. So what I just showed you was the CPU specific view. You can look at the process view. In this case, I was running Emacs at the time. I guess not much happened, but you get some useful information already, right? So it tells you, over this period of time, the task was running on the CPU. And if I press M, it shows me, I get a nice bounding box of what was happening, and I can see, yes and true, this was running on CPU 1. Over here it was runnable, so it tells me, it was preempted, so it didn't get to run until it ran here, and I can click back here and see, it was preempted by this K-worker task. So you can really, dive deep into details to see. Over here it was an uninterruptible sleep. So all of this information is gotten purely from ftrace. You could, there's no, and it's sort of created a UI that is hopefully helpful for most people. But you can look at the raw ftrace events as well. So if the CPU view or the thread process view is not cutting it for you, you can go into the raw ftrace view. And it's unfortunately a little bit hard to find, but if you click on this little arrow here and click on ftrace events, then you get a sort of constantly updating view of ftrace. So if I zoom completely out, if I zoom completely in, there's no events. If I zoom out a bit, I start to get more events, and I can see the details of those events. So if I sort of wanted to figure out what are these events over here, they're not clickable, but you can see, there's just one. This was a sked weekend event. You can see detail about the trace point. And if I zoom, out a bit more, I see sort of these 3 events. So you can really navigate, and once you can either navigate that way, or if you scroll along here, you get a nice line that tells you where you are in the timeline. So a key part of Perfetto's success is in the UI is constantly giving you context about every trace event that you have and how it fits in with whatever happened on your device. So let's get back to the slide so we can get into slightly more interesting examples, but hopefully this gives you a starting point. Oh, there's a command palette which I should also mention. So if you're familiar with VS Code, Command-Shift-B, there's tons of commands to find, and you can sort of search, and it has fuzzy search, so you can search for a bunch of things, and there's so many events that I'm not going to go into most of them on this talk, but it's something to know that you can trigger. So just to be mindful of time, I'm going to get back into some more interesting examples in my slides. So there's an example here I captured with, from a not busy device. So I ran a toy workload. I used a tool called Dido, which was developed by a colleague at Google. I wouldn't go into the details of the config, but roughly all it does is allows you to specify as a config workloads. And I specified a bunch of CPU workloads, and so 3 different tasks running on, pinned on CPU 2, I guess, in this case. And the goal was to show the CPU frequency response to the tasks running and not running. So there's some periodic tasks running, and just to see the CPU, visualize the CPU frequency response. So if I go to the trace, this is the trace for that slide. Like I said, first thing, I head over to info and stats. So it's interesting because you can see here it does tell me that there was some data loss from ftrace, and this is something you generally want to avoid. In this case, it was fine. It doesn't really matter for my use case, but you generally want to avoid ftrace data losses. So if you do see it, you probably either have to increase the size of your buffers or reduce the number of events you're tracing. So there's some finesse into it. Here's the data source I captured. This has a bit more things. The interesting bits, buffers defined here, data sources defined here. There is sked switch and power CPU frequency. So this is what gives me the CPU frequency tracks. There's a bunch of things on process stats. This is mostly to get process tree organization, so that without these, you would just see all the threads pulled out of every process listed as a flat list. But if you provide this data source, then it scripts proc command line and figures out the process tree hierarchy and then groups threads within processes in the UI. And that's really all there is. Okay, this is a CPU frequency period to also sort of pull CPU frequency from CSFS if we don't have, if CPU frequency hadn't updated, at the start of the trace, for instance. All right, so here's a trace very similar to the one we had before, but now a lot more load. This is this task called normal prior. The tasks was running the workload. And you can see similar tracks, but now you have some additional new tracks. You have 4 new tracks for each CPU core, and you can really zoom in and see how the CPU frequency changed over time. So on this Raspberry Pi 4, I think the frequency is between 600 megahertz and 1.8. So you can see the frequency changes. You can see as soon as the tasks stop, the frequency ramps down back to 600 megahertz. Tasks start again, frequency ramps back up to 1.8 gigahertz. It took me a while to generate this trace actually, because I tried with RT tasks, and RT tasks, as soon as you run them, they ramp up to the max frequency, which was not a very interesting trace. But I was able to come up with something that showed a bit more interesting CPU frequency growth. To reproduce this, I also had to change to governor to sked util. But anyways, the point isn't so much the workloads themselves, but I'm just providing the context on how this was generated, but that you can visualize this, right? So you probably have your own workloads that you care about, and you might want to see, investigate this. There's some additional, so I guess if I open here, this is the tasks running. As you would expect, there's not too much happening. But as I mentioned, you now get a nice sort of, this is the tree view I mentioned earlier. So for each of these top-level tasks, these are processes, and when you click on them, it shows you the different threads within them. Without the process stats scraping, you wouldn't get this hierarchical view. All right, back to the slides. Function graph tracing, this is probably one of my favorite examples. This one, John helped contribute. I'm sure everyone here is familiar with function graph tracing in the kernel. It's a bit of a pain to reason about if you get a massive dump of function graph traces. With Perfetto, well, you can visualize all of that. So this was a simple, so I guess let's head over to the trace and see what was used. Graph. Yeah, so enable function graph. There's a bunch of ftrace events. Ftrace events keep growing. There's enable function graph, true, which is the config that enables function graph. And then you specify what's the graph root. So at what point, at what depth of your functions do you want to start capturing, function names do you want to start capturing traces for? And that's all. And you go to the trace, and boom, you have function graph traces in view with everything else. You can visualize all of this. You can, you have all your, you can highlight, you can select multiple, and this is one of actually my favorite features. So over here you can see it's a bunch of TCP requests being received. You can pin this, for instance. Now I pin it, it takes up too much of my screen. And you can look at, a different, hierarchy, no. Yeah. So you can look at a different track called Hierarchies, and you can reason about what was happening. So yeah, this was an hierarchy that arrived. There should be a network one, soft hierarchies, I guess. Yeah, so this is a network hierarchy, and you can see, you can really visualize hierarchies arriving on your device and the function graph in the kernel at the same time. I'm going to unpin this because it's a little bit hard to visualize. But one last thing I'm going to show in this page is, if you have multiple of these function graphs, you can condense them into one graph. So let's say over here there's a bunch of things. It might be hard to reason about the hierarchy of all of them. You can just simply select over all of them, and you get this details panel that merges everything into one slice flame graph. So this, this is, if you're familiar with flame graphs, the x-axis is not time. This is just an aggregation, a weighted aggregation of duration spent in each depth of your functions. This is a pretty useful UI tool in my opinion. There's a bunch of other things like pivot tables and slices, but I wouldn't go into it now. And let's move on a bit more to even more interesting demos, hopefully. So this is a demo on a cyclic test. It's the RT cyclic test in the kernel. This John really helped me a lot with, so I have to thank him again for it. He also has a handy script that helps run this test. So I guess what the test is basically, I guess, a test used in the kernel to measure wake-up latency of tasks. So you run it, and you get some statistics on wake-up latencies of tasks. Like it runs a bunch of RT0, highest priority RT tasks. You can see some statistics from it. Here's an example run. So in this case, this is just running the cyclic test. Like his script is also linked in the slide, so you can take a look offline. It just runs a cyclic test, and it shows you the average, the max wake-up latencies across the different cores. This is on his Nook device, I believe. And things are fine. There's no egregious wake-up latencies. But you add some load, so he runs this, now this is the script that he runs, which does a bunch of iperf work to simulate, to create network requests, and a bunch of DD for block load, for IO load. And you can see there's a wake-up latency of 1.1 milliseconds on CPU 4, and that's not great for an RT high prior task. And where did this go? I guess this is the challenge, right? So this he ran this and then captured a trace, and this is what the trace I'm gonna show you here. So this is what a trace looks like. Well, where's the scheduling the wake-up latency? Now this is the goal of this demo is to really show how much SQL can shine in cases like this. And I am going to, hopefully show incrementally this demo if I think I have enough time. If I can type fast. So select start from SCAD. So this is the SCAD table, and it tells you if you do this, I'm just going to say limit 100. So this tells you every SCAD event that happened in the trace. Now, not very useful to find things. There's a ton of them. If I said, count from SCAD, select count from SCAD. So that's there's 1.6 million SCAD events in this trace. Now, SCAD just tells you everything that was running on the CPU. So what you generally want, if you want to understand things like scheduling latency, it's a very similar table called thread state. And thread state has even more because it tells you all the thread state, all the transitions of your process state. So D, R, all of the usual stuff you're familiar in the kernel. I'm going to pick up the speed for time. And I'm just going to jump straight in to give you the query, which is helpful. So you can look at thread states, but this doesn't really help you find the long task you're looking for. So what do we know? We know the name of the task. The thread was called cyclic test, so we can do that. We can see that this is the task running. There's a lot of SCAD happening, but good luck finding the needle in the haystack. So now we can join with a table called thread using a unique TID column in these tables. And what this gives us, if I just show an example of this, so it tells me a bunch of timestamps, duration, CPUs, the thread name, thread IDs, more information than I need. I probably wanted to filter down to where name of the thread equals cyclic test. And I'm trimming down, but there's still a lot of things. Maybe I can say count just to see progressively where things are going. So only from the cyclic test in thread states there is 169,000. So we're getting there. Okay. So and duration of task and state is in R. So in this case, I want to see thread states where I'm waiting for CPU, and now I'm down to 56,000. But I also want to then see the ones where the duration is greater than 1 millisecond. And now I'm down to 28, so we're almost there. But the final bit, and I'm kind of cheating here because I know, is the main thread, the cyclic test has a worker thread that does a bunch of setup, and that thread is not an RT thread. So I want to exclude that thread from these because there's 28. Wake-up latency is greater than 1 millisecond seems a bit strange. And if I can easily do that by saying, well, and it's not a main thread equals 0. I know I get just one task now. So, where's the task? At this point, sorry, I go back here. I can then see all the details of this task. So now I can see the task. I can see, it was woken up by an hierarchy, or I believe this is the RT timer. There's a bunch of detail here, but this is not super useful yet. So I can go back to the timeline, and this is one useful feature which, if you were sleeping all for the rest of the talk, this is the one feature to wake up for. And it's called show debug track. So you have a list of things with timestamp, duration, that's sort of the key columns in Perfetto in most tables. You can just simply say show debug track. And what it does is it takes this information, this timeline, this event, and places it in a new track in a trace. So now you've created a track yourself. And you can then easily find where that track is. And you can see here that it says cyclic test, and you can click on this, and boom, this is a 1 millisecond task, wake-up latency. So if we zoom into this, yes, this is, we click on running, you can see it's a priority 0, so RT 0 task, running on CPU 5, but had a 1.6 millisecond latency. Why? We can pin this and quickly head over to CPUs, because we collected hierarchies. So we can see, well, first of all, what was running on CPU 5? Let's also pin that. So there was an IPEF task running on CPU 5. Unsurprisingly, we were using that to create load. And we can see that it was handling a network receive request. So this was an hierarchy it was receiving, and was running the bottom half of the hierarchy, which runs as highest priority and would even preempt an RT0 task, even though the actual task that was running was a SCAD normal task that shouldn't preempt an RT task. This really is the key point of the demo, that you can use sort of SQL in addition with the UI to really navigate traces. I'm almost out of time, but I'm going to ask Kevin how much to rush. I have 5 minutes. Okay. So I'll quickly go through. This is what we covered. And lastly, instrumenting user space. So this is a very contrived example, just to show more navigation in the Perfetto UI. Simple workload, simple C program. All it does runs an arbitrary, a contrived benchmark to measure the effectiveness of read-ahead, IO read-ahead. So in one case, here is the sort of core of the benchmark. So there's a run read test that takes a Boolean use read-ahead or not. If it's using read-ahead, if it's not using read-ahead, it advises the file to open to f-advise random so that the kernel doesn't use read-ahead for it. Otherwise, it just does it. This is the read, so, custom read block that just does a linear read, so the kernel will read ahead. If you run the benchmark, before running the benchmark, it's helpful sometimes to see user space workloads alongside the kernel events, and you can inject user space events into the trace marker directly. You can write the trace marker, and because Perfetto understands Android systrace, Android systrace has a convention of some trace marker. So this cryptic BE basically means begin and end, and there's a format for it where B, the TID of the task, and if you read about A trace on Android, the format will be clear, but this is not the point of it anyways. The point is that you can inject details into the trace marker. There's a better way to do it with the Perfetto SDK, but it's a bit more involved, and as an embedded developer, you're probably too busy to do that anyways. You can inject things in the trace. All I'm doing is just I want to understand where am I reading with read ahead and not read ahead, so I can see this information in the trace when I open it. Here's a simple benchmark. You can see I'm basically alternating. So once I write with read ahead, drop caches, write without read ahead, drop caches, and you can see the throughput is alternating between 37 megabytes per second and 16 megabytes per second roughly. You can see an average, which is, if all you looked at was the average, it would be a pretty misleading value because you have a bimodal distribution here. And well, let's look at the trace in the last minutes we have. So this is the trace. This is the trace markers we added. So you can see with read ahead, takes about 104 milliseconds to read. Without read ahead, more than doubles the time. And it goes on. I ran, I think, 10 of this. And what can you do from this? So one of the interesting things you can do is you can click on what these rectangles are called slices. It's a pretty hidden feature as well, which is a bit annoying. But you can say click slices, show slices with the same name, and it basically searches the entire trace and shows you slices that have the same name as this. And you can quickly see, this is the duration column. You can sort by, lowest, highest, lowest. And you can do the same thing for without read ahead. And you can also sort highest first. And you can see sort of very clearly the difference in the tasks. You can reason about what's happening in the without read ahead. So you can see lots of IO stalls, a lot more IO stalls. You can zoom into the CPU to see what's happening. You can zoom into the hierarchies to see what's happening over that period. That's pretty much it. I can go back to present mode and breeze through the rest of the slides. So yeah, that's actually it. Okay, thank you.
Can you run the web UI locally, fully locally? So I wouldn't have to use any sort of internet connection?
Yes, so the question is whether you can run the web UI fully locally, and the answer is yes. You can build it locally. It's a TypeScript project, so there's very straightforward command, literally UI/build.
Thank you.
I didn't see an example of this. Can you grab data from a target? Is the SQL database on the same machine as the target, or can you do like a host target type of setup for grabbing trace data?
Sorry, could you please rephrase?
Well, can you have, is there any way to gather data from a machine where Perfetto's not running, or?
Yeah, good question. So, yeah, can you grab a trace from a machine where Perfetto is not running? Yes, you can, but you typically cannot capture in the Perfetto native data format. So if you have some data, for instance, if you have perf on that machine, you can capture perf events. You can also capture from the trace marker directly, so you get the raw ftrace output, and you can open that directly in Perfetto. So you don't need to have Perfetto in your machine. You lose out on some, you have to do the configurations yourself on the trace FS, but you can, and if you, whatever ftrace output, you can open it in Perfetto.
Okay, thanks.
But Tracebox binary is available for lots of, you can run Tracebox, if you have Tracebox on your target, you can run that locally, right? And then move the trace over to the machine with the web browser.
Yes, that is correct. That is correct. So once you run, if you do run trace on a machine, you can, the trace is self-contained, and you can open it anywhere and share it with people. There's actually a nifty share option in the trace.
How do you discover what ftrace events are helpful? And like, it looks clever from ftrace events, but from the get-go, I don't know which one I should enable.
Yeah, it's a good question. So how do you discover ftrace events? It's a lot of trial and error, I think. I mostly copy-paste configs. If you work in a particular subsystem, it's a bit obvious. Maybe, it's usually useful to start with capture everything, see where there's data loss, and then see the list of everything and trim it down. So there's no good answer to that, unfortunately, but there's lots of snippets online. There's a lot of documentation. So in Perfetto dev/docs, there's a lot of information on that.
Thank you. For those of us who don't want Google Analytics, can we self-host the web UI and run that in Firefox?
Yes, yes. So that was literally the same question. You can self-host the web UI and run it yourself. You also don't need to use the web UI, actually. So the way this is structured is there is the web UI, which talks to a SQL database, which is populated by a C++ library called Trace Processor. And you can run Trace Processor as a binary on your machine. You don't even need a web UI. And then you can issue your SQL commands to it directly. So I actually do that quite a bit. If I don't, on a terminal, I don't want to open a UI.
Okay, thanks. And a separate small question. Do you have plans to package the binaries and the libraries in Debian at some point?
In Debian?
Yeah.
I don't work on the Perfetto team, so I cannot answer for them. But there are release binaries on the GitHub page. So you don't have to build from source if you don't want to, and you can just download. And there is available release binaries for most architectures, except RISC-V, as far as I know. But ARM64, there's definitely, on my Raspberry Pi, I was able to just pick a release binary.
Okay.
Do you have a slide for GPU capturing? Because I've used that, and it's the coolest thing of Perfetto, actually.
Yeah, GPUs, I think, famously tricky to. Yeah. I don't have a good answer for GPU tracing. I heard yesterday from someone that there is some files that you can get information from about GPUs, but
yeah, it actually works really well. And yeah, that's probably one of the coolest.
Yeah. So also, if there's a file on your machine, Perfetto is not just about ftrace events. It polls files regularly. So there's a bunch of information that we poll regularly from files. For instance, UMA_just is a pretty important information in Android, and we poll that, and you can configure that polling interval. Yeah.
Got a question from an online viewer. He's asking, can you easily look at two different times in the same trace and compare them?
Yes, you can. So two different times in the same trace.
Yep, that was the question.
Well, look at is a bit, I would need some definition of that, but you can technically open two different tabs, but what I thought the question was about is, can you look at two different traces with the same timeline? And that you can, but.
That's probably what he meant, I assume.
Are there plans to add support for the common trace format?
So, sorry, I didn't get the last word.
The CTF, common trace format, that like Babel trace and LTTNG. Those
BTF.
I thought it was CTF.
Did you say BTF?
CTF, common.
CTF. Sorry,
Yeah.
I'm not familiar with that.
Okay.
Yeah. But for what it's worth, a lot of people have contributed a lot of formats. So I'm not familiar with it, doesn't mean it doesn't exist in Perfetto. I'm just saying, I don't know. Yeah.
Thanks. Thanks for this presentation. I have a little question, okay? Perfetto is for CPU usage, okay? Do you plan to extend Perfetto to memory usage?
There's a lot of information today about memory in Perfetto. Unfortunately, I didn't have the time to show them, but you can add VMstat information, you can get there's RSS stat information, there is a ton of memory you can get.
Okay, thanks.
Thanks for showing how polished it is. Do you find yourself reaching to Kernel Shark? Because Kernel Shark also does some stuff like that? Or do you think Perfetto is a superset from of what?
Yeah, I was anticipating a question about Kernel Shark, and I didn't do my homework. I have never used Kernel Shark. I know of it, but I guess I don't know. If you have used Kernel Shark, try Perfetto and see what works for you. But I'm not going to also sit on any tool, so.
Okay, so it's a Qt application which has some of the UI elements that you have. Okay. There is also func graph with redval. Do you already visualize that in Perfetto? It allows you to show the return values, which is very useful.
So there's a func graph with what?
Func graph with redval. It allows you to show the return values of kernel functions.
You can see that already in, so you can enable this kprobe support at least. Is this return values based on kprobes or?
It's at, yeah.
Oh, it's a feature of the function graph tracer. I don't think that's supported, but it should be, if you file a bug, I think it shouldn't be too difficult to do that.
Okay, thank you.
Can I run Perfetto in any embedded system? Because in the beginning you mentioned this is from Android, but like it is already working in an embedded system.
Yes, yes. So if you you can build from source on most machines, like at least x86 and ARM is supported, and there are also release binaries that you can run. The Android is branded, but you can.
Second question: is there a Yocto recipe for Perfetto?
Is there a separate CPU?
No, a recipe, Yocto recipe, like to build. It is already integrated in Yocto or not?
Okay, thank you. I didn't get the question.
And last question, can I capture the log and then open it in another machine? Like?
Yes, you can. It's the traces are completely self-contained and version, so it should be always openable any version of UI. You might see slightly different information across UI versions, but it always works any.
Okay, thanks.
So I can answer or address the Kernel Shark topic because I've been using Kernel Shark and Trace Command for years for power management debugging, and I recently discovered Perfetto, which is one of the reasons I asked Zim to come and speak to us. So it's a selfish talk, but I can say for comparing Kernel Shark to Perfetto, one of the things Kernel Shark obviously doesn't have is the whole SQL side. So an example would be power management issues. If I want to debug a single suspend resume problem, Kernel Shark, I've been doing that for years. But if I want to do 1,000 of them and then start looking at averages and things that are happening only once in a while, then you get the power of the SQL side of things becomes really interesting. So it really, when you get huge traces or long-lived things or repeated events, you really want to add some query stuff. This is where it really shines.
Yeah, just to add a point about huge traces as well. So there is some browser limit on the size of traces you can open, and we do hit this limit at Google, like I think 1 gigabyte at some point. I think maybe it's 4 gigabytes now. But if you run into that limit, you can run Perfetto as a, like after you capture the trace, you can run it as a server effectively, and launch the UI. The UI will discover the port, and you basically, the UI is not, you don't open the trace in the UI, but the UI is speaking to the local instance of Perfetto, and at that point, your limit is your machine memory limit.
Got another online question for you. How does it compare to LTTNG? I'm not sure if I'm pronouncing it right. In terms of overhead, typically when trying to trigger on real-time events?
I have not used LTTNG either. Yeah, so.
Okay, thank you very much. It's a great talk. Next, we're going to have our first lightning talk before our lunch.
Yeah, that's right. Yeah, that's more. Everything coming through? Oh, no, that's it. Ah. That's on the wrong desktop. Where's my mouse? There we go. No! Wrong screen. I think it's crashed.
Okay, we're going to do our first lightning talk before our lunch. So welcome Kieran to give us an update on Libcamera. Thanks, Kieran.
Hello, everyone. Thanks for coming to Nice. My name's Kieran Bingham. I've been working on Libcamera since we created it some 6 years ago. Today I want to have a bit of an overview of what we've done, what we're working on, and where we're going, hopefully. And I'm very aware that I'm in between all of you and lunch, so normally my talks are, I've never done a short one before, so I will try and talk fast. So Libcamera was started because of this, really. Cameras got more complicated, and we saw that as kernel developers. So we found that on embedded platforms particularly, we have this extra complexity that we need to manage from the internals of a sensor, which is managed by sensor drivers, but then control loops that we need to manage for that, and a whole set of independent blocks, sorry, not independent, but interoperating blocks in an ISP. I've often wondered why we've called the project Libcamera when a lot of what we do is ISP, so maybe at some point we could have been called LibISP, but we do support the whole camera as an abstraction. So every platform has had to manage these in the past, and all the complexities of managing an ISP. So then, of course, you end up with lots of different people implementing the same things. And I've always thought Libcamera is just the next one, the one to rule them all. So everyone else becomes irrelevant. We created Libcamera with as much modular design as we could anticipate. We have lots of building blocks that let you construct pipelines and abstract kernel components, and up at the top, manage the independent components that build up a pipeline for a specific platform. We also have these nice abstractions for all the algorithms, which lets vendors choose how to manage their camera, and we are implementing our own algorithms, which can run on many cameras. I'll skip through there. So historically, you will have found that if you were trying to interact with video devices or camera devices in Linux, you will either have your application directly talking to the kernel through vFile2 devices. Maybe you want to have the extra complexity of managing media controller, or you have some scripts setting that up. Or you'd expect a framework like GStreamer to sit on top of that, and you just simplify things by writing an application with a GStreamer element. So then, of course, Libcamera came along and gets in the way of that a little bit. So now we've got Libcamera acting as a layer for these complex pipelines. But you can either write your application directly on Libcamera with the C++ APIs, or through the GStreamer elements, or we have other frameworks on top. And the other thing that is now all in place, which I'm really happy about, is the Pipewire integration. And perhaps I would say less embedded, but it actually gets used in embedded. This allows more context awareness and user permissions awareness of the requirements and policies, which can then sit in between the applications so that perhaps the user might choose whether the camera is viewable or not. And that's helped a lot when Libcamera is being used on mobile phones and laptops. That brings in the portals where the permissions come in. And of course, now you can see that you can then have the same abstractions that may sit on top of Pipewire, but Libcamera can still be there in the layers managing the camera for you. So a lot of the time, I do think Libcamera is something most users don't even want to know about or experience. It's just a core system component. I mentioned a few of the frameworks. If you find yourself writing a custom camera application or a dedicated system, we have had a couple of projects that have used the Libcamera API natively, and that gives them full control. But we have GStreamer plugins, so you can just build that into your pipeline. We have Chrome OS using Android for the Android HAL, and I'm fairly sure I've seen people using the Android HAL on Raspberry Pi and other devices. We have a Python API, which lets people write cool helpers and scripts. And I think a lot of the Raspberry Pi community find using Python much easier to get started. And I've already mentioned the Pipewire. And all this integration is where I'm really pleased that this is done. It's all working now. And the Pipewire integration means that all of that can end up even into your standard applications and browsers, and the use cases that you expect a camera to work, where Linux struggled for a while of, oh, I've got a device and the camera doesn't work, we can kind of now say that's solved. Because you can join a video call on these devices with an ISP managed through Libcamera. So a few things that we're working on now. I tried to tag, I found myself as the Libcamera release manager. I didn't particularly ask to be that, but no one else was doing it, so I started, which I, thanks to Greg's talk, I discovered is now means I'm the CRA legal person, I think. I'm not sure I was aware of that as a responsibility, but at least I'm happy that from Greg's talk that it's not going to be too burdensome. So I'll come on to the versioning later, but we've just tagged 0.5 with a new ABI release. I really want to reduce the number of ABI changes that we have, make it easier for distributions. And I also try to align to Linux kernel releases. So I think we're at RC6 now at the weekend. So I can imagine within the next week or two, I will be aiming to tag the next version of Libcamera without changing the SO name. And just for fun, I've always tagged Libcamera with a name based on my travels. So anyone can perhaps predict what I might code name the next Libcamera release as. We have had a lot of platform support development going in recently. Pi 5 is in there now in the 0.5 release, which I thought was quite apt. And that's taken a long time. There's been a lot of work on that and a lot of support from Raspberry Pi, so I'm really happy that's now in. It's actually a little bit interesting because there's other ongoing work that means it's not currently directly compatible with what Raspberry Pi are shipping. So there's still a bit more work to go there, so we're still actively developing on that. Standing here with my X13S ARM laptop, the software ISP support from that Red Hat and Linaro are working on is really cool. There are vendors who, for their reasons, are not yet willing to open up the ISPs, which means we cannot configure and manage the whole pipeline. So we now have in Libcamera a CPU software fallback, which means I can run my camera on my ARM laptop for video calls, which is good, but it's CPU bound. So I think I can achieve 15 frames per second with a single CPU being limited at 100% CPU. And there's a lot of work ongoing there to improve image quality. We'll get to that in the future. Mali C55 was a really fun project. We've been working with ARM to support their ISPs directly. We have full kernel drivers supported for that. They're not yet in mainline, which is why I've got it in present. But we do have the pipeline handler support in Libcamera, so we can say it's supported. And it will also be supported by all of our common algorithms for the image processing. And a fun one actually came from Google over the last year is the virtual pipeline handler. So we can, even without hardware, test the whole plumbing, which is cool. And I keep having these crazy ideas that I want to put an OpenGL shader into the virtual pipeline handler so you can just render fun test patterns rather than the dull single bars. The other thing we've been doing internally in Libcamera teams are working on a lot of tuning and developer tools. That's actually the next slide, I think. Oh, no. So we're creating a lot of tools to help us see the pipeline and see images in real time and interact with the camera. A lot of people ask me what cameras are supported by Libcamera. My easy answer is if the camera is supported by the Linux kernel, then we can support it. If it's not supported by the Linux kernel, then we can still I still want to see those drivers upstream in the Linux kernel. And very simply, I've taken a list of the identifiers that are in our database. And that can always be extended. Mali C55 is a really cool platform because we were working on the FPGA implementation, and KQP came out with a Renesas chip that implements that, so we get to work it on real silicon. So getting that running on a real display was really fun, and we get to take off-the-shelf components on other platforms. Okay. We've got a lot of new feature development coming in. We've got de-warp support on the IMX-A10 Plus, which lets us do digital zoom, fixed fisheye lenses, and arbitrary rotation, which is fun to demo. These can be seen up on the booths up in the coffee hall. And now I'm really wary of time, but I've got an awesome demo here that I like. We've got Stefan has been creating an implementation of WDR support where you can adjust the image algorithms and processing of the ISP so that you're not overexposing or underexposing the whole image. You can balance it so that you can still get the bright scenes in the background and the dark scenes in the foreground. That might be, if you've got a sensor that supports HDR, you could use HDR for this, but not all sensors support that, and you can have more control over the processing with the WDR implementation. And this also shows off the Camshark tool where Stefan's built in the ability to view internal graphs of what's going on in real time, which I think is really awesome. And now I can't get out of the video. We have a lot of complex projects with FPGAs and differing inputs that go into the system. So one of the active developments that I'm keen to progress is that we push or abstract how those devices get in, or how you configure the camera to be routed into the ISP. And what I am hopeful for that, although we've done that on the IMX8 Plus, it should be generic, so it should help every platform. So, things that I see on the future roadmap for Libcamera. HDR support, I've just mentioned, we can extend from the WDR support into supporting features that the camera sensors can provide, where you can take multiple exposures to capture both the bright scenes and the dark scenes in a single image, and then merge them. Got a really cool system coming from Raspberry Pi. David is working on or has created a sync algorithm where you can synchronize any cameras, any number of cameras, which is really cool because that's the bullet time demo. If anyone's ever seen it, you can have lots of cameras, and they'll all take the picture at the same time. Having my own personal laptop without an ISP, GPU ISP development is going to be really awesome when we get to accelerate processing through the GPU. There's so much and I don't have time. We've got a lot more platforms coming in as well, which I'm really excited about. The Mali work that we've done will expand to a lot of other variants of the ARM ISP ecosystems, so I'm really looking forward to where we're going with that. We've done a lot of work on IMX8 Plus, and NXP are leading the development on the next generation of chips from them, the IMX95, so I'm anticipating a full Libcamera stack from them. I've also seen a Libcamera stack implementation from Microchip, and I'm fairly sure ST are working, or have an implementation, but I haven't yet seen those being posted upstream, so I'm really looking forward to those being contributed to the upstream project. I haven't seen any RISC-V developments. I know there are chips out there with RISC-V with an ISP, so I'm really looking forward to seeing those in the future. And I've mentioned things like GStream and Pipewire. I have never seen anyone try to use FFmpeg with Libcamera. That'd be a fun project if anyone's an FFmpeg developer and wants to integrate that. There's also, being imaging, OpenCV is a big part of the user base. There's no native Libcamera implementation yet, so I've seen a lot of people developing on that, and I'd love to see that develop. That's another big topic, but we're working on supporting a single ISP to be used in time multiplexing. So we're working within the kernel space and Libcamera to make it so that we can reuse a single ISP instead of having to duplicate an ISP graph through the kernel. That's a huge amount of work that Jacobo's developing. And there's also lots of cameras that have long cables and serialization technologies like GMSL and FPD-Link. I could definitely see those being something we can abstract in Libcamera. So what's the ultimate future for Libcamera? How do we say that it's done? I'm not sure how to ever complete an open source project, but I do still have in mind things that would make a Libcamera 1.0 release happen. A stable API, ABI. We do have active development on that. Barnabas is working on trying to create a C API, which will then be able to give us a more stable API than C++, which is what we're using. And two topics that kind of spring to mind as kind of essential for Libcamera are perfect frame control and reprocessing. Very desirable features to create a camera stack where you can precisely control the camera and then take images you've had and feed them back to make refinements on the image quality. Ultimately, we believe that even with Libcamera open source algorithms, we're going to be able to exceed the functionality and features of the closed source camera stacks. So I'm looking forward to that. So the future of Libcamera, I believe the future of camera support on Linux is Libcamera. One more thing. There's an enormous amount of work for us to do all this camera support, so we are hiring. If you think cameras are interesting or cool, or you want to learn more about the internals of algorithms and how you run an auto-exposure loop or white balance, please get in touch. We're looking for anyone interested in open source and camera processing. And if anyone has questions, everyone's hungry, so look for a red tag. Orange tag, sorry.
or anybody else with the Libcamera shirt on.
I did actually wonder why we have so many Libcamera developers with the blue T-shirt that has been swiped. Yeah. So, but yes. Thank you very much.
Okay, just to check, check, check. I'll use this one. Check, check. Just a quick reminder for lunch. All the lunches today are vegetarian, vegan, so go ahead and help yourself to lunch. And also a reminder, please don't eat, or please don't sit at the picnic tables by the food vendor in the park. We need to leave space for the people that are paying for food to sit down. So wander around, there's lots of benches, and enjoy your lunch. See you soon. Stefan? We're going to do one more test. We're going to do one more test. Hello, hello, welcome back. Welcome back from lunch. We're ready to get started again. As you can see, we are now official. We finally have, we're 3/4 of the way through the event, and we have our, we put our poster on the stand here, so now it's official. We're so well organized here. Okay, welcome back. We're going to kick it off now with John Agnes to talk about real-time applications. We've had a few hints so far about real-time processes and real-time kernels and stuff, and John's going to tell us even more. So welcome, John.
Nope, that's a little bit. Hold on, let me click on this one thing. No. Show. All right. Okay, thanks. So I'm here to talk about writing real-time applications for Linux, because this is not obvious, and we need to spread a lot of awareness. The company I work for, Linatronics, I'm one of the happy hackers at Linatronics. We're currently working on documenting all of this stuff that we've been working on for 20 years. Hopefully this time next year, there will be official kernel documentation where it's all documented. Right now, all you have is YouTube videos and blog posts and social and things like that. So it's, yeah. So we're just trying to spread a lot of awareness. So I'm going to start off with a bold statement. Linux can do hard real-time. Yes, I did say this. And to qualify this, what do I mean by hard real-time? I mean that if you miss a deadline in your application, it's a critical fail, your system has failed, and it could be catastrophic. So this is how we define the preempt RT developers. This is how we define preempt RT. So if you miss one of your deadlines, it's either a kernel bug, or more likely, it's a problem in your application design or implementation, right? So you should never, ever, ever miss your deadlines with preempt RT. And since 6.12, it is mainline, so you can just turn it on, which is an amazing thing. It's about 25 years in the making. And actually, Thomas Gleixner wrote a book, a very mini book about it, that talks about the whole history of the last 25 years. On the table upstairs, there's a whole stack of these. It's all the rest that we have printed. So if you're interested in kind of reading a very technically accurate and interesting look back on 25 years, feel free to grab one. There's not a whole lot left, but yeah, maybe you're interested. Okay, so we had this huge celebration. This was like last September. And for us that have been working on this for 20 years, 25 years, it was a big celebration because we'd worked a long time to do this. But the rest of the world was like, yay, is this good? What happens? What does this mean for us? Do we have now a deterministic Firefox with guaranteed latencies? Like, what does this mean? And no, it does not mean this, because Linux is still a general purpose operating system. And when you turn on preempt RT, you still have a general purpose operating system. So actually, if you turn on preempt RT or install a preempt RT kernel, you probably won't notice anything different on your system, because your applications are doing the same thing that they were doing with a non-preempt RT kernel. And the applications are the things that have to do the magic. Of course, with preempt RT, what you get is a new set of semantics to certain functions that make it possible to do hard real-time. But the applications need to do that, and that's why I'm having this talk. So this is basically the main 6 things you have to pay attention to when you say, okay, I want to do a hard real-time system or application or whatever. What are the things I need to be aware of about Linux? So let's just go through these. So the first thing is we need our application to be in physical memory, and all the libraries we're using and all these things need to be in physical RAM, obviously. If they're not in physical RAM, then it causes a page fault when the CPU goes to these instructions or we start accessing this memory or whatever. We get a page fault, and Linux has to scramble to get memory, and this is fatal for all real-time applications. So we need to make sure that our application is always in physical RAM. So what are the things I have to worry about there? First of all, you have to realize that Linux maps memory on demand, right? So allocating memory is really fast because you haven't allocated anything yet. It's just marked, you've allocated this, but you haven't actually. When you start touching that memory, that causes page faults, and then you start getting 4K, about 4K a piece, you start getting that memory, and it's dynamically being assigned to you. So, you know, if I allocate this 2 gigabyte array, that's really fast. But if I start touching this array, you're going to notice that just touching that memory the first time is extremely expensive, right? So you have to be aware of that, this on demand. And it's not just for heaps. It's also for your stacks. The first time my stack grows above a certain page denominator, then I get another page fault, and another page is assigned to my stack. Even the text and data segments of my application. Linux does not load an entire application into physical RAM. It just loads the pieces you're using. And as the CPU moves to new text segments, that'll cause a fault, and it will load that into memory, right? So these things are all loaded on demand. You need to be aware of that because that's all fatal for real-time applications. You have to also be aware that Linux recycles memory. So we're all aware of swapping to disk. You know, if memory starts to get full, then it'll start swapping unused pages to disk. And even if you say, yeah, but I have an embedded system, I don't use swap files, you are still vulnerable to this because if things get really tight, Linux will start dumping any pages that it can reclaim from the disk, including, for example, the text segments for your application, right? So it's like, okay, I'm getting really full on memory, but if I throw out these text segments, I know that when the CPU needs that function again, I can just repage it from the disk, right? So even on an embedded system with no swap file, you need to be aware that this paging can happen. And then, of course, the glibc likes to reclaim unused heap space. So if I have a huge heap and I'm not using the top parts of it, glibc will actually give it back to the kernel to use, right? So maybe I had all these page faults and got all this memory, and then I wasn't using that memory for a while, and now it went back to the kernel. So if I want to get it again, I'm going to have to page fault it again, right? So these are things I have to be aware of. They're all not good, absolutely forbidden for real-time applications, and there are solutions for that. For example, locking your memory, pre-faulting your memory, and tuning your glibc with mallopt so that, for example, you only have one heap and you're using a true heap. Yeah, so you're not using maps for your heaps. You actually are using, with the break system call, you're actually managing a heap like we all learned in the university. And you can also do things like tuning how your stacks work, avoiding allocating with mmap altogether, and things like this, right? So these are things you can do. I'm not going into the details of these things. You can find them in the internet by Google searching, or I have a talk called Checklist that actually goes into more details. So just so that you know that these are like the key terms to do that, but you need to do that. Every real-time application must do these things to avoid these problems. The next thing is to understand that there are real-time policies and priorities. These are not specific to preempt RT, but with preempt RT, they become really important because they can actually be used much more effectively because preempt RT is much more interruptible. I think everyone knows this. You have the policies sched FIFO and sched round robin. Basically, it means your application stays on the CPU as long as it wants until it says, okay, I'm done with the CPU, right? So it's not like the EVDF and stuff where we have certain time slices, our time slices up and we get kicked off the CPU. This doesn't happen with the real-time policies. You stay on that CPU as long as you want. If you go into a busy loop of nothing, that CPU is basically gone because it's just going to busy loop forever. There are different priorities. So we've got from 1 to 99, we've got the different priorities that are available. So this makes it possible so that we can have tasks that are more important than other ones, of course. And the way that this sched FIFO works here, let me get my mouse pointer. The way this sched FIFO works is that if a higher priority task becomes runnable, it has something to do, then obviously it will take over, right? So it's just, if nobody more important than me has something to do, then I can just go all day with sched FIFO. As soon as another task with more priority wants to come in, it immediately takes over, and it can go as long as it wants. There's also this sched round robin variant. This is just, the only difference between those two is if the priorities are the same, then there are time slices between those tasks. So you can actually choose to have two tasks with the same priority kind of take turns on the CPU. But it's only if they're the same. If they're different, it's exactly the same as sched FIFO. Down here, I show you the CHRT tool. This is a tool where you can change the policies and the priorities of running applications, running threads, individual threads. So these scheduling policies and priorities are per thread, right? So you can have certain threads that are real-time priority and the other ones that are just sched other. So with CHRT, you can control that. Or if you want your application to do it itself, you've got sched set scheduler. And there's also a pthread variant if you want to use that. Synchronizing and notification. This is something that you do all the time because we have some sort of protected resource, and usually you'll have high priority tasks that need to modify or read this resource and low priority tasks that need to modify it, and maybe sched other tasks that need to look at it. So we need some way of synchronizing this data and be able to notify each other when this data is changed. For this, you definitely want to use locking, right? We want to protect it, we want to synchronize it, and the pthread mutex type is the type you want to use to protect this. This is the only data type that supports priority inheritance. What priority inheritance means is if I'm a low priority task and I take that mutex, and now a high priority task comes in and says, I want that mutex, then what will happen is that low priority task will get boosted to the same priority level as the high priority task so that it can finish its work and release that mutex, and then the high priority task can take over. And this is really important to avoid priority inversion. We don't want our high priority tasks waiting on low priority tasks. So we can boost them to our priority, they finish what they're doing, release that mutex, and now we can take over. And the pthread mutex type is the only type that supports this. So you need to use this type for locking. Unfortunately, it's not the default that it has this priority boosting feature, so you actually have to turn this on there's a mutex protocol attribute, you actually have to turn on the priority inheritance. If you want to do some sort of notification, often this is so in real-time applications where you're waiting for an event, and as soon as you wake up, the first thing you want to do is grab a lock and look at what the data is. That's a very common pattern. I'm waiting, someone's modifying data, and then I wake up, and then I want to look at the data. So basically, you've got a conditional variable, an event, a wait object, and we have a mutex, because we need to get to that data, which will also be protected. This is what conditional variables are. They basically marry a mutex to a wait object, so that you can have a nice, clean handover when someone's modifying the data and they wake me up, and then I will wake up, grab that mutex, and look at that data. That's exactly the pattern that conditional variables are for. It's safe to use the glibc implementation of convars. However, you might be also interested in libartpi, which is also in Debian, which has a more efficient ownership transfer. So basically, I've modified the data and I want to wake someone else and say, hey, look in there. Basically, a more efficient transfer of the mutex to say, okay, now you have that mutex and you can look at the data. So it's a little bit more efficient. With conditional variables in glibc, it's okay, but if you've got a lot of contention, it's not super efficient, but it'll still be correct. Cyclic tasks are something we have all the time. You know, maybe once every millisecond we have to read some sensors or check some registers or do some sort of work, whatever we need to do. This is actually quite often in real time. You need to be aware that there are APIs, system calls, that are not RT safe. For example, TimerFD is a big one. Everyone thinks TimerFD is great. It is great, but for preempt RT it is not great. The problem is that depending on when the timer interrupt fires and the current load of interrupts on the system, that interrupt handling might actually get deferred into the ksoft IRQ daemon, which is running a sched other, which means your high priority task, which is waiting for wake-ups every millisecond, that might get the responsibility of that wake-up might move into a sched other task, the ksoft IRQ daemon, which is fatal. Because sched other it'll be scheduled when all the real-time stuff is done. So TimerFD is unfortunately not good. I hope someday we can fix TimerFD so that it is good, but right now it is not. Also, POSIX timers have the exact same problem. POSIX timers are even worse because you're kind of in a user space interrupt context when you come in user space, so you're not allowed to take mutexes, you're not allowed to do a lot of things in an interrupt handler. I think yesterday there was some talk about signals and how horrible they are. They are horrible. So the POSIX timer interface has this deferred interrupt problem, and it's using signals. It's just ugly, ugly, ugly. So the best thing to do and the correct thing to do is really to have a dedicated thread. It's very simple. It just runs a clock nanosleep, so it sleeps amount of time. It'll wake up, does its work, goes back to sleep. So it's a very simple loop of just doing my work, and when I'm done, I go back to sleep. The beauty of this is you have a dedicated thread, so you can give it a dedicated policy, a dedicated priority. It's a normal thread context, so you could take mutexes and do everything you need to do there. You'll have priority boosting and all of the stuff, so you have all the control that you need for this cyclic task. Important here, make sure you're using the monotonic clock because it's immune to time setting, for example, every year or twice a year when we change our clocks, or for example, with the leap second and things like this. Clock monotonic is immune to these sudden changes. And also absolute time is important because you shouldn't be calculating, okay, I did my work, now how long do I need to sleep? No, use absolute time. So if I know I'm waking up every millisecond, I can calculate my wake-ups for the next million years. It's going to be every millisecond. I can calculate that. And if I'm using clock monotonic and absolute time, I know exactly when I'm waking up for the next million years. So I don't have to calculate anything. I just go back to sleep, and I just had to increment that by 1 millisecond. Just keep incrementing the previous sleep by 1 millisecond, right? And so I have a nice, steady, no variance, no drift. Even 1,000 years in the future, I'm still hitting this 1 millisecond as the humans have defined it. Task and interrupt CPU affinities. This is also important because often you want to dedicate certain CPUs for certain tasks. So it's possible to, for example, to isolate certain CPUs and say, I'm only going to run my real-time tasks on this CPU. This is, I think this was talked about yesterday in the OSCIL talk, so that you can have less interference from other tasks. There's still issues like caching and things like this that you have to be aware of. These are actually hardware issues. But getting the processes, the different tasks off my CPU so that I can reserve it for real-time can be very helpful just to reduce the noise on that CPU. Generally use CPU set for that, so there's a man page, it's based on C groups, how to use that. There's also the isol CPU's boot argument, which is currently deprecated, but a lot of people are still using it. It's a little bit easier to use, but obviously you don't have the fine control that you have in C groups. Again, here you see the API of, if I want to manually set the affinities, I can use the task set tool, so I can manually set affinities per thread, right? So I can say this thread is pinned to this CPU, the other threads are not on that CPU, or whatever. However I want to set that, I can do this per thread, I can set these affinities. I can also do it as a program with the sched set affinity. You can also use C groups, which is basically what's set up here. So you can use C groups to basically confine applications or a set of applications to certain CPUs. And you can also set the IRQ routing for the physical IRQs. So for example, I can say that my network IRQs should be firing on CPU 3 because that's where I have my real-time application, all these things. I want the IRQs to be firing on the CPU that's going to be dealing with those interrupts. So I don't have to do any IPIs, you know, the interrupt fires here, and now I have to do a wake up on another CPU. That costs time, and we don't have to do that, right? So you can actually control the routing of your IRQs so that the hardware is really from the moment of interrupt doing what you want it to do. The last topic is real-time networking, and this is something that's actually quite tricky. The first thing you need to have is hardware that will support real-time networking. So you don't have to have hardware that supports real-time networking because you can emulate all this. But if we're talking about real-time, then we're talking about being serious, and we're going to buy the hardware to do serious real-time networking. So for example, we need to have the ability to do precision timestamps in the hardware. We need the ability to specify priority traffic classes and time-aware traffic shaping. We need to be able to send packets at exactly nanosecond specified times is when we want to send them on the network. And this multi-queue allows us to actually identify when traffic is coming in on these different traffic classes. We can say, okay, this high priority, this is going to go to CPU 4, and it's going to be handled CPU. The stuff that's not important is going to go to CPU 2, right? Like we can actually, the hardware can do this, can actually route the incoming traffic. So these things are very important to allow you to do real-time networking. Now currently, you also have to have an isolated CPU for your real-time networking. So I can't just do normal networking like I'm used to. I actually have to decide, okay, I have a CPU for it. I'm going to put the hardware interrupt on that. I'm going to put the interrupt handling thread on there. I'm going to put the NAPI instance K thread on there. And my application is, my real-time application is going to be in there. So basically, I have a dedicated CPU that's just doing real-time networking. That's how you have to do it right now. But actually, there are patches currently on the Linux kernel mailing list so that we don't have to have that requirement, right? So it would be nice if they could, all these things could just be on whatever CPU is nice, because then allowing things to just run on all the CPUs, you're just giving the scheduler the freedom to schedule good. So forcing the scheduler to always use certain CPUs is not always the most efficient approach. Excuse me. So those patches are currently on LKML, and hopefully with like 6.16, 6.17, this requirement will no longer be there. There's also a tool called RTC Test Bench. This is a tool that is basically, it's a collaboration of all the hardware vendors of this real-time networking hardware, because they wanted to have some tool to verify that this is actually working correct. This multi-queues are working correct, the non-real-time traffic and the real-time traffic are being sorted correctly, that we want to measure exact timing and latencies of everything. They wanted to have a tool for this, of course. And Linotronics developed this tool. We're the maintainers of this tool, but it's a collaboration effort of all the hardware companies. And so you see it's a real-time and non-real-time traffic validation tool for converged Ethernet networks with and without utilization of TSN mechanisms, right? So this is the tool. If you want to do real-time networking, that's the tool you need to go to test. Before you start writing applications, test your hardware. Can we do real-time networking on this hardware? Because if you can't get it to work on that, you will not get it to work with your application. So this is a quite an important tool, because real-time networking is complicated. And the nice thing is it has a lot of pre-existing configurations, so you can just kind of take things out of the box and configure it fairly easily. Okay, so we've heard about all these things that are there that we have to be aware of. What are some design considerations now when we're doing our application? The design. The first thing is you need to understand this idea of event flows. A hardware interrupt happens. This is going to go to an interrupt handling thread on PreemptRT. That's going to wake some sort of application. This application might wake another application. So there's going to be like a chain of events of the flow. And this flow should go from high priority to low priority. You shouldn't be having low priority tasks notifying high priority tasks, because this is kind of a mistake in your logic. Really, the events that come in need to be high priority, and then you can sort them out and say, okay, yeah, that's not so important. But if they start out as low priority, they may never get scheduled to come to high priority. So you really have to make sure that the direction of priorities in the event chain is always going the same or going down. This is really important. And obviously the hardware interrupt, this is what you'd consider the highest priority. Yeah, this is basically all events originate at some point from a hardware interrupt, right? Software just doesn't magically do stuff. There's always some sort of hardware event that happens that triggers that chain. Real-time work. Only use the real-time priorities for actual real-time work. So I've written in my documentation, my requirements documentation, we have latency requirements. We have to fulfill these deadlines. That's the work I should be doing in real-time priority. Nothing else. No pthread joins, no let's read some configuration files. Don't do this stuff in PreemptRT. I'm sorry, not with PreemptRT, with the RT priorities and policies, because what you're doing is, it's not that it's in and itself is bad, but you're taking the CPU from maybe other important tasks on the system, right? If I'm using a real-time priority to do a pthread join, this CPU cycles I'm getting maybe could have been going to an important sched other tasks. Sched other tasks do have important jobs too. So really keep yourself at sched other. There's enough tools available with NICE, with C groups, and all these things that you can actually tune your system how you want without using real-time priorities. I've seen people use real-time priorities because they're like, yeah, I want my web browser to get a little bit more CPU cycles. No. If there is no deadline specification, don't use real-time policies and priorities. It's that simple, right? As soon as you see someone using a real-time policy, then you can immediately ask, can you show me the specification for the deadline, right? I want to see it. What is it, 100 milliseconds, 100 microseconds? Where is it? We have to write this down because we're using real-time stuff here. Okay, and then the last thing really to consider, when a real-time application goes to sleep, this is kind of a scary thing, right? I have a real-time application or a task, and I'm going to sleep, right? It's like I have a huge test in the next morning, and now I'm going to bed. That alarm clock better wake me up, right? Like I'm going to sleep now. And this is the same thing with the real-time tasks. You really have to ask yourself, who is the waker? Who is going to wake this task in all scenarios? Because you need to make sure that that waker is at least as important as I am, right? When I go to bed and I have that big test the next day, that alarm clock is more important than me when I go to sleep because that thing needs to wake me up, right? So really in all scenarios, you need to consider who is going to wake this task up. Yeah, when I do a clock nanosleep, it's the hardware interrupt that's actually going to do the waking, right? I can rely on that. Okay, so we have all this stuff that we've seen, so now we can go out and we can write perfect real-time applications, right? Wrong. You will not do it correctly, right? And the reason why you still will make mistakes is because Linux provides many, many interfaces, and you don't know the details of how it's implemented. You don't know if it's RT safe. For example, timer FD. A lot of people are shocked to hear that they're not supposed to be using timer FD. It's not their fault, right? But it's just the fact. They can't use that. Right? So people are going to use interfaces that are wrong. Also, not all subsystems and drivers are doing things the same. So if I'm using like the GPIO subsystem, it might be okay to read some GPIOs, but if I'm using the I2C subsystem, it might not be okay to communicate with an I2C controller. It depends on how the subsystems and the drivers have implemented that, right? So you can't really know. Also, the libraries themselves might be doing things wrong. Even the libc might be doing things that are not RT safe, right? So you have all these problems that you don't even know. And also the first 10 slides I showed, that was a lot of stuff, right? So you're supposed to keep all of this in mind, and now you're going to do a big application, you're going to mess it up. And so this is why we decided we wanted to have a tool to show us what we're doing wrong. And just recently, so the 12th of May, from my colleague Nam, we posted the runtime verification monitor for real-time applications, right? So it's currently in version 8. We think this is the version that will get accepted. When you've applied these patches, you'll see in the kernel configuration you have an RT app monitor. This monitors your entire system to see if any real-time applications are causing page faults or they're sleeping incorrectly, right? They're sleeping in a way they shouldn't be sleeping. And basically with these two scenarios, if you can catch that they're going to sleep incorrectly or they're being woken up incorrectly, that's the opposite of sleep, right? Or they're causing page faults, you've covered a whole bunch of problems. So what this is just a nice tool that you just turn on. So the way it works, if you have a system patch like my system here, basically you just have to turn on the RT app monitor. A reactor is, there's different ways to react to when a problem is found. So one of the options is to panic the system. So you could actually say panic. So that if I have a page fault in a real-time task, the system panics, for example. In this case, I'm just using print K, right? So it's just going to let me know. And then you can use perf to just record, and you have these two events, the RV error sleep and the RV error page fault, that you're just recording. And you know, if I'm saying -G, I can also grab the user space stacks. So after I've done some recording, I've just let this run on my system. I'm watching YouTube videos, I'm doing Zoom, whatever I'm doing. And then I can break perf record and take a look what it found. Right? And I see full back traces of things that were incorrect. So but it's only for real-time applications, right? These are real-time applications. So we're saying that, for example, Pipewire, which is a very important real-time application, is supposed to be replacing Jack, which is a professional audio solution. And we see that some warnings appear there. And in this case, we can see that actually it's doing an epoll wait. And unfortunately, epoll is currently also a function that's not RT safe. So I can look in there, and now I can look in the Pipewire code. And we actually did this. So we looked into the Pipewire code, and my colleague Nam actually created a merge request telling him that it needs to be changed. We need to get away from epoll. This is the problem, and here are the patch to do it, right? So we could fix it. Now, there's a lot of epoll in Pipewire. So there's a lot of things. So it's going to be things that we're going to have to do one at a time. but this is something we did. And if you look, what is the actual problem here? When you look at the code, basically what's changing is, this is the interesting part we're removing. What Pipewire was doing is it was telling the real-time task to connect nodes, right? So if you have your Pipewire and you're connecting your speaker to your microphone or something like this, you're creating a node connection. And there's no reason for that to be done in real-time context. But Pipewire does it in real-time context. It basically does this PW loop invoke, which basically just tells the real-time loop, hey, can you create this connection for me? Which is, it's just wrong. It's just wrong because it has nothing to do with real-time. You should not be doing the real-time task. It was a pure convenience thing that we implemented that way. So basically what this patch did, and the patch is bigger than this, but basically it added a mutex lock with priority inheritance, and we're protecting that list with that lock. And when the nodes need to be connected, I just do it in the sched other context, right? And I just take the mutex lock, I connect those nodes, and release the lock. I don't have to have a real-time task do it for me. And when the real-time task wants to look at these node connections, it also needs to take the lock. And if my sched other is holding that lock, it'll get boosted, make the connection, get deboosted, and now the real-time task can use that list, right? So it's a relatively conceptually simple change, but it's just, again, showing real-time tasks should only be doing real-time stuff. Now, as with all maintainers, the patch wasn't good enough how it was, but he took it seriously, so he actually, in the Pipewire, there is actually a loop lock branch that's been created, and so you see that Wim actually, he did his own version of that. That's fine. He's the maintainer, so he sees, okay, we should do it a little bit differently. So you can actually see these 6 patches that he put on there that basically implement that. So he's actually seriously looking at this. He didn't even know that priority inheritance existed and things like this, right? So, we had to give him a little lesson about how it works. And he's like, okay, yeah, now I understand. Now I understand what I have to change and why. Unfortunately, that was just one thing we found wrong with Pipewire. Pipewire has all kinds of things. We saw page faults happening in real-time context. It uses timer FD for a lot of stuff. So Pipewire, which is supposed to be this amazing real-time application, and it does a good job, but it's not ready for Preempt RT. Like, it's not doing things the way Preempt RT needs it to do, right? So these are just little things, but the nice thing is we have this tool now that we can just run. You just turn it on and just do whatever you do on your system, and it's just going to start noticing the real-time applications that are doing something they shouldn't. Now, that doesn't mean that everything it finds is an error, right? Sometimes it's like a false positive, like ePoll is not always bad. There are situations where it's okay to use ePoll. There are situations where it might be okay for a low-priority task to notify a high-priority task. Right? There might be some, but generally speaking, you're doing something wrong. So you have to go through on a case-by-case basis and say, like, is that right or is that not right? But it's a good start because this is the first time that we have something that just kind of spits out. Because until now, customers had to wait till their device blows up, and then they have to reproduce it, and then they have to like trace it and use Perfetto and all this stuff to try to figure out what went wrong. And now we have something that maybe it can just immediately tell you, hey, you have priority inversion because this low priority task is waking you, right? So these are things that can really help there. So that's the end. So it's not perfect, but we're working on it. We're working on the documentation, and I hope by having documentation, people can read about what's correct and what's not correct. By having this RT monitor, they can just turn something on and it'll just start complaining about the real-time application. We hope that this will try to educate people and get them to better understand how to use Preempt RT correctly so that they can really have hard real-time with Linux. Any questions?
How do you work around the power usage cost of using a small sleep to implement your timers?
I'm not sure what you mean using clock nanosleep or?
Yeah, so something that's been chased in desktop world for years now. It's the recurrent wake up of CPU. So basically every 20 milliseconds you wake up the CPU, every 5 milliseconds. Yeah. Do you have a technique where you can sleep longer but still have a chance to change your deadline later because you have some other information that maybe your deadline is shorter so you don't want a big sleep? But you don't want a small sleep because you don't want to keep waking up.
Yeah, I mean, this is a really complicated thing, and these are one of the things where power management is a direct enemy to real time, right? So I'm not aware of any interfaces, if I understood you correctly, so that I can push out my delays further if I don't want to wake up. I mean, there's modes like no hertz full, where it just won't wake up the system at all, but if I do like a clock nanosleep, I'm actually setting a timer. That'll actually wake me up. So, but if you just want to avoid the tick, there is the no hertz full that will completely get rid of the tick, and you're only going to wake up when actual interrupts fire, right? So you can turn that off, that tick. But you have to be aware that the tick is sometimes important because it's in charge of updating the clock diffs. One of the problems is that when you do wake up, like for example, when a really important interrupt happens, the kernel will first update the clocks because it hasn't done that for maybe 2 months, right? Because it's been sleeping.
Right.
So the problem is with no hertz full, we usually recommend against that for real time because you're delaying work to the moment when you have to do something else, right? And because you'll wake up for something important, and now I have to do all this work I didn't do because I was sleeping. Right?
Yeah, so basically that's where my question was going. Basically, do you have any strategies where you would do something less real-time to wake up earlier, and then you go more real-time to get more precision or something? Is it something you've ever done? Or?
I see what you're saying.
Because power management is going to be a real challenge for Pipewire because it's not meant just for like a wired device. It's also for your laptop, for your phone. And
well, sure, but I mean the principles are the same. When I stop having my real-time task do non-real-time stuff, that's not a bad design decision. Actually, when he started looking at this, he's like, oh, actually, this is a better design when we start decoupling real-time for the real-time stuff. So there's nothing wrong with making Firefox real-time capable. It's not going to make Firefox bad, if that's even possible to make the Firefox real-time capable, or even what that even means. But yeah, so generally, it's not a bad design decision. When I write just regular code, I'm used to writing real-time applications. So even if I'm just writing some stupid hello world, I'm writing it to be RT safe because I'm just used to that. And when you get used to it, it's actually quite easy. Right? There's just things I don't use signals, I don't use timer FD, I can use other things. So, yeah.
Thank you.
Yeah.
Hey. So you mentioned that you implemented support for Pipewire and PreemptRT. Do you have any figures for the round trip latency?
I'm sorry, the question, what was the question part?
Metrics for round trip latency tests.
For network?
Pipewire.
Going through Pipewire.
You mentioned
so you're just talking about locally, right? You're not talking about network or anything like that?
No, we're talking about Pipewire and audio playing.
Yeah.
And you mentioned in real-time support and you had to implement some
yeah, so we didn't do any testing to see latency because maybe at some point we will, I don't know. We didn't want to become maintainers of Pipewire. But we're just noticing like design patterns that are wrong.
Okay,
so we're just helping them fix that. That should improve latency in bad scenarios, right? Like if there's never mutex conditions, if I'm not getting cache misses, all these things, then I can have a bad design work great. The problem is when we get memory pressure and we get only cache misses and all these things happen, memory bus contention, then all of a sudden things just explode, right? And that's where the design makes the difference.
Right,
so we're catching things that are badly designed, but it hasn't necessarily, a bad thing has not necessarily happened.
Yeah, so it makes sense because years ago we implemented Xenomite support as a plugin in Pipewire, and we were measuring 8 milliseconds round trips. So obviously we didn't notice these things that you mentioned, so it's a matter of testing again and see if we see an improvement.
And you should definitely do that to make sure nothing gets worse.
Absolutely.
Right, like making these fundamental changes in the design and we see Pipewire gets way worse. That's not good either. Right? So.
Yeah, leaving the deeply technical parts for a little bit, we all know that we also need to talk to people who are not understanding all of this stuff, like your Firefox users. What's your punchline to tell people enabling PreemptRT on a box standard system will actually not make it faster, but slower? Because I have to explain that every time.
Yes, this is important to understand that real time is not as fast as possible, it's as fast as specified, right? So Preempt RT does a lot more accounting, has a lot more interruptibility, and you don't just get this for free. We had to write a lot of code to do this. So the CPU does a lot more in Preempt RT. So just turning it on for fun, you're going to give your CPU more work, and you're not necessarily going to see anything better because the applications are not written for Preempt RT, right? Like I mentioned. So it'll work the same as before, but the CPU has a lot more work for nothing, right? So really, Preempt RT is still should be reserved for real-time loads. We actually do something real-time. We're going to do this extra CPU work in accounting because we get something for it. Our applications can take advantage of it, right? So it's more work for the CPU.
Could you go back to the Pipewire code example, that with the lock and the loop?
Oh, here, yeah.
Yeah, so when you move that out and have a lock, it doesn't improve the worst case, right? It's because in the worst case, you are just taking the lock, and then the real-time task has been woken up, and then it needs to wait, and you have this random time that you need to wait. So this doesn't improve the worst case, right?
Exactly, and this is what Wim at first talked about. He's like, yeah, but in the worst case, we still have to wait for the list to be updated before I can do the real-time stuff. We're like, yeah, but you have to do that now because you're posting something on the real-time loop. It has to update the list before it even considers the next event. So it's not better or worse than the worst case. It's the same. But the difference is that if we're not in this worst case scenario, then we don't have to be in real-time context to update these lists. So the normal case has been improved, and the worst case maybe is the same, but the normal case has been dramatically improved, right? And that's really the goal. Don't do RT stuff if you're not actually doing RT CPU instructions, right?
Okay, thank you.
Thanks for good talk. I would like to add one small comment to the first one about power management. For example, you are talking about tasks which could be related to hardware, and you told about RQ affinity and other things. The same applies to power management queues, right? That when some drivers, for example, UART, could go and on the sleeping CPU, you need to wake up, and you cannot provide time-based protocols. So you need also to set up not only RQ affinity, but PMQOs. And what I noticed that many even experienced developer doesn't know that, like you said, in general purpose operating system, with all gigahertz of CPU, UART is a hard thing. The CPU cannot afford it, actually. Cannot do UART nowadays. And one question, have you already answered with Pipewire? It's like the application which needs to be real time. But the other half of the question is, what applications currently already implemented as a real time, and what applications that will never need those? Like Firefox doesn't need or not? Or
I mean, the applications that don't need real time is probably most. I mean, real time is a pretty special thing. It's usually you don't have such timing requirements. But there are applications that do things correctly. I mean, the RTC test bench, for example. We ran this tool on the RT test bench doing real-time networking, and it said nothing. It found nothing. And Kurt, also a colleague of mine, he celebrates it. Yes, I did it right. Okay. There are applications that are doing it right. So, but most don't. And to your first comment, power management is extremely complicated. And when you're doing real-time and mixing power management, you're opening a can of worms. Yeah, so generally speaking, if you're going to be doing real-time, you need to forget about power management. That's currently the state today because power management is so complicated, and as soon as you start ramping down hardware and putting hardware to sleep, you can seriously be jeopardizing your real-time requirements. So it's really, really scary to play with those. So, I mean, of course, if you have people that are really skilled and you have all your tests and everything, it's certainly possible. But it's a lot of knobs and switches to play with to get it right.
So if I have a customer that is doing their application and I'm developing the BSP, and they're like, oh, we want it to be real-time, and I'm saying, okay, then you have to change the code. Then they say, nah, we don't want that, but we want it to be real-time. What are my options then? Can I tune these things? Like, I know certain things don't do time FD, that's hard to do, but malloc and of course, the real-time priorities we can change from the outside.
I mean, this is also something that the RT monitor could be helpful, because they say, let's just make it real time. Make it real time, turn on the RT monitor, and then give them the 50 pages of back traces that say, here, this is stuff we're doing wrong. It's actually a problem for real time. So you actually have something in the hand, or in your hand, where you can say, this application needs to be changed, and here's all the points where we have to do it, right? But you have to change it, because if you have priority inversion, if I'm blocking on my high priority task is blocking on a mutex that's owned by low priority, and I don't have priority boosting turned on, I don't have real time. It's just sitting there, and this sched other might be preempted, and it's not going to get scheduled for another 10 minutes. And the real time task is like, I want to deploy the airbag. Sorry, you can't, right? So it has to be taken seriously.
More than 10 years ago, I had a problem that the non-real-time threads were interfering with the real-time threads due to page locks. Is that something that still exists, you think? So the solution back then was to just make sure that non-real-time is in a separate process and not in the same process?
Just so I understand, you're saying the non-real-time tasks were interfering with the real-time tasks?
So concretely, it was a non-real-time task doing a fork, and because of that, there was a page lock taken on many pages. One of the pages was actually used by a real-time thread, and that caused issues.
Yeah, so this could be really bad. If you've had forks, and now we have copy on write pages and things like this, these are things you have to be aware of with your real-time application, right? So if the application is doing any forking, and that's also going to be a real-time application even later, you need to be aware that you have pages that are copy on write. So yeah,
so it's still a good idea to keep
it's a good idea to keep them separate
in a separate process.
Yeah, it gets really tricky when you mix real time and non-real time in the same memory space. You can do it, but it's tricky.
Real-time and dynamically loadable module libraries. Is there something to do there? Because there's the resolution of symbols in the dynamically linked libraries that happen lazily, usually. So you should turn on RTLD now, so that that's just like doing mlock all. So you have to resolve all the symbols at the time of loading the library, and not wait until you get to do it lazily, because it takes more time.
Correct. Those are some of the tricks you have to do, and I didn't go too deep. I have another talk on it's called the real-time checklist or something, where I go a little bit deeper and talk about these things like immediate binding. It's important because that's not necessarily related to memory. It's just the dynamic loader is being lazy, and it's waiting until the wrong moment. I actually want to use the function, and now it's actually going to set up the jump. That's bad for real time. So there is a lot of little things, although that's not that expensive. Because you have to keep in mind that with preempt RT, generally you have to be expecting, depends on your hardware and what you're doing, but generally you need to expect 10 to, let's say, worst case on cheap hardware, maybe 150 or 180 microseconds. So this is the kind of latency that will be there. So if I have a real-time application that has requirements under 100 microseconds for jitter, then I need to be really careful what hardware I select, right? I can't just take some Raspberry Pi off the shelf and expect to get 40 microsecond worst case latency. You're not going to get it, because the hardware just it's not set up for that. So just have to be aware. We're kind of talking like, I always tell people about 100 microsecond world. That's about the latency world we're in. If you have requirements less than that, you need to really be careful of your hardware as well. The hardware plays an important role. Memory, bus, latency, and stuff like this, contention.
All right. My question is preempt RT capable of hard real-time? And if not, why?
It is. That's what my first slide. Where are you? All right. Do I see you? It is, because people are doing it. And it's not just since September. People have been doing it for 20 years, right? People are flying to the moon and going to Mars and doing things with preempt RT. And they're actually, you know, especially if you go to like USA and you see like autonomous cars everywhere, this is Linux everywhere and Preempt RT that's handling a lot of these things. So it is there, but you have to program your applications correctly, right? And that's the big hook, right? You have to write your applications correctly because it's a general purpose operating system and it has so many things. Maybe someday Linux will be so far that you can use any interface, any driver, and you'll be RT safe. Maybe someday we'll get there in 20, 30 years. But right now, it's not that far. So you really have to be careful. What system calls am I using? What arguments am I using in these system calls? It's important. So right now, we just want to document these things, and hopefully the document of exceptions will get smaller over time, that you can use epoll, you can use timer FD, right? We want that. But right now, you can't. So.
Thank you. One last question.
Thank you for the talk. I had one question on the RT monitor. Like how exactly it finds the fault in the application that it's not real time? Does it have some logic to check if high priority task is not getting the CPU or some tolerances there, and how accurate it is?
Yeah, I can actually just really quick, we're kind of late on timing, but let me just really quickly just show you actually. Put this in the background. I kind of, oops, LTL. So actually the way it works is it uses linear temporal logic. So all of these monitors are implemented using a state machine. So basically you have a kind of an abstract logic that describes a state machine, and the state machine, basically if you violate the state machine, that's when the errors come. Now the state machine that was implemented in the runtime verification code was very primitive, and it just wasn't powerful enough to express the kinds of things we want to express. So NAM actually implemented a linear temporal logic models, and this is what that language looks like. So you can see things that we're defining things like RT-friendly sleep, RT-valid sleep reason, RT-friendly nanosleep, right? So that we're defining these things, and then at the top is just a simple rule, right? So we're just setting a rule that if you're an RT task and you go to sleep, then it needs to be either an RT-friendly sleep or it needs to be on the allow list. So there's a few things that we just allow always. And just setting up these rules, I mean, you can see things, for example, an RT-friendly wake, things like woken up by equal or higher priority, right? So we kind of define that event, and this is actually implemented in the kernel. There's actually a point, it's sched switch, or I'm sorry, it's sched wake up, where we compare the priorities. And if it's a real-time task, we compare the priorities, and we can say if this event is true or false, right? So we can use these general rules, and this is turned automatically into kernel code and then built into the kernel, right? So it's in the kernel that I'm running right now. But it's just based on rules. So these rules will start to get more complicated as we start finding more things and more exceptions and things we need to improve. But it's a very high-level state machine. Yeah.
So we don't have to give any parameters to the tool, just run it?
No,
okay.
You just run it. Like it's literally, that slide I showed you, echo 1 into that thing, it's running. And then just check your D message if you turn on the print K, or you could turn on the panic reactor, and then your system will just crash if anything goes wrong, right? But that's pretty hardcore. But I hope that someday we get to the point where you can do that. We're not triggering any false positives. So.
All right, thank you, John. That was wonderful.
Je les ai pris pour le prendre en photo. Tout en bleu, ils sont tous pareils. Oui, oui, je sais. Viens, monsieur Jean, je te tire le portrait. Ah bah oui. Avec la postelle. Ouais. Non, j'ai HDMI ici.
Je vais déjà mettre dans le bon sens l'ordi. No. Don't do that. Merde, il monte la fenêtre, je regarde.
Tu vois le titre, tu vois le...
Okay, we're ready for our next talk here. We're going to switch gears a little bit, and Jean is going to switch us to 3D printers and CNC machines. So, thanks, Jean. Welcome.
Hey. Hello. Thank you for being there. We tried to talk about something a bit different. It's not about kernel and so on, although it is what I do all the time, but I wanted something a bit different, and let's see. Who am I? So I'm Jean. I'm a freelance running neworbits.com, doing low-level stuff, bootloaders, hardware, software, Linux kernel, optimizations, all those. I have collaboration with Mind, Mind.be in Belgium, so we are working together on those projects, internal projects and also customer projects. It's a great collaboration for years. And so, as you can see in the box, what I do is work on a lot of hot topics that we are discussing at this conference, like SBOM, right? Fast boot, secure boot on various platforms, optimization of resources, of boot time, all of those. That's what I do all day long for customers. But this is more of a side project. This is more of, I like to tinker with machines, use open source software the best I can. And this is about my findings and how I do stuff. But I really would like you, if you have more info, more use cases, more usage, this presentation is a living presentation. So if you have suggestions, I can change that for the next talk, right? Next conference, let's see. All right, so it's about using open source all the way. It means from A to Z, hardware, software on the machine, but also, more importantly, software on the host machine. So you have your laptop, you want to create a model, you want to print it, you want to CNC a part. I want it to be fully open source. So I will try to give a round trip on the best software we can use, open source, of course. And I will show you how it's done. And if time allows, I have a bit of a demo on FreeCAD. FreeCAD is the CAD software on the host. So what are the needs? I would say for 3D printing, it's really common. So everybody knows that. It's really stable, really robust. You can print 24/7, no problem. This is not an issue. But you need to find the correct tools to do it. On the other hand, CNC is a different beast. So it's much less common. It's more industrial. And the goal is to do simple CNC, three axis,
rather manual. So when you have to change the tools yourself, you add all by hand. Let's say it's a light CNC that you could even use in small business cases. If you do panels for automation, you do plexiglass like this thing, you could CNC that kind of stuff, no problem. But it's not industrial, it's not Formula One part, you know, that you need 5-axis machine and micron precision. It's not the same world. This is light CNC, but still really robust, really workable for everyday use. Right, starting point. I started all of this because I could put my hands on a machine that I got for free, but it was really obsolete and not doing what I wanted. So I say, why not do it the right way and do it fully open source from scratch? And this talk is about, I will show you the case of 3D printing first, because it's much more common. And I will try to use all those principles to do CNC. That's a bit what I want to show. Quickly, a bit of history of 3D printing. You see there the very first 3D printer that can replicate itself, 2005. So it originally wooden stuff, threaded bars and all, bolts, screws. That is meant to be, you can do that at home and you can replicate the machine so you can make it better. So all those wooden things you can replace by parts that the printer prints itself, for itself and for the next. Scary, right? Then came more. The hardware went better, of course, but software started to pick up. That's really important. So 2010, Prusa started with a machine that is really inspired by the one you see in the picture. Then came Ultimaker and so on, firmware for the machine, printing farms and all. So a word about open source. So what is open source in this case? It's not only software, it's the whole chain. So it's electronics, you know, the hardware, the schematics, the parts that you can find even. The extruder on the machine is really a part that is custom made to extrude the material. The heater, all of those hardware parts, they must be open source as well. We need to find schematics for them, resources for them. Obviously, also you need the firmware. Firmware on the machine needs to be open source. That's pretty basic. Yeah? It's pure software that you compile and flash on the board. The host tools need to be open source. If you want to do it fully, you take a Linux machine and you install purely open source kernel and software on it. You are safe, you are good. Although most of the host tools, they can run on Windows and Mac as well. It's really flexible that way. About the slicers, for instance, the one that slices your model in layers to be able to print them. We have an history there, and for instance, you see slice 3R. Slice 3R is the first one that was there. Was merged and evolved into the Prusa slicer that we have today. It's fully open source. Ultimaker is making one, Cura. And then you have Octoprint, really the thing that you put on the machine, the laptop to control and monitor your print. And also important, the models. So you need models to get inspiration from or to print. You can find them on printables.com from Prusa. Thingiverse is there as well. That's a bit of it. So open source to me, it needs to be from A to Z, the whole chain. So now 3D printing. What do you need as host tools? See my mouse? Not really. Oh, yes. All right. So in blue, then you see you need a model. So what do? You have a CAD application that you can create model from a 2D bitmap, 2D drawing, or from purely 3D modeling. The thing is, you get a part really on your computer. What you do then is you slice this in layers of a given size. There are a lot of parameters, of course, and this for every layer, you generate G code. G code is machine code. Just is basically text, a line telling, please go to this location, X, Y, Z, with that speed. Please draw an arc, so a round trajectory. Please do this, please do that, please enable, please eat at that temperature, and so on. That's the G code. So you will really need the slicer to generate the G code from the part you have. And then the G code you send to the machine, so the yellow part below the line, it's the machine, 3D printer, right? How you do it, the old way, the old-fashioned way, you put the G code on a SD card, you insert the SD card in the machine, and you do print. And it starts to, every G code makes it move, and so on and so on. So you print, that's fine. You have an LCD, a basic two-line LCD, something really basic with buttons, and then you can control a little bit what you do, change the filament, reset it, whatever. And then the new way that you can use, it's really interesting, the green part is the controlling part. So on the laptop or Raspberry Pi, you put Octoprint, for instance, and you can monitor the whole thing remotely. So you can start a print and go upstairs, take a coffee, and look on the smartphone. You see the progression and the temperature and everything needed. You can control the print from there. That's quite convenient. Right, that's an overview of the tools. Now I will give you a rapid tour of those, what they are as open source. It's really important. Open source, I will not mention, not open source tools, which could be really good, of course, but this is not the point. 2D, basic 2D stuff. Vectorized bitmap is quite interesting. You can take a picture, vectorize, you will get a part that will neatly be imported into the 3D CAD program. As CAD, first Blender. Blender is not really a CAD tool. It's more animation, to do movies or small sequences. But it can be interesting because it has a lot of features, a lot of plugins, a lot of stuff. I use it sometimes to generate specific shapes or to deform a shape. That's quite nice. But be careful, it's not a real CAD program, so it will destruct geometry. So, for instance, you take two 3D parts, you do a Boolean operation, like intersect them, you will get the result. It's fine. But the two parts, the original part, they will be destroyed in the process, which you can accept in some case, but a real CAD program doesn't do that. It keeps the whole history. So if you change something in the original part, it will not be destroyed, but it will apply the whole chain up to the result. So I mentioned Blender because it has features that can be interesting. Next one, OpenSCAD. OpenSCAD is a script-based generation. So if you want to generate parametric parts, repetitive parts, that's really nice because you write like to do a gear. You can specify the number of teeth, the height, the length, the whatever, and it will generate. It's really a script. So it's quite nice. There are a lot of libraries available to do a screw, for instance, to do a bolt, to do a gear, whatever, you can do it. All right. Next one, FreeCAD. The one I like. I want this talk is about mostly FreeCAD because I think today this is a one-stop shop. I mean, with only this one, you can do everything you need. You can do 2D sketch, you can do 3D parts, you can do an assembly of parts to make a product, whatever. It's fully scriptable in Python, so you can automate a lot of stuff there. And today it's really mature, so from 0.19, 0.20, it's really usable. I mean, you can use it, no problem, works. Doesn't crash like every 10 minutes, it's really mature. It's coming great. 1.0 is really good now, and it's quite recent. And then you can see the CAM. One module is CAM, or what a part it was before. Now it's CAM. This is the module that allows you to do CNC. We'll see that in the second section, of course. So with one tool like FreeCAD, you can do really everything you need. Right? Now the slicer. Slicer is converting the 3D model to G-code. Two big ones, open source Prusa Slicer and Ultimate Cura, they are quite comparable. There are pictures of there. A lot of options. You can specify a lot of parameters for the printer you use, for the filament you use, for the model you are printing, and you can save that, export, share on GitHub, whatever. It's really, really good. It does a lot. Yeah. And then there are exotic slicers. They are really slicers that you can use for a specific need. Like you see the picture right there, you can print things upside down at an angle without needing support. Because normally if you print part and then it comes bigger at the top, you need some support below it to support what you're going to print. Otherwise you print filament in the air. It will mess up, you will get a nice spaghetti plate of plastic. Not good. So this one can do different stuff. There are infinite Z as well, so if you want to print a part that is 10 meter high, you need a 10 meter printer, right? No. With this, you can print the thing at an angle and put the part on a sliding, we say a rubber band, like you see in the airport for your luggage. You can print that in angle and then advance the part every time. You can get a really long part. That's one of the examples. There are a lot of them. I mentioned two of them, but there are a lot. They are experimental mostly, but working. Now the control part, what's the green part? It's really nice to do the setup and maintenance. So what if you need to load new filament in the machine? What if you want to tweak temperatures and all, and see graphs and so on? You can see the picture. You can control the whole thing there. On the left side, you also can upload the G-code directly to it. So drag and drop from your machine, you drag the file. You see there G-code in red. You just upload that, you do print, that's it. And then you get a nice camera view. You can do time-lapse, you can do videos, whatever. Right, so two types of control applications. It's mostly linked to the firmware you use. So the usual way, it's to have Marlin as a firmware, we'll see in a minute. And the control in that case is Octoprint. Octoprint is really nice, maintained by one person, the same since the start, so it's really worth mentioning, I guess. The other one is if you have Clipper as the firmware, then you have Mainsail or Fluid UI applications on the smartphone or on the laptop. It's really, really cool, really nice looking, and a lot of features, a lot of plugins. You can do a lot of stuff there, you can see. For instance, you can do a time lapse that every time a layer is started, it will take a picture. Every time, so the head is like on the side. So when you play the movie, you don't see the head moving. The head is always at the start, and it does. Cool, right? Next point, firmware. That's what runs on the machine itself. We have today two big families, two big software. First is Marlin. Marlin is the old one, the first one that evolved a lot. It's really stable, supports a lot of printers. But it performs all the tasks in one firmware. So it does the real-time tasks. There is no OS, but it's really like a really bare metal thing on Arduino. So it's moving the head, looking at temperature, whatever. But it's also doing the UI with the LCD. It's doing a lot. So it's maybe less performant, but it does the job. You can print 24/7, no problem there. Then the new stuff that it runs really well as well is Clipper. Clipper divides the firmware stack in two parts. One is the RT task, as I say, on the board, and the other runs on a Raspberry or on a PC, and does the whole thing, all the rest, basically. I will show you there a graph. So on the left, you have Marlin. You can see Octoprint does the web server to do the control, the code, everything, and sends the G code to the printer. And then Marlin does the whole thing. It interprets the G-code, moves the motor, everything. It does the UI with LCD buttons. And when I say G-code handling, you have to understand that when you draw an arc, for instance, it's only one G-code. But in the firmware, there is a lot to do. You need to interpret every tiny movement, make the head move a little bit, and be still real time, because otherwise the arc will be like not round, right? So that's a limitation of the thing. On the right side, you have Clipper. Clipper implement all the real-time task on only that on the machine, and then does all the rest on a different board. You can see it could even slice the model for you. It could even integrate the slicer. That's the new direction that new printers take. So they are even bought with an ARM-based or Arduino-based processor for the RT task, and then there is a main processor for all the rest, all in one board, quite convenient in the machine. Right? That was about the firmware. Now the machine. So when you buy a machine, it's like on the left. Nice marketing picture, right? It's so good and it works, no problem. But in reality, what you end up is what is on the right. We've added a lot of stuff there. So there are only 4 power supplies, an heated bed, so that you can print different materials. There is a Raspberry Pi on the side with Octoprint and a camera, and so on and so on. Optimized airflow, that's really important. You need a good duct tape to do that. You can see the blue at the bottom. It's the optimized airflow. But yeah, that's really fun. You can hack the machine as much as you want. You hack it, you try, and there is even a door you see in cardboard, whatever. Quite nice. But then you say, okay, but what about my firmware? I will be hacking my machine like crazy, but is it supported? Yes, it is. What we did on this machine has been hacked for robustness, speed, print size. The Z-axis has been modified so that we can print bigger parts, for instance. Higher temperature, multi-material, so we can print PC or those exotic materials that require higher temperature, for instance. And the remote and the control is via the Raspberry Pi, for instance. All of that, the patch is like 40 lines of code. It's not line of code, it's line of configuration. Just configuration. So you can see in the shell there, it's just an header file that you change with, there are macros. Define this, just change that. 40 lines of code, really nothing. You recompile, you reflash, the machine supports what you just saw there fully. So that shows you it's really ready for improvements. It's really easy to use, really easy to hack. Quite nice. Okay, that was about 3D printing. Easy. No, CNC. Second part. So CNC is a different world. So it's much less common. It's not that you don't find that everywhere. It's mostly industrial. You buy a machine for a huge price. Software costs you a lot. It costs you tens of thousands, and every year you need to pay extra and so on. It's really good, but it's not for amateur or do-it-yourself hackers. But no, you can do it. So I started from a machine and I said, what would I do with this? So I noticed CNC is quite similar to CNC because hardware is kind of the same. It's X, Y, Z, move ahead, right? It's put on, put off, measure maybe temperatures, things like that. But the core of the machine is the same stuff. It takes G code, moves ahead. Right? But it differs as well. The tools, they must be different. They are different. You cannot use regular tools to do constraints. The head moves, you interact with the model, you cannot bump into the model if you go too far, whatever. Also, the start reference point. So in 3D printing, the start is just the start of the bed where you print. In CNC, it's different. The start is on the part that you want to engrave. So you need to calibrate, put the head precisely at the 0 point, and then start going down. You would start, so basically you do 0 there, and you go negative in Z axis. While for 3D printing, you put a 0 and you go up. That's the main difference. So you need a software on the host that supports this. Okay? So rapid tour of host tools that I tried myself. I just tried a few of them. I'm sure there are others. Those are open source and they work, but more or less, right? PyCam, I tested first. It's a set of Python scripts and an application. You can see screenshots. It's basic, but it works. It does the job. Not many options. It's not maintained anymore. It's quite old, but it works. So as a start, it was fine. Then I tried Linux CNC distribution on a BeagleBoard or Raspberry Pi. It works as well, but I found it really hard to use and yeah, not really good, but it's a long time ago. Then I saw CNC Toolkit. I see guys using that. I never tried myself. I don't know. Then comes FreeCAD, latest release, really good for that, really nice. It works out of the box. There is a CAM module. So you use FreeCAD to model the part, to subtract a part from another, you get the result. Then you can instruct the CAM module to generate G-code to engrave this, right? So you can do profiling. Profiling is just get the outside detour of the part. So you can, like this part here in plexiglass, you can do the outside. That's the profiling. Then you can do drilling, yeah, holes. And then you can do engraving. So let's say I want to put the embedded recipe logo in this. I can just engrave ER embedded recipes in this board. That's engraving operation. So FreeCAD is highly configurable. You have a lot of options. You can do Python scripting. You will see it's really convenient in my case. It's mature, as I said. So reusable, stable, no problem there. So what about the machine? So a friend of mine gave me the machine for free. I was really happy to get it. Sorry, quite old, but looks like new. You know, it's German over-engineered stuff. Weighs 40 kilograms. You need alone. It's a bit heavy, but it's really good. Mechanically, it's really good. The power supply is just a monster. You know, toroidal transformer caps that big, really good, but firmware was really old, was running off non-standard stuff on the serial port or parallel port, I don't remember. Application was only on DOS, 6.2 something, okay. It works, I've seen it working, not bad, but it's not what I want. And I think now the application, you cannot find it anymore, you have to pay or whatever. I did not want that, so what I did is try to hack this to keep what is good in the machine and modify what I want. So here comes the tinkering. So leverage the hardware electronics, so the hardware of the machine, the power supply, I keep. And then I take the best of the 3D printing stuff. Here comes the 3D printing part that I explained before. I take the hardware and the firmware, I integrate this in the machine, and then I have a CNC machine. So how do I do that? I choose from a list of boards that are compatible. They are supported by the firmware, Marlin. I choose for a Rambo board. Rambo should be robust, I guess. See, why? Because 24 volts, because it's the power supply I have. And Rambo stands for RepRap Arduino Marlin compatible board. Was just what I need. Then you have a USB interface to connect the laptop, to do the update, but also to send G-code if you need. And I've added basic LCD buttons and SD card reader. You see the blue thing. On the left side, you see the SD card, this white stuff. It's just the SD that you insert into it, and you can read from the SD. So yeah, I have the basic stuff. You can see more or less clean wiring. Give me a note after the talk. Just interface the stepper motors, the end stops, power supplies. Let's go. What about the firmware? Same as for 3D printing. 30 to 40 lines of config. Not a single change in the code, just configuration. So I've put my oscilloscope on the stepper motors, looked at the current, the phases, everything, timings. And from there, I derived the parameters to put in the configuration file, test it again, until it was okay. So just simple modification, a little bit of patience, you get it. I have, by the way, a GitHub repo in the reference if you need. So yeah. That was about the machine. So now about FreeCAD. So I choose FreeCAD because you can do everything you need just at just one place. So what do you do then? You can configure FreeCAD to have preamble code and post-amble code. Means G-code instructions you have to put before the print job and after. That allows you to set the starting point, 0 that I was talking about, to ask you via the button, are you okay, are you ready, is it configured correctly? You say, okay, you press the button and it starts. Let the spindle start, so the machine runs, does its job, and at the end, you run the post-amble code to come back to home, to 0, put the spindle off for security, and so on. So that's basically what you need to configure in FreeCAD. It's mostly G-code, extra G-code, nothing. And then I realized the post-processor, so the Python code that exports the G-code was not compatible with my firmware. Stupid stuff like \n, happens. Some fast moves, because when you are not in the part, you are outside the part, you can move much faster to gain time. When you go in the part, you need to respect a speed, depending on the material. That kind of fixes. So what I did is to write a Marlin post.python script. So it's basically the one that is in FreeCAD. I copied over, changed, and put in a directory. It takes this one instead of the original one, and that's it. You can see on the picture default arguments. Then you can see the post-amble, pre-amble code, basically G codes. You see M300 and so on. You can do a beep at the end, basic stuff. So that's about FreeCAD. I will give a demo of FreeCAD if time allows. Should be fine. Something else? I did not try that, but I've seen it working. It's really cool. You can engrave the PCBs with FreeCAD. So there is a plugin, really magical. You import the KiCad design files in this. It draws you the board, all the layers, everything, and from there you generate the G-code to engrave and let the traces, only the trace you need. You can see the part in green. That's what the head will do. All the green stuff, the head will just remove this. And it will keep only the traces. Cool. Only for 2 layers. Otherwise, yeah. But yeah, really useful at home. You don't need to buy expensive stuff. You can do that if you need. That's about the CNC stuff. So conclusion, quite rapidly. Open source 3D printing, it's really doable. And my opinion is really the way to go. I don't see any other option. It's really mature, robust. You can do print farm, you can do whatever. It's really nice. Open source CNC, it's okay. Quality is more than okay. It's usable, it's mature. For small companies even, I find it really interesting because you have the freedom. You don't have to pay all the time. You are at home, you have your software. you do as you like. So I will try to give a demo now. So start from a basic sketch, do a part, and engrave in this part. Let's see. This one. Ooh. Nice. So this is a part, right? Supposed to be a keychain. So you see, there is a 3D part, basic block, and then try to engrave a hello stuff in there. That's the idea in 3D. So how do you do that? You start from a sketch. This is the sketch. It's a 2D stuff. You give dimension constraints, whatever. You draw in this. You can move stuff like. You see, it's not. This one is not constrained, so I can move it because the vertical line is constrained, so it keeps vertical. But the point there is no constraint, so I can move it. I could constrain it with a dimension on the right or an angle on the left, whatever. Then it will stay like it is. A keychain requires a hole, right? I will put it there. You see, it's calculating stuff because in the background, it's recalculated all the parts that the CNC needs to perform later. So I have my sketch now. I close it. You see, it has been updated automatically. That's what I was talking about, non-destructive geometry. You generate one part, then afterwards you change parameters, dimension, whatever, and it reflects directly in the part. And then I have the shape string is just the hello text. And this hello text, it's a shape in 2D, then I can extrude it to get a 3D part. Then what I do is a Boolean operation, so I remove the hello text from this initial block. That's the cut. You see there's a cut. It's a Boolean operation. See, 5 minutes, I'm okay. You remove basically the hello object from this one. That's the cut operation. Then, okay, the model is fine. What you do now is try to generate the CNC G-code from there. So you create a job. You see a job here? That's the job that will contain operations. The job has a lot of options. The tool you use, the speed, all of that. And then you create operations in there. So, for instance, profile, you see a profile? That's the one. You profile the part. So we just do the contour, and you see layer by layer. Because you cannot engrave like 10 millimeters at a time. So you say, I want 1 millimeter at a time, depending on the material. It will do it 10 times. You see? That's the one. Then, remove this. You can do an engraving. So you see, start from this point, goes there, engrave this, and then back, and do all the letters. And I gave a finer pitch for the example. So you see all the layers. So it's just doing engraving of what is needed to be removed. Cool, huh? And from there, then we have the part, they are generated. Now we'll export. So we go to job. You do post-process, and it generates the G-code. So you see the preamble, right? It does all the thing, change the tool if needed. Even if it's manual, you can change the tools in between. Does all the G-code. You see it's layer by layer. So you always go from 0Z to -Z. Does the whole thing, and then at the end, you see the post-amble. It will stop the spindle, go back home for security, beep, do something else, whatever, and that's done. So you get it. You save that. Save that, put it on a SD card, go to the machine, or upload via the Octoprint if you have it. and you can start. That's basically it. Right? It's easy. That's a simple demo, but really FreeCAD works really well. So you can do really bigger parts on a regular laptop, no problem. Then I have another case is where you need a more complex part. This is a part. This is a cargo bay for a small plane, RC controlled plane that we put below. It's a belly, like kind of. You can see it's made of different parts. So this is the shell that I remove, just for you to see. There is a plate in between, so you have two tanks of things you can put in. You have the doors at the back. You can operate them while flying to drop stuff. You have brackets. You have a lot of them. See, so it's a complex assembly of parts. And the message here is that some parts you just 3D print them directly, like mechanism, brackets, you print them. So export the STL, go to the slicer, print them. And then there are parts like the flat parts you can see with the green. You can do CNC. See, this is a CNC G-code. So just to show you, FreeCAD can do it all. One assembly contains 3D and CNC parts, all in one tool. It's basically what I wanted to tell you. Let me see. Back here, so that's this example. Then if you want, there are a lot of references for you to see. My GitHub there, if you want to see the scripts, whatever. Right. Questions, remark? Do you use something else? You have suggestions? I'm there.
I built some of 3D printers by myself. Till now, no CNC. And major problem which I had till now was to make like its embedded world scenarios, build a BSP with all needed components like Clipper, Open Print, Octoprint, and so on. So have you seen anything packaged like in Yocto or something like this to make life easier?
For the old tools, you mean, or to be the printer itself?
I mean, a BSP which should be used for the printer.
No, it's not really a BSP in that case. It's really just like Arduino kind of code you put in a project, you compile. It's rather basic, I would say, even if it's complicated. That's the way to go. Or go to Clipper or to Marlin. You will see a lot of on the GitHub. You will see a lot of README documentation, but it's really easy to use. I would say really easy to build.
Because for my in my experience, it was too loosey to all of these parts like Clipper configuration, Octoprint configuration. Everything is just pulled from each other. And just make a BSP which is concretely for this printer with all needed parts.
That's correct. It's 3D printing is a bit experimenting yourself, try error. Otherwise, you have a lot of money. You really nice machines. You see Vorum Design. It's a brand.
I built one of this.
You go to the website. You generate an SBOM. Yeah, it's really the BOM of material and of software. You add options, size, you click and you get the BOM, and then you buy the parts from there or from where you want, and the software is also configured correctly for the printer. That's really the luxury solution. It's really nice, but that's the high end of stuff. You can do it really yourself, no problem.
Thank you. On the market, we have a number of 3D printers that can be, let's say, converted to Marlin or similar, some low-cost stuff.
Yes. For the CNC, we have something, or we have to resort to finding old hardware, let's say, and then hack on it to obtain something.
And there are also options. You can buy machines that are ready-made or in kit form. It's existing like, what was it? Mechanica.io, you see this reference?
Yep.
Then you can find kits that you buy. You buy and you build yourself in all sizes. It's quite easy. It's basically aluminum rods, stepper motors, belts, and so on that yet you assemble.
Thank you.
Can you, in the CNC setup, can you actually tilt the tool head somehow in the CNC machine, or is it fixed?
You mean to have a fourth axis to...
Yeah, tilted the tool head so you can kind of mill underneath some sort of a top layer.
It's
is that
also,
possible?
yeah, it's possible. I did not try it myself, but I know it's possible. I've seen some, what was it? I have this somewhere. In the CNC toolkit, you see?
Mm-hmm.
This can do multi-axis. So there are tools to do this.
And the CNC device which you have can do multi-axis then?
Of course, you need a machine with a 3D plus rotation of the head. And you need a special machine for that. Or
Thank you.
one.
Thank you.
But I do only 3D myself. But why not later try something else?
Cool stuff, thanks.
Thank you. Over there. Boink. Koen had a question, no?
You should practice with chocolate.
We are in a basketball training session. Oh, nicely. Oh, missed.
Hard to catch.
Yes.
So my understanding is that you're reusing the firmware from the 3D printer and modifying the config to apply it on CNC machine, right?
Yes.
For a 3D printer, the task is quite easy and it's sufficient to use open loop, right? But I would say in the CNC, based on the material that you're using, there are like other elements such as forces that you need to take into account and heating of the part of the material, right?
Yeah, correct.
How do you consider that for the CNC machine with these solutions or with this firmware, or are you even considering it?
Yes.
Considering that you are using the 3D printer firmware?
Indeed, CNC in some material is really tricky. Like aluminum is really tricky. If you go too fast, it's kind of bouncing. It's like too stiff. If you go too low, it melts. It's a mess. It even breaks the milling tool because it melts around it. So you need to be careful about the speed and the rotation speed of the machine. And indeed, as you said, I'm using a 3D printing firmware to do CNC. You can see on the blue screen, there is 0 degree, that's the filament, because I'm not using it. 22 is the board. Yeah, the board, in my lab is 22, but I don't care much. But yeah, for the speed, it's really important. So I have a sheet of per material I made testing. I broke a lot of bits, of course, because with aluminum or some plexiglass is better than other. Like the transparent is better than the white, for instance. The white melts a lot, while the transparent it makes it really clean. So I adapted the speed and the oiling also. You need to oil the stuff regularly, but it's manual for the moment.
So currently it's only open loop. There is no, let's say, capability of expanding and consider, for example, force sensors in the CNC?
No.
All right, thank you.
Yeah.
Okay, thank you, John.
Thank you. Thank you to Belieber for this conference. Really nice.
Okay.
Okay, next up we have Tim Bird, so we'll say welcome to Tim. Thanks for coming.
Okay, I know that we're running a little bit late and I'm all that stands between you and a break, so I'm going to do this fast. This is a presentation that is not a comprehensive look at everything. That's not possible. There's so much going on with embedded Linux. So I apologize in advance if I miss something that you're interested in. This presentation will be in kind of two parts, what I call the fire hose or the shotgun part that's really fast. And this is actually, I give this presentation at other events, and so I have a lot of material in here that's kind of reference material. So there'll be links and stuff. There'll be slides that I only spend like 5 seconds on. So I apologize for that. But if you're interested in the topic on that slide, I've got links to LWN.net articles. I've got links to presentations and conference talks. And then at the end, I'll try to wrap it up. So it's going to be a little bit like this, drinking out of a fire hose. But let's go ahead and get started. We'll start right away with the Linux kernel. And I'm actually going to start my stopwatch here. As you notice, the Linux kernel release schedule is so boring. The most exciting thing we had in the last year was that we delayed the release by 1 day because Linus was lazy and did it on a Monday instead of a Sunday. So you can pretty much set your watch by Linux kernel releases, except in the case of 6.15, when will it occur? Well, it happens to be Memorial Day weekend. So I don't know what that means. I think I'm not going to hold Linus to be working and redoing a kernel release on Memorial Day weekend in the United States. That's a big holiday in the United States. This is the only time I asked AI for assistance for this talk. I wanted to know, has the kernel ever been released on a Memorial Day weekend? And the answer is no, unless you count this Saturday, and I don't think this is a Linus release. This is a 2.2.9 back in 1999. So over 20 years ago, there was a release on Memorial Day. The bottom line on all of this is Linus should really take more vacations. But anyway, it'll come out in May. It'll probably be the next weekend or the Wednesday or something. That would be, whoa, mind-boggling. So I'm just going to go really quick through kernel releases. the last year's worth of releases. So in 6.10, we saw a bunch of improvements with Rust, encrypted interactions with the TPM. Cryptostats, they had this whole subsystem that was keeping track of cryptostats. They just pulled that out because nobody was using it. We also got alpha code removed. The interesting thing I thought in Linux 6.10 was they have this new system for doing memory allocation profiling. So they have this really neat set of tools and instrumentation points in the kernel for tracking memory allocation. And it's really, really useful. And particularly, it's useful for tuning like your cache hits on your kernel data structures. And so if you think that you're getting affected by that, then this is the tool for you. It's a really, really interesting project. In 6.11, we had a new power sequencing subsystem, and I'll talk a little bit about that later. Our very own Wolfram Sang got something in the sloppy logic analyzer, which is a GPIO analyzer inside the kernel, kind of a poor man's GPIO, so you don't have to go out and buy your own. I don't know if it completely replaces OpenOCD or something, but anyway, that's really cool. There's the kernel is getting so big. There's all kinds of great stuff in there. There's a new runtime const macro. So this is a little bit of replacing kernel code at runtime. So you know we've got virtual machines running in the kernel. Why don't we also have self-modifying code? Actually, that's nothing new to the kernel. It's only used in one place right now. And what it does is it converts some variables into some hard-coded instructions. That I think they're using immediate operands so that this particular hot spot in the geentry code is faster. And then there's a new VDSO implementation of GetRandom. And the extensible scheduler class, the big news with the 6.11 release was that it did not go in this release. It actually came into, there was some disagreement about the status of it. But it did land, I think, in the 6.12. So Preempt RT, we already heard that that was the release that the Preempt RT got kind of finalized. And I'll talk a little bit more about that later. The security module subsystem now uses static calls. So you see a lot of these things in the core are kind of optimizations. So instead of jumping through indirect calls, it's possible to use static calls, which are faster. The tracing ring buffer that persists across reboot, integrity policy, management enforcement. And here we go, the schedgext was actually put in, and this was referred to in the CMOS talk. So this is pretty new. It's exciting that people can experiment with their own schedulers without having to recompile the kernel or even submit them upstream. So there's a little bit of an issue there. But we'll see. We're already seeing a lot of experimentation, particularly by the people who are running data centers. But you also see in the SteamOS case, people want to experiment with schedulers for different workloads. And 6.12 was selected by the Civil Infrastructure Platform as their new super long-term stable release. That means they're going to be supporting 5 kernels and for 10 years. That's a long time to support a kernel. So when they pick one, it's kind of a big deal. In 6.13, now we're getting into January. ARM64 can run Linux in virtual machines under the ARM confidential compute architecture. Some other stuff about ARM64. The lazy preemption patches have been merged, and I'll talk about those in a sec. New thermal threshold system. And enough Rust is now in the kernel. There's enough Rust infrastructure support, in particular for VFS data structures, so that they could handle an implementation of binder in the kernel. And that is pretty crazy. I can remember when the binder support, this is an Android IPC mechanism. It was a big deal when it got accepted into the kernel. And now it's written in Rust. I don't think it's made it to production yet. I was talking to Greg about it the other day. But I want to talk just really briefly about lazy preemption. So this is a new set of patches that has to do with real-time, but it's not for full real-time stuff. So this is a allows kind of a cleanup or a simplification, if you will, of the different preempt states that are in the kernel. So you have preempt none, preempt voluntary, preempt full, and preempt RT modes. And of course, preempt RT is kind of the full-blown RT mode. But you had kind of a lot of these other different modes you could run the kernel in. And the real-time developers really wanted to clean that up and kind of simplify it. And so they've done this work here. And I will let you read the LWN.net article, which will do it more justice. And then just a couple more things with 6.13, multi-grain timestamps for VFS, a new MAdvise thing to install guard pages. RiserFS is now gone. F2FS has some new features. One thing that I thought was interesting in this release was we're seeing a lot more, FDO stands for Feed Directed Optimization. So we're seeing a lot more tooling that where this is a lot of Google and the other cloud providers are doing this type of stuff, where they're taking a kernel, they're running their workloads on it, taking the information and giving that as feedback back either to the compiler or to actually they're taking the binary, disassembling it, reassembling it so that they get better cache hits and better locality on a lot of the operations. And so you're seeing a lot of this optimized, automated optimization of the kernel. And so I think that's actually really interesting. And that's one of the themes, I think, that we're seeing a lot lately. In 6.14, which is the latest kernel that came out in March, we have a new check, the AT exec VE check, to allow us a little bit better security for scripts. The Fuse file system has some performance gains, and then this other stuff. Let me see. Okay, so we've had the merge window for 6.15. I couldn't find a terribly lot of stuff that was relevant to embedded here. So we do have a new kernel command line option having to do with tracing. Automatically disable the trace after the init process is started. And then Fuse now supports handling timeouts. So this is kind of our current status as of May 2025. I apologize. I normally take more time to go through this type of stuff because this is kind of celebrating the work that a lot of the consulting companies are doing. But these are kind of the commit counts. Don't read too much into this. A lot of these, you can have something where you do a single refactoring and get like 500 patches out of it if it's the right type of thing. But this shows you, just as an overview, what kind of things people are working on, who the kind of top contributors are. You see a lot of GPU work, a lot of stuff in timers, SoC support, obviously, and stuff all over the kernel. One note, when I did this, I noticed that I misspelled his name. Uwe Klein-Koenig actually switched from Pengutronics Bay Libre. I thought that was interesting, little thing you notice. If you're interested in kind of stats about the kernel, LWN.net has this thing called the kernel source database. And just the 6.14 release had a little bit of a dip, not a big deal, but people kind of noticed that there weren't as many. I think there were about 9,000 commits in that release, and it's normally averaging about 12. So no concern. We'll see. I don't think it's a long-term trend. Okay, just a couple of miscellaneous notes. So Linus really likes imperative commit messages. And he was quite polite about kind of asking people to do better with their commit messages. You can read that message there. Okay, so technology areas. And a lot of the resources I'm going to refer to were talks from ELC Europe, which was last year in September, and also from Plumbers Conference. So if you see something in here you want to look up, go to these sites to find the individual talks or pages. So I have started something called the Boot Time Special Interest Group. And this is just a working group. It's an ad hoc group. It's not supported by any organization. We don't have a board of directors or a committee, a technical committee or anything. It's just a bunch of people that get together on a monthly call and we talk about boot time. If you are interested, our next monthly call is coming up May 27th. Here's a list of kind of the things that people are working on. And like I said, these are going fast. In terms of the core kernel, the capability analysis, so there's this set of patches. They're not in the kernel yet, but there's patches in progress to do what are called capability analysis, where they, this is for locking and thread safety detection. So you put annotations in the source code, and the compiler, the Clang compilers, GCC doesn't support this yet, but the Clang compiler can actually check that you are doing thread safe operations, or that you're releasing the locks when you're supposed to, or that you have the appropriate locks. So this is actually another example of automated tooling to improve the kernel, in this case for thread safety. And of course, we have Rust continues to be developed in the kernel. We don't have a whole lot of production grade drivers yet, but if you're interested in Rust, and you should be because of that red thing at the bottom there, John Corbett gave a really great talk at Open Source Summit Japan and talked about some of the reasons why Rust is taking a while to get there. But I heard this from Greg KH at Member Summit last November. Linus says the future of Linux is Rust. Okay, so all of you people who are, are really proficient at C, you've got a little homework. Sometime in the next 5 years, you probably want to check out Rust. And let's see. Oh, also, Linus does not like case-insensitive file systems. This was a little bit of a blow-up. I don't know if you saw that on the list. But there was a... Linus, this is the... How can I put this nicely? This is the least diplomatic I've seen Linus in probably 5 years. So he's really improved. Anyway, so there's some talks here about maximizing SD card life. Great talk by Andrew Murray. It was given last year at ELC Europe. In terms of GPU, you've got a ton of GPU work going on. And so I think that is great. That has been a sore spot for, particularly for embedded. We've always had a lot of GPU stuff out of tree, but a lot of it is now getting into tree. And Mesa 3D also has some good stuff going into tree. Let's see, networking. Here's just some talks about networking. There was a whole track at Plumbers. And these are kind of the stuff they were talking about, reducing the overhead of network virtualization, state of buffer bloat. Again, I'm just giving you a real skim across the surface. In terms of power management features, this was a great overview talk at ELC Europe about the different features. And one thing that was really interesting was Stephen Boyd was there talking about kind of, there's so many things in the core kernel to do power management, suspend, idle, frequency, all that kind of stuff. But he was saying that we kind of needed to look at it also from an SoC standpoint. And he made the case for having an SoC-specific power driver. Power management driver. And I thought that was a really interesting talk. I don't know the status of it since then, but that's something to check out. And then, like I said, PowerSeek was added in 2.6.11. This allows you to handle the sequencing of when you bring power up on your SoC, because there's a lot of issues involved there. So the kernel has this new capability to handle that much better. Okay, real-time preemption. What's left? Okay, so John spoiled my surprise. Nothing's left. They were accepted in the 6.12 merge window. Thomas Gleixner printed the pull request on paper, wrapped it with a golden bow, and handed it personally to Linus. I thought that was great. And he did it with a nice ceremonial bow. And that happened in Vienna. It turns out, of course, there's always a couple little things that you want to clean up after the fact. So my advice to people was to wait until 6.13. But there are patches outstanding. There's about 58 patches still outstanding. But it's no longer like the features out of the tree. The features definitely in the tree. These are just development patches, right? So this is the same type of thing that every other subsystem has. They have their next tree saying, what are some more things we're working on? And so even though you see that there's patches not upstream, that's totally normal. Every subsystem has patches not upstream. They're working on a lot more stuff. If you want to get a retrospective on kind of all this stuff and kind of the history, there was a great talk by Sebastian and by Steve. I think those were at, it was Kernel Recipes, okay, last year. And then what's next? A lot of the stuff that John talked about today is what's next. They're working on tooling to help identify problems with applications and that type of stuff. Let's see, in terms of security, there's a steady stream, constant stream of patches and fixes to handle security issues in the kernel. New proposal to use hashing instead of signing for secure module loading. If you can't immediately think of some issues with that, then you haven't done this work before, but I encourage you to read that article. There was a good status talk talking about a lot of security now is coming from the tooling again. And this was a good comparison of which tools supported what types of security operations or security analysis or defenses, and the status of them. And so you can see some things are green, some things are red, some things are yellow. So there's a lot of work in progress on the tooling for security. We've revived the Automated Testing Summit. There'll be one in Denver this year. If you're interested in that, the CFP closes on Monday. I'm going really fast now. Let's see. I really enjoyed the Perfetto talk today. And if you want even more Perfetto stuff, there was a good talk also by Anna-Lena Marks and Stefan Lengfeld at ELC Europe. So, and let's see, Yocto project. We just had Walnutscar, a new Yocto project minor release come out just like a couple weeks ago, maybe 1 week ago. You can look at the status of that. And I think there's actually a lightning talk talking a little bit about the Yocto project and YP. The one thing I've been following is BitBake Setup, which is a new integrated feature. So we've had CAS for quite a long time, which is a tool to take a single YAML file and pull all your layers in and set you up to do your first build. But they're doing something now that's going to be built into BitBake and Yocto project. And so that's something. It's not upstream yet, but I understand the patches have been put on the mailing list and they're being reviewed. So there's also been a build root release, and I'm going to have to. I got to mention this. So people are even working on tooling for shell scripts to do static analysis to detect bugs in shell scripts, but without executing them. So crazy stuff is going on. Okay. I'm going to go very quickly. Linux Foundation, that was the list of all the projects that are kind of embedded related or embedded adjacent. One of the big ones is AGL. They had a release in February. The one I'm excited about is modeled after AGL called SGL, which is the space-grade Linux work. And this is being done under the umbrella of the ELISA because space grade has a lot of these safety requirements. And we had a meeting at NASA in December, and this is how these projects get started. You get a bunch of people together, a bunch of companies, and pretty soon you have a distro and tooling and stuff for that. Okay, moving right along to miscellaneous stuff. I'm going to skip that first one. There's a new developer support okay, I said I was going to skip it, and then I didn't. Okay, because I wanted to get this one. So AI scraping. AI is interesting, but it's causing lots of problems for open source projects. There's too many AI systems that are scraping OSS projects for their training data. And it's gotten kind of into a serious issue. I think it was one of the projects, I can't remember which one it was, had to actually block the entire country of Brazil in order to save themselves money. 75% of the traffic to readthedocs.io was scrapers. And it was costing them $1,500 a month. And Read the Docs, right, is a free service to the open source community. And that's like real money. The scrapers are not well behaved. Some of them will identify themselves in their browser strings, but a lot of them won't. They'll switch IPs. It's like botnet attacks. So it amounts to a denial of service attack on these sites. And a lot of it is open source sites, right? So that is a big problem. Even our very own LWN.net has been affected by this. They had an article talking about, they've tried all kinds of solutions, robots.txt, throttling, tar pits. They don't want to add like JavaScript and gatekeeping. That's what Lore had to do. I don't know if you noticed, but there's now a human detector on Lore. And so it's not just scraping that is causing kind of internet bandwidth problems, but also you're seeing a lot of fake content. So Stack Overflow had to adopt some policies to restrict AI submissions. Curl has been flooded with a ton of invalid, just bogus AI-generated bug reports. And so it's having a real impact. Unfortunately, I don't have a solution. I mean, I'm hoping that the Linux Foundation will step in and maybe do some support. The Linux Foundation is kind of like the IT department for a lot of open source projects. Okay, so changing subjects completely. Ubuntu is changing to some Rust-based utilities for core utilities. And that is very interesting. There was a lot of angst because they're moving from a GPL license to MIT license. But I don't think most people care. I don't know. There are some people who care a lot about the license of core utils. But it shows you that, again, more and more, Rust is getting adopted, and it's to improve the security through language features, right? So this is just kind of yet another example. Redis went to a business-oriented license, and they had to recant just this month because the community and the industry created a fork called Valkey that was BSD 3 clause. So Redis had to kind of backpedal on that. So I don't know how to put this. I won't comment on that. But I was happy to see them see the light. Okay, and then I'm going to skip over. This stuff is about Intel and stock and this shift to NVIDIA's market cap. NVIDIA has a new ARM-based, a Linux-based ARM AI desktop computer. Okay, so we're seeing AI being developed as a first-class citizen in terms of the feature set for laptops and desktops. And that's pretty interesting. So I really think we're starting to see the age of AI here. Okay, I'm trying to keep myself on track. We'll see. Okay, in terms of community, just a couple little things. Okay, so there was this kerfluffle back in, I think it was October. It was called the removal of the Russian maintainers. It was more complicated than that. There was a patch that removed a bunch of maintainers, and there were complaints that, oh, this wasn't discussed beforehand. It turned out it had been discussed beforehand. There was a lot of speculation about, oh, you know, the kernel's now involved in geopolitics. It was not a removal of Russian nationals because we have anything against individuals, but it was removal of people who worked for specific companies. And the problem is it was a requirement by the US government. And I know that rubs a lot of people the wrong way, but there are geopolitical sanctions that happen. This is because of the Ukraine war, and Russia was sanctioned, and so there were limits to what representatives of Russian companies could do with regard to technology in the US. And so Linus and Greg have to, do you want to say anything? Yeah, that's a really good point. Greg was right in the middle of all this, so he knows. Yeah, U.S. was not the only country that had sanctions on Russia, and we did as well as we could to abide by all of the regulations of everywhere that Linux is developed and used. And I have to say the Linux Foundation did a lot of legwork here that I don't think a lot of people appreciate. You know, the Linux Foundation is the kind of the legal department of the kernel, and it's a legal department that no one here, except for maybe Greg, talks to very often. And so there's actually, they put out a really good kind of description of everything that happened, the timeline and the reasons for everything on Phoronix. And so if you want to look that up, you can. There was also, there was one of the first code of conduct penalties I've seen in quite some time in November. So there was a maintainer, there was some issues, there were some email exchanges that were not very friendly. The penalty, we see a lot. So most people don't realize there is a code of conduct committee operating behind the scenes that, that takes care of trying to safeguard our working environment, right, to make sure that it's not hostile. And the developer apologized. It was a relatively minor, I thought, penalty. He was banned for one release, so he wasn't ejected from the community, wasn't removed from mailing lists, and he apologized, and he's now an active developer. So I just want people to remember that there are all these kind of processes outside the technical sphere that are going on, and making, I think, the community and the development process a better experience. Okay, so I'm gonna keep plowing through really fast. But I'm going to skip a lot of this. Okay, so Embedded Linux Conference is coming up in Denver in the US and in Amsterdam in August. And so we experimented with something this year. It turned out not to be such a great idea. We had a single CFP for both events because they were so close together. And I know having them close together was a bad idea, and I apologize for that. Anyway, it is what it is. Later in the year, we've got Open Source Summit Japan, Linux Plumbers Conference. Both events, obviously, in Tokyo, and so that should be a really good event. I'll just keep going. Okay, with the eLinux Wiki, where we've got a lot of embedded Linux information, the OSU OSL just recently announced that they're running a little bit low on funding. There's a crowdfunding site for donations. Okay, conclusions. Okay, so this is I want to make sure we have enough time for eating some stuff, but just a couple little wrap up things. So what are the themes? And I want to talk a little bit about where we came from. So one of the themes is AI is upon us, and it's bringing a whole host of challenges. So we got the traffic challenges. We have hallucination challenges. We have license and provenance challenges. That was not on my bingo card for this decade. I didn't think AI has. I mean, it's been like only 3 years, but that is really like kind of churned in. And it also, my question is, okay, so where's the AI directory in the kernel tree? Because we know we got to have drivers for this stuff. And we have to deal with it as a computer science technology, right? As something the kernel has to deal with as well. So AI is going to bring a lot of churn in a lot of different ways. The other thing is use of tools, compiler features, automation. So we see this feedback-directed optimization, the thread annotations, a lot of automated testing. People are putting a lot of effort into kernel CI and other projects. And of course, the rise of Rust, a whole set of language features to address making the kernel better just kind of intrinsically and with less kind of manual labor. And then finally, I think one of the big themes is the community is more mature, professional, and friendly, right? So a lot of stuff happens in the background that we sometimes don't acknowledge or appreciate. We have an active code of conduct committee. The Linux Foundation acts as, I tried to think of all the things the Linux Foundation does, and a lot of people don't know what they do. I happen to be kind of more deeply involved, but they do legal stuff, they do HR stuff, they do IT, they do marketing, if you count conferences as kind of marketing. They also do IP. A lot of people don't know how much work the Linux Foundation does to make sure that we're protected from patents and patent trolls. That stuff happens all the time. They're the payroll department. There are some people who are paid and the accounting department, and much, much more. If I was to give this presentation to myself 32 years ago, I would not have believed it. I was involved in a couple of different companies early on: Novell, Caldera, Lineo, and I helped create the Embedded Linux Consortium. And that was mainly a promotion organization because nobody believed in Linux. I was involved in the Consumer Electronics Linux Forum. That involved technical development, and then the Core Embedded Linux project with ecosystem building. So no one in the 90s believed Linux would become anything. Not on desktops, right? We take it for granted that Linux is the #1 operating system in servers, and it's made inroads in desktops. But especially in embedded, nobody believed in Linux. Remember, back in those days, there was no Git, there was no Bitkeeper. Linux was using patches and tarballs, okay? We didn't have lore. There was lkml.org. Remember, this was before Google. We didn't have Google, okay, in those days. There was no methodical release process. There was no code of conduct. There were some communication norms, and things were a little bit rougher back then, but there was no trademark, no legal protection, no patent protection. We only had one tool chain. Compared to that, we're in the golden age of embedded Linux. We really are. We've got so much going on. I know just watching the presentations, there's a lot of work still that needs to be done. But things are really, really great. And I would say they've never been better. So what do I worry about? AI. I already kind of talked about all this. AI is putting stress on open source ecosystems. I don't think it's really good at creating new technology, and there are kind of issues there. So there's some things that AI doesn't do very well, and we have to be kind of careful about that. Maintainers. I always worry about maintainers. Although recently, I've seen a lot more. I was just introduced to a couple of new maintainers, younger maintainers. I hate to say it, but a lot of us are getting older. I have 8 grandchildren, okay? So, and I'm not going to be around forever, right? I have things I want to do with my grandkids that are, don't involve Linux kernel. So we really need to be, getting that new generation of people. And I'm actually heartened. I've seen some good progress there. I do worry also about the tools. All this automation that we're doing, are we going to break the network effects? And I don't have time to talk about everything. There are still some things in the Linux kernel, like boot up time optimization, that take too much manual effort. And so that's kind of what I'm focused on just myself recently. But there are things like that, right? There's stuff that could be easier, that shouldn't be so hard to do. But overall, we're doing great. The kernel core systems, they're all in place to support embedded. And conservatively, we're in 2.5 billion devices, okay? Conservatively. Probably more than that. It gets hard to count because there's so many instances we don't know. But after 32 years, I can't believe we're not done yet. Anyway, so think about what's left to do, what we can do to make things better. And with that, just a quick list of resources. I get a lot of my information from LWN.net, Phoronix, Kernel Newbies. And while we're talking about LWN.net, they are suffering a little bit of a funding crisis. So if you can go out and get yourself a professional subscription, that would be great. And with that, I will say thanks.
Thanks, Tim. We have time for a couple questions. Yeah.
Rather a comment, small comment. Half of the presentation I was thinking, okay, where is AI? Where is AI? And the second half of almost was about AI. And now about AI and open source and commit messages. It's interesting that a colleague of mine noticed that AI is very good to make good commit messages in imperative mode. Basically, you put data and tell, make me imperative mode. So it might be good.
Yeah, well, if AI can intuit what Linus likes in the commit messages, then that's good. My rule is if you can't tell that a human didn't write it, then maybe it's okay. But so for commit messages, we've always had kind of crummy, well, we've had suboptimal commit messages for some of our patches. But like for code, I really worry about code getting into the kernel. So.
Looks like everybody wants coffee, so let's take a break.
Okay, great.
Let's see, what time is it? Let's come back. Yeah, let's come back at past.
Okay.
Thanks.
Thanks,
Stefan. Okay, welcome back. I hope you're refreshed with some coffee. We're gonna switch gears a little bit now and switch to a round of lightning talks. So we'll have several short talks back to back, and then we'll do our final closing game, and then we'll say farewell. So we'll start it off with Martin on a talk about Yocto. So welcome, Martin.
Is this working? Okay, perfect. Good afternoon, everyone. So I'm Martin. I work for Igalia, and here's the thing. So what if I told you that in the Yocto project, that has been a tool that can give you over-the-air updates and seamless updates, and it's been sitting there for a few years, and nobody has touched it, apparently. So yeah, there is, and it's called like systemd sysupdate. And the goal of this talk is basically just to explain what this tool is, and also show how you can use it in the Yocto project. So let's start with sysupdate. So what is it? It's basically a tool that allows you to have atomic updates for different types of resources. It can be files, directories, partitions, and other things. These updates can come from remote or local sources. For example, it can be like a web server through HTTPS, or it can be just a directory. You can have parallel installed version of these resources, like in A, B, C, or whatever like style. And it's relatively small, depending on how you see it. For example, in the demo that I'm going to show, it's like 10 megabytes and roughly like 5% of the original image that didn't have the tool enabled before, right? So, and the most important thing, this is available since systemd 251. So yeah, it's already available in some of the LTS versions of the Yocto project. Optionally, there's other things that this tool can do. It has some built-in services, for example, for regularly checking for updates and even rebooting the system. It has a DBoss interface for applications integration. And there's other like optional things, like, for example, you can group some resources, so you can enable or disable those together, and that's called like features. And because it's part of systemd, this leverages other mechanisms that are already baked in, like, for example, like automatic bus assessment, and takes advantage of things like systemd boot. Before I actually show you how this works with the Yocto project, I'm going to do like a high-level thing. So basically, these are the things you need for like any OS to use sysupdate. You need a way to tell sysupdate what is the current version that you're running. You need a way to version the resources that you want to update. And you need to tell sysupdate what are these resources, right? So I'm going to explain that now. So, and this is a disclaimer. Of course, like, this is just an overly simplified demo. Please do not like take this, put it on a rocket to the moon, and then like tell Greg and Martha that you did your CRA like homework, right? So with that disclaimer, so of course, this demo just starts with a Poke image with a few modifications. For example, it uses like systemd, of course, for the init manager, and systemd boot, because it gives some extra functionalities I'm going to explain. And I'm using a custom image with UKIs, which stands for Unified Kernel Images. There are many good reasons for using Unified Kernel Images, but for the sake of this presentation, I'm just using it to reduce the amount of resources that I have to update, okay? Yeah, you can read more about like what UKIs are about. Yeah, of course, I have my Kickstart file. I basically have two partitions, one for my boot partition, where the UKI file is going to go. And then I have my root fs partition. The only thing special about this is that I already assigned the proper like part types to these partitions according to the discoverable partition specification. So in terms of update, for a full OS update of this, there's basically two resources that I want to update. One is the UKI, and the second one is the rootfs, which well, the UKI is just a file, and the rootfs is a partition. Both are supported by sysupdate, so we can move along. So going back to the thing that I explained before about like the things we need to do. So the first step is basically just adding the image version to OS release. This way, sysupdate can know like what is the current installed or running version. And yeah, you can read more about like exactly what are the formats that are available, and you can use different things to do this, right? The other thing is that you need to version your resources, the resources that you want to update. For example, instead of just having a UKI.EFI file, now I have to name it UFI_image version.EFI, right? So sysupdate knows how to handle this, right? And the other thing that I want to update, my second resource, is actually the whole rootfs. So I'm actually also versioning it by, having the partition name being like _image version. And you will see later like how this can make sense. Okay, so the next thing will be just to enable and configure sysupdate. The first thing is kind of the obvious things. You have to build systemd with sysupdate enable, and for example, you can also enable sysupdate D, which is the debug service. The very important thing here is that you also have to provide something called transfer files. So for every resource that you have to provide a transfer files to tell sysupdate exactly like where the updates are coming from and where that update is going to. One of these per resource that you want to update. So in this case, right, we need one for the rootfs and we need one for the UKI, right? So let's see like what these transfer files look like. For the rootfs, basically a transfer file has 3 sections. The first section is just transfer, which is just general properties about the transfer. In this case, I'm telling to protect the version A, right, the first version. Then we have the source section, where we're basically saying where this update is going to come from. For example, in this case, it's going to be a URL file. So I'm basically putting there the URL of my update server, and I'm giving it some pattern for it to understand like which of the resources that is serving through this web service corresponds to this resource, right? And then the target, which in this case is a partition of type root, and is going to match with the underscore image version, right? That's what the V there is standing for. And I'm only going to have like 2 instances for this, because I'm only interested in an A/B schema, right? The same thing goes for the kernel. Like we have the transfer, we have the source, but for this one, the target is just a regular file, which is going to live like under the boot partition, under the EFI Linux path, and then I have all these different like patterns to identify it. Like the last one is the basic one, but the others are like the ones you could potentially see, like if boot assessment is like running. And of course, I only have like 2 instances of this as well, right? Plus, for my keystart file, I need to add, because I'm going to have like A, B partitions for the rootfs, so I need to add like an extra partition, which has to be exactly the same as the A partition, right? Except that initially, I'm just going to call it underscore like empty, and it's going to be like really empty, right? And of course, like how do we serve these updates? Like I said, it can be just like a web server, and this is like the most simplistic example possible. So we see here the contents. These are the different versions of the rootfs and the different versions of the UKI, and the SHA-256 sums is basically just like some sort of, yeah, it acts as a manifest to tell like what is available to sysupdate. And yeah, then you can serve this with your preferred web server, which in my case, I'm super lazy, and this is just a demo, so I'm just using Python, right? So now comes the boring part, which is showing how this is actually working, right? So I built this image, and I did all the steps that I showed. And let me go here. So, okay, this is the version 0 of my image, right? Like there's no update at all. I'm showing there that the web server is running, and these are the contents of my like server, which only has the version 0 of my rootfs and UKI, right? So here I'm just making sure that I'm actually running the proper image, right? I can see that the image version is just the 0 version, and if I look at the boot partition, I can see that there's only like one UKI, which is the UKI 0 version, okay? So now if I try to update, which is update CTL, is one of the front ends, it's going to tell me, of course, there's no available update. But now I'm going to just cheat because, this is just a presentation, and I already pre-generated some updates, and I'm just going to drop those updates into my server. And now if I check, it detects that it has a new version, which is, of course, called 1. And now I'm going to run the update.ctl update, and it's done. Now, I just need to restart my system, and then we'll see that, system deboot already defaults to the newer version. And we're going to boot that one. And we're just going to make sure that I'm actually running the proper partition and that the UKIs are still there where they should, both versions, right? So yeah, I can see there that I can see already like the image version is 1, and I can see the UKI version 1 as well, but the UKI version 0 is still there, of course. Now again, I'm going to try to check update. There's no update. I'm going to repeat this, and I'm basically just going to add another version 2, no surprise. And I'm going to check. Again, it detects it. I'm going to just update, and I'm going to reboot again and repeat. So now, of course, it defaults to the version 2. There's no version 0 anymore. And just going to make sure that I'm actually running the proper thing. Again, I'm checking the OS release file. I see image version 2, and also I can see the UKI version 2 as well. Now, if I still have time, just going to do one more thing. So what I'm going to do is I'm just going to go back to a previous version and make sure that everything is running as supposed. So I just rebooted. I went back to the version 1. And I'm going to check again the same thing. So I'm running the proper partition. And I can still see that everything is there. But now if I check if there's an update available, of course it's going to say no because, sysupdate understands what's going on, and I just went back to another version, and there is literally a newer version in the server, so there's nothing to do, right? And here I'm just checking, and it detects that the version I'm running now is the protected version according to how I define that in my transfer file. So, of course, I hope I have conveyed like in 10-ish minutes that this is a very simple mechanism to use. But of course has limitations. So sysupdate-wise, something important that it's missing is the delta updates. There's already discussions about like how to implement this, which is basically like a plugin like architecture. So this can be done like in different ways for different scenarios. Like Yocto-wise, well, as I just shown, I mean, you can enable sysupdate, version your resources, like, and do all those other steps. I mean, to me, it doesn't look like much, but of course, I imagine that there will be like better, ways to do this integration. I don't know if in a separate layer or something like that. Yeah, I guess I'm in the right place to ask. So, and demo-wise, like the demo that I show, it's like it uses like UKIs, like system deboot and all of that. So it's like very UEFI firmware dependent. So for if that's not available, then it could be more complicated, of course, right? So yeah. Lastly, yeah, there's some recommended readings about this. There's literally very, very little about this, like at all, not Yocto specific, like just at all. So I mean, so I recommend reading like these 2 articles because they are really good at explaining like, I mean, how this works and like different ways of integrating sysupdate and working with it. But I'm hoping to make this presentation a proper blog and actually release the demo sources so anyone can actually have like a running version as a sort of starting point or reference. And with that, thank you for your attention. And if you have questions, I'll be here, or you can send me an email. So thank you.
So I forgot to mention for the lightning talks, we're going to go quickly, so we don't really have time for questions. We're just going to talk after talk. So thank you, Martin. Tim got us started in going increasing the speed, so we're going to keep the speed up. It helps keep you all awake on the last day.
Okay, 1 second. Okay, mirror displays works. I tried this morning, it should work. Start presentation, it should be it. Does it work?
Okay, welcome Valerio, and here we go.
Hello everybody, good afternoon. My name is Valerio Setti, and today I'm going to present you another talk about security, but in this case is Zephyr and its security cryptographic features. Starting from a short introduction, I work for Libre. I know you know the company by now, but in case not, this is an open source consultancy company based a few kilometers from here, so in the Nice area, which is specialized in all the things related to embedded devices, so Linux kernel, Yocto, U-boot, Zephyr, of course, and more recently also the C compiler and toolchains. I joined the company in 2022, and since then I have been contributing mostly to MBTLS, but also Zephyr, so that now I am part of the Zephyr Security Working Group Committee and the Zephyr TSC. When we talk about real constrained embedded devices, so like microcontrollers, I'm sure you know that there are several options available on the market, open source ones. Here I just listed a few of them. The laser pointer is not that great. And Zephyr is among these, and it's owned by the Linux Foundation. Speaking of growth of the project, as shown by this graph, you can see that in the last decade, so since the project's beginning, it has been continuously growing in terms of commits per year, as well as unique contributors. This brings us to the current state where you basically can find support for most, if not all, the available 32 and 64 bits platform on the market, and more than 700 boards, which makes it extremely easy to start playing with that. So if you haven't tried it yet, I strongly suggest to give it a try because it's super easy. There are some products at least already on the market using Zephyr. I just left the link here in case you're curious. The reason for the success of this OS is that it's not only brings you a full feature kernel, which you might have, for example, also with FreeRTOS, just to make an example, but it also comes with a high number of subsystem and modules that brings you a lot of functionality directly out of the box. And crypto is, of course, one of these. The development workflow is, I would say, pretty close to what you would have with an embedded Linux board. So for all the module and subsystems that I mentioned before, but also for the kernel, you can configure and enable, disable single things using a kconfig file. Then you'll have your device tree to describe your hardware. So the end developer only really need to think on developing his own app. The build system is a bit different compared to the Linux kernel because it's a CMake based, and there is a bit of Python scripting. The reason for that is that it performs some checks, but it also automatically generate some source files which are included into the build. The reason for this is that we're talking about really constrained devices. So everything, like the device tree, has to be resolved at build time, not runtime. Having such powerful real-time OS means that IoT is a great application for it. But when we talk about IoT, security is an important feature. So I'll go through some of the subsystems which are requiring crypto support. So you'll find support, for example, for Bluetooth Low Energy, Wi-Fi, and more recently also IoT-specific protocols such as Thread, supported by OpenThread project, and Matter, which require you to support cryptographic, to have cryptographic support somehow in order to have key exchanges, authentication, data encryption, etc. You will also find TLS socket. Doesn't matter if it's wireless or wired, you can have it. And in this case, you also have to handle certificates and again, key exchanges, encryption, decryption, because you would like to connect to a server or you want your device to act like a server. You'll have JWT, JSON Web Token, for client authentication. Or you can also require crypto support for hardening your device. For example, you might want a real random number generator able to generate a large amount of random data. Reason might be you want your device to really behave in a non-predictable way. Usually devices, now, microcontrollers nowadays comes with some sort of hardware random generator, but it only can provide you a limited amount of data per unit of time. So in case you want to generate larger buffer, that's not good. So you can apply cryptographic magic on top of that to get a larger buffer and use the hardware thing as a seed for that. You will also find a bootloader, which is MCU boot in case of Zephyr, which is used to verify. Actually, it can also decrypt, but for microcontroller, most of the time it's just verify the signatures of the following images before just jumping into them. This clearly is interesting in case you're looking for OTA update, which is possible in Zephyr. You will find secure storage. We saw that there's protocol requirement, TLS, etc., that have sensible material like credentials that needs to be stored somewhere securely, also at rest. And that's where secure storage comes into play. You will also find some remote management tool which have some flash feature, like to verify that the integrity of your flash or part of it is still okay using hash algorithm. Well, all of these means that there is some requirement for a crypto provider, right? So first thing first, speaking of interface for this crypto support, the project recently moved toward the adoption of a unified and a single interface for that, named PSA Crypto APIs, where PSA stands for Platform Security Architecture. This is a standard who has been designed by ARM. Actually, the standard defines more than just crypto. It also defines secure storage, attestation, and firmware updates, for example. So what about in practice? Who provides crypto support in Zephyr? Well, nowadays you basically have two options depending on the hardware you're running on. You can either go full software with embedded-TLS or rely on trusted firmware. In the first case, as I said, you're relying on embedded-TLS to provide you everything because embedded-TLS is a full TLS stack library able to provide higher layers with TLS X509 for certificates, as well as the crypto support for that. Just a small notice that crypto support can be provided in two flavors, PSA interface, of course, as well as the legacy ones, which, by the way, is under the process of being removed. Application has some bug that can be exploited to retrieve some data on the RAM. The attacker can just dump part of it, including the credentials, which is not great. And data by default is not securely stored at rest. It's up to the end developer to do that. For this reason, secure storage, as we saw before, has been introduced in Zephyr to overcome this limitation. This brings us to the second solution, which is the most secure one. And it's the one based on trusted firmware RAM. To be noted that this is only available on CPU implementing the ARM v8 or 8.1 architectures, which, as you know, they implement the ARM trust zone. In case you don't know, the trust zone introduces a new state for the CPUs so that we are not just dealing with execution privileges, so secure or, privileged or unprivileged, but we are also introducing an orthogonal configuration, like you can also jump from secure to non-secure. Of course, the Zephyr application will be, in blue here, on the non-secure side. And whenever it needs to perform any cryptographic operations, it calls into the secure side, where TFM is. And here, there is the transition from non-secure to secure. Some magic is done here to provide the result for the cryptographic operation, and the result is returned back to the non-secure side. On the TFM side, embedded TLS is still used under the hood, the crypto part, of course, the lower layers, to provide the cryptographic support for that. But the asterisk here highlights the fact that it's not the stock version of embedded TLS, because TFM team applies a few patches on top of it to add support for some hardware accelerators, especially the harm ones, like the crypto cells. The other block here, it's meant to highlight that the fact that TFM does not only implement crypto, but it implements the full feature, the full PSA API interface. So you also have secure storage, attestation, firmware update, and status. And speaking about the future work, on the Zephyr side, we'll continue the transition, which has almost been completed toward the adoption of PSA crypto API as a single interface for crypto operations. And we'll continue working on refactoring and improving the integration of embedded TLS inside Zephyr. Whereas on the embedded TLS project, there is a major release expected by September this year, where there's going to be, among other things, a repository split, so splitting the higher layers, TLS and X509, compared to the crypto ones. And on the latter, there will be a removal, as I mentioned before, of the legacy crypto interface. After that release, we'll likely also focus on the support for hardware accelerators, somehow out of the box. I don't think there's anything defined clearly yet. But it will help in both scenarios, both in TFM, because you can take advantage of that, of your hardware accelerator, but also in case you're just relying on embedded TLS as a single library. It won't be the best secure, maybe, but at least you can speed up computations. Yeah, that's it. Thank you for your attention.
C'est moins J, oui. C'est bien. Ok. Ah, il faut que je... All right. Okay. Okay, hello everyone. So this talk now about the Yocto project, which I'm going to give, I need to be very fast apparently, I have 15 minutes. So let's just jump straight into it. I'm going to talk about the recent changes and the future directions of the Yocto project. I'm at least going to try to summarize it. The reason for that is that I am currently the maintainer of the documentation for the Yocto project. So I just see things moving in the project. I try to document them. I try to keep the docs up to date. And so the idea of this talk is just to give you, not everything, of course, because there's lots of bug fixes. We don't really care about that. Let's just talk about the new features, the cool stuff, at least what I think is cool, right? And yeah, so let's just, I'm just going to throw stuff at you. No real order. Let's just go straight in. So let's take a look at the release cycle first, just to see where we're at right now. So last week, Walnut was released, the 5.2 release here. And I guess most people right now are using ScartGap, right? So my idea was just to cover these 3 releases because I only have a limited time. And as you can see up there, there are 2 new releases coming up, which are feature releases. And especially the last one here is the LTS release. So Also a small note that Kirkstone users should maybe start worrying and maybe update, but just an idea. And so the first thing I'm going to talk about is something really simple, but I think is a nice quality of life improvement. It's just a variable called user add depends, and lots of times when you're doing Yocto, you want to define new users on your target, and it's kind of a mess sometimes to just manage everything within your recipes. And this variable here is quite nice because it just allows you to define some dependencies between your recipes and avoid recreating everything all the time. So let's just take an example. Here we have the first recipe here, which is creating a group called my group. And quite simply, what you just need to do here in another recipe is just make a dependency on the first one and reuse the group in the second recipe. So in that case, I didn't have to recreate everything with the group add param variable. So really simple. You can be creative, I believe, within your recipes to use that. But yeah, I think this was introduced in ScartCap, so it's a bit old, but I think it's really nice. Another thing that was introduced in ScartCap is a new DevTool command, which is not so popular, I believe. It's a really complex command, which is should be an alternative to populate SDK, which is allowing to generate SDKs. The idea is to create an SDK and a remote debugging and cross-development environment for any application. So if you are doing application development, this will be useful to you. Basically, there are 3 steps to set it up. First step are top-level configurations. I'm not going to detail them here, but there is a link in the slide. Then you want to modify the recipe with DevTool. So if you know DevTool already, this will just extract the sources in a directory. The last step here is to call the IDE SDK command. This will, combined with an image recipe, create a remote debugging configuration automatically, depending on the framework used by the recipe. So it must be supported, but if it's a CMake or Mason recipe, it should work. And so what this is going to do is create new configuration files within the source, which you can, by default, use with VS Code, I think. And so if you are an application developer, this will be quite useful, I believe. Or if you are not, but you want to give that to someone, that can also be quite useful. So there is documentation over there if you want to dig more. It's quite extensive and good, so I recommend it. Next thing is a big change in StyHead. So previously, a lot of recipes were doing this because they wanted to unpack sources directly within the work directory. This is not possible anymore because I think the reason is simple. It's just we don't want to extract everything within a directory that contains other things that are unrelated to sources. So this is not possible anymore. This will produce an error. And the simple way to fix it is to use another variable called unpackDir. So the recommended way of setting S and unpackDir is this one. Don't ask me why. This is the way. And so the sources will be extracted in a directory called sources. It will be cleanly separated. I think that's the idea. And then if you need to install files directly from the source on your target, basically you can use the unpackDir variable. I think this is the cleanest way of doing it. And this appeared in StyHead. Right, so small change, but impactful. Next is a bit about fragments and configuration, so top-level configuration. So there is a new concept within the Yocto project called configuration fragments that was introduced actually recently. I think it was by Alex, which is over there, right? So the idea is to abstract some set of configuration, and I've taken an excerpt from the auto builder configuration, which is kind of the CI/CD of Yocto. And so what this does here is just setting some limitations and resources constraints here in a single file, right? And then what you need to do is provide a description and a summary. You need to call add fragments. And so the syntax is detailed a bit more in the documentation. I don't really have time to explain everything. And then at the end, you want to add the fragments that you want in a variable here. And what this will do is simply just take these configurations into account and apply them for your build. And actually, it's, I think, a building block for a bit-baked setup, which is not yet merged into master, but there is some talk about it tomorrow in the OE workshop, so maybe you will get familiar with it if you are participating. There is currently a limited documentation about it, about all of this. I need to work a bit more about this. I need to dig into it. I think it's interesting. It will allow, I think, much more modular configurations overall, and avoid, spreading or gathering everything into a single file. So that is nice. Kind of related to configurations is the include all directive. So this is new. The idea is that you may have a file in multiple layers, like in this configuration here. We have a maintainers.inc. Actually, this is a real use case within the Octo project. So the file is named the same in different layers, not necessarily the same path. And so the idea is really simple, and it's really simple to use. You can just call include all in another file. It will just go over all of the layers that are listed in BB layers, the variable, and it will just simply include the file. So you can be creative with that. I just put a real use case that probably lists maintainer for different layers, but if you have multiple layers, I guess you can also include some kind of information to say, hey, my layer is there, whatever. I think you can be creative, but that's nice. It's a small convenience thing that wasn't possible before, actually. That's a new variable, which is also quite recent, and I think it's really nice. There's no reason to not use it. I think it's just allowing to compress the firmwares that you install on your target, if you have any. So it's a single variable called firmware compression. By default, it is empty, so no compression is done at all. You can pass either XZ or ZST to this variable, and what this will do is just compress the variables to install on your target, right? You just need your kernel to be configured with either one config or the other here, and the kernel will take care of just decompressing the firmware before loading it. And I did a test on my setup here. I just installed every firmware that was available at the time where I was testing this, but it was around 1.5 gigs. And as you can see, it saves 1 gig for XZ, maybe 700 gigs for ZSTD. Really significant and basically free because you don't have to do a lot to configure this. So I just encourage you to use it. It will save some space on your device. It is always nice. Right, another interesting change that is very recent is the removal of something called debug tweaks. So it's an image feature, which is usually put inside this variable that you can see there. It was an abstraction of several other features. It wasn't really nice for a security, from a security point of view, because it just, you can forget about what it is really doing. So it was removed, and now it will just simply not do anything, I believe. What you need to do is simple. You just need to explicitly list the features that you want to enable. And this is really what it did before. You don't necessarily need all of them, but yeah, I think it's worth mentioning here to keep you updated when you will be updating your Yocto distribution. Something I wanted to talk about, which is interesting, is related to the kernel. So the kernel LTSs are now 2-year. It used to be more. I don't remember what the exact number was, but it switched to 2-year, which is smaller than the lifespan of the Yocto project LTSs. So there's no real solution to this. I mean, there is one, which is quite simple. The default kernel that is present in the Yocto LTS will at some point, actually at the midpoint of the LTS, be updated to the currently available LTS kernel. So, and the previous one will be left but not updated, obviously. So yeah, this is, I think, pretty impactful, especially if you are using the Linux Yocto recipe directly. There is a discussion thread and just a reasoning behind it in details at this link if you want to take a look. Another thing that is new, and it has been introduced in StyHead, is SPDX3. So there has been already talks about security during embedded recipes. There was even talk about SPDX, and out of the many things it can do, I'm not an SPDX expert, but it can manage vulnerabilities. And so there is a little example here which associates a package and a CVE. This is an extract from a very good presentation by Joshua. I put some links in there if you want to dig more into it. But this will come in the next LTS and is already available, still under development. There is lots of things going on with this. So it's really important, I think, nowadays to have that. And it leads me into another topic, which is the future of CV checking within Yocto. So currently we have a class to monitor CVEs, which is called CVE check. And it relies on the NVD. And if you don't know already, there was kind of a lag with the NVD, starting in the beginning of 2024. And they just stopped associating CPEs to existing CVEs. So the CPE is just allowing to identify a software component and associate it with the CVE. So what this means, I think the bottom line is that the CVE reports that we have right now within the Yocto project look good, but are missing some known vulnerabilities that just don't have any CPE to match. So it's just not really possible to track this automatically. So I would really like to give you a solution. I don't have one, and actually there's nobody that really has a solution for now. There has been a talk about it. Yes, and I think that's one of the ways everyone's going to become a CNA, right? Okay.
Can you repeat what Greg said?
Can you repeat what you said?
The kernel's now issuing those directly and feeding them directly, so you don't have to rely on NVD anymore.
Oh yeah, right. Oh, last week, okay. So now the kernel is releasing the CVEs and you don't have to rely on NVD, and they already have the CPE, of course, because it's only the kernel, right? So out of this, something that is relied to SPDX is that it may rely on SPDX. The new way of tracking CVEs within Yocto may rely on SPDX3 since it has that vulnerability tracking feature. To be fair, right now it's under discussion. There needs to be prototypes to be written. There is a beginning of the discussion and actually a huge email by Ross Barton at this link, which gives the context and future maybe decisions to be taken. So just under development, I would say, under discussion. We will see what the future brings, but for now, that's the state. Right, the last item I wanted to talk about is something that is really fresh. It was actually sent maybe like 3 weeks ago, is support for CLang within the Yocto project as a default compiler. And so there was a patch series sent by Raj, which is doing the work for that. So maybe in the future, maybe the next release, I think that's the goal, is to have CLang to be selected as a default compiler and toolchain provider. Right. It will not override GCC. Good point. It will not override GCC. It will simply be an optional thing that you can take. It will be tested and yeah. It will be tested by the auto builder team, which is over there. Right. So that's interesting. Still work in progress, but in the future we may have this. Last thing, I didn't have time to talk about everything. Those are some more links and hints to new things. Of course, there are the release notes that try to detail everything that is going on within the project. And yeah, I would just really encourage you to take a look at them. And that's all. Thank you.
Yocto hijacking one sentence. We will informally gather after Tim's hopefully very entertaining show outside. If you feel like connected to Yocto or just want to heckle us, we will be there and then find something to do this evening. That's it.
Do you want to plug the workshop for tomorrow? Is there still room in the workshop for tomorrow?
Kevin says I should point out the workshop that we have tomorrow. I actually don't know if we have room because Bay Libre is running the registrations.
Well, you can try to register if you want, I guess. I don't know how many room, if there's any room left.
Yeah, actually we have a bit of room. We have maybe 5 to 10 seats for someone who wants to attend tomorrow. It will be at the Sheraton, 5 minutes walking from here. So yeah.
There's also a LabCrit workshop, and we have still room left. So if you want to register and you are here tomorrow, please do.
That worked like a charm. Okay, one more announcement before we start. During this talk, we're going to be passing out some green and red papers. It's for the closing game that'll happen right after this. So we'll be going up and down giving you paper, but that's why. Okay, take it away, Wolfram, our last talk for the day.
Yeah, I really hope it's last and not least. So, my name is Wolfram. I'm the current I2C maintainer and a consultant, mainly working for Renesas Electronics. And I'm talking about I3C today. Being an I2C maintainer does not make me automatically an I3C expert, so I had to learn like everyone of you probably else had if you start with that topic. And the reason was because Renesas developed an I3C controller, and my task is to upstream the driver for it. And so I got started. This is not the right key. Let's not my laptop. Help. Okay, kind of works. So why is there I3C over I2C? So these are marketing slides from NXP. I took the liberty to copy them. Two selling points, especially for hardware makers, is like for I2C, we have these data and clock lines. It's promised to be a 2-wire bus, but if you want to have an interrupt, you need to have an extra line per device. And some people said, hey, we have been promised a 2-wire bus, and this is what I3C offers. You really have 2 wires and a lot of features. Also, the bus rate, of course, has been improved from 400. 1 megahertz is pretty usual at I2C. 3.4, not so much. They go up to 12.4 megahertz, and depending if you have single or double data rate, it can be really fast, in theory. Sorry, here, it's old slides, so we're still talking about master slaves. The documentation has been reworded to use a more inclusive language controller and target, which I think is a very good move. And here are some more advantages from I3C over I2C. So you still have interrupts, but there are no in-band. And you can have hot join support. A lot of people want to hot plug I2C and have lots of problems with that. A lot of things. We don't need to go into details. You see that it offers a lot of new features, but that also makes it more complex, right? And they, on this I2C side, they write that it's a simple implementation, where was another, somewhere was another simple relationships. I don't know if they mean this simple here is an insult to shine with I3C, but we'll see about this later. So this was all introduced in law 2017, 2008-ish, so around that area. So what happened on the controller side? Since then, we have seen 6 controllers being upstreamed, which I think is okay. I don't want to see 100. It's complex, right? And especially the Designware and the MIPI one, they're like Cores you can buy and you can add your platform stuff to it, but the core will stay the same, so we don't have to maintain quite a lot of software. So I think this is a design where, if you think Intel and AMD, they will use these designware cores, and here the embedded people are, well, they often have to do their own stuff. So I think this is kind of okay. But we don't, the key features of course, not the controllers, but the devices we want to talk to. So let's see how many devices have been upstreamed. Yeah. And I'm going to marketing mode now. It has been a slow start, but since a few kernel versions, it's a pity that I don't have, oh, Kevin, your laptop is on battery low. I should have taken mine. Okay, but since a few kernel releases, you really see a huge boost in i3C target drivers, right? So everything is good. But if you see that, if I take out the smoothness of the graphs, you probably get the idea, if I add the numbering on the Y scale, is that things don't really look so good. I mean, it's 4 drivers in, what, 8 years? So, and the last 2 are temperature drivers, and this one, basically the last slope is me, because I wanted, for my device, things to be upstream. Yeah, that's an idea how the adoption went. And so, oops,
on-the-fly hacking.
Yeah, thanks for doing this. So I wondered about this because converting an I2C, an existing I2C driver to I3C is not hard. The maintainers of I3C maintainers made a lot of things right. So the documentation is there. There's even RegMap support. So if you're in an existing I2C support, adding I3C is basically a no-brainer, and still not a lot of people did it. So whenever I talk about things here, this is really no bashing of the I3C subsystem itself. It's just to get an idea how the adoption is, where the problem is, and it's all about this. It's just I'm observing the situation. And there is one basic problem is there's really not much hardware out there. I had the Professor Renaissance gave me this controller and I needed to talk to some device. And then I really spent the first time of this talk just researching. There are not a lot of chips supporting I3C and even fewer boards I could buy like off the shelf to connect it to my controller. And well, this is like industry backed up, so 100 euros or dollars wouldn't be out of the reach, but still for a temperature sensor, I think this is not very hackable. And then you still get basic support. I mean, the temperature sensors have in-band interrupts, but I haven't found HDR, high data rate capable devices, nor hot join capable devices. If you do, please let me know. So far, I haven't found. It's not so bad. My hardware doesn't support that. But
Can RISC-V help you?
It always can, right? So here's my solution. I found this board from NXP. It has here a temperature sensor. If you buy it from distributors, it costs $100. If you buy it from NXP, it costs $16.50. I was lucky there. And so I had one i3C device, which was already good. But then I checked schematics and found out that they have the same baseboard for 2 different temperature sensors, and they're selling either this or that. So I got the other temperature sensor as plain sensor as a free sample and got someone to solder it here. So I have 2 I3C devices now on one board. This is state of the art. And then it has this nice connector. So this is just power and ground. I can connect it back to the baseboard. And then I can connect the legacy I2C board to that bus. So I can simulate a pure I3C bus or a mixed I3C I2 bus. So I was kind of happy. It cannot let me test everything, but actually quite a lot given the money I have invested in that. And it felt me like hacking on things. Let me see. This is the board. It's still available. If you need it, buy it now. Maybe they found out that it's too cheap. I have no idea. I added the sensor, target. Oh yeah, both targets are supported upstream, so this board can test 50% of all Linux i3C drivers. Interrupts are possible. I haven't tested that yet. And what's also nice, it can handle different I/O depending on what your controller delivers. But then the next thing comes, okay, I have a connection, I can somehow talk. Now I want to check the corner cases. I want to debug it. I want to analyze the data. So, okay, USB to I3C adapter, how much can that be? Yeah, 1,500 to 2,000 euros. You get a protocol analyzer to it. Okay, this is nice, but this was really out of the range. And luckily, there is a hacking scene. And I really want to mention the GitHub user Xyfro, who is opening up the i3C world to us hackers. One thing he did is he wrote an i3C analyzer plugin for the Salea Logic 2 software. And it worked pretty well for my cases. Source is there. He was so hackish that he forgot to put it under some license, so I can tell you that you can please try it out, but please be careful with distributing it until this issue is solved. And if you're bored, please port this C++ analyzer to Python in for SIGROC. Then it would be all easier to access because, well, no, for me at least. Because I have a 100 megahertz analyzer for SIGROC, but not for this software. Okay, I do have an i3C controller, but if you want to double check how is your controller working compared to other controllers, and you want I'll buy a second one, you run into the same problem. i3C controllers are mostly available on newer SoCs, like think IMX8, IMX9. The boards are expensive and they're not even exposed. Sometimes the SoCs have the support, but they are not exposed on boards. So if you're lucky, you can do some strange pin muxing to get the signals out. Otherwise, so it's really, really difficult. MCUs, if you don't think out of the box, don't think Linux, MCUs often claim to have i3C support. That often means target support. They're not controllers. They can act as a target. Renesas has a board for like 80 euros, which has an MCU with i3C controller support, which is nice. It is well supported in Zephyr, except i3C. Here we are again. The complexity of the software side is really, really hindering, I think. So now our Xyfro user to the rescue again. He took a Raspberry Pi Pico and basically made a bit-banked i3C controller. And if you add a level shifter, he has a custom one, which is pretty awesome. I bought one off the shelf. I have to try it. I didn't have time to do this now. You end up with $10 or 10 euros, roughly. And this opens, this time he added a license. It's MIT licensed. It's the only controller I know which can do high data rate HDR DDR transmissions. So he really, really put some effort in it. And I'm actually looking forward to try it out and help him with his project, see how to report him my findings. So this guy is really a true hacker in the hacking sense. So Mikkel, are you here? Here you are, yeah. You probably recognize the slide. I stole it from you. It's the status of the i3C in Linux from late 2021. Hardware, and I can basically copy it. Hardware manufacturers are more and more interested. This is still true, but we're coming from a very low level. 3 controllers upstream, we're now to 6. Okay. 1 driver upstream, we're now up to 4. But the command that it's not leveraging the full power is still true. There's 1 driver using in-band interrupts and the rest is still not used. And this ongoing controller handwork, that was the patch series which is described here, is still the latest patch series of that. It has never gone further ever since. Again, no bashing. There are reasons for that. And I think this whole list of room for improvement is still open. I know that the dev interface has out of 3 patches. I don't know, is HDR supported meanwhile? Yeah, it is? Okay, cool. We can take one off the list. HDR is supported meanwhile. But there's no target interface. Pardon? There are patches for the target interface. Awesome. Yeah, but there's still room for improvement. My BSP has patches for like power management, suspend, resume. There seem to be issues as well, which I have not seen covered in other drivers. So yeah, that's still where we are. So my conclusions about i3C are, well, as reading from the spec, it's obvious the complexity is shifted from hardware to software. You don't need muxes anymore. You don't need separate interrupt lines anymore. But at least in Linux, the software has not caught up yet. And the progress, the whole thing, i3C feels like slowly moving. It doesn't really, nobody's really crazy about it, trying to get like new touchpads into the laptops which talk i3C, at least not for the last 8 years. But it will be used, that's my impression, because it's MIPI, and MIPI took effort to get it into standards like DDR5 and PCI Express, at least. So there will be some users. And this is why I focus on this make it hackable. But I don't know what the future of i3C is, but I think the first step for us is to make it hackable. So either we can improve and add the features, or if we get devices which use i3C, we can at least try to understand how they work. Otherwise you get this i3C thing and you can't figure out what is it. And yeah, so I'm not afraid that I2C will disappear soon. I think it will be around just because of its simplicity. I3C, we will see. But I repeat myself, the first thing is to get access to it, make it hackable. And this is why I gave this talk, to show you my approach, to show you if you need a device, go there. If you need a protocol analyzer, go there. If you need a controller, go there. And then we can start from there, or not. We will see. Thank you.
Closing game. Does everybody have a piece of red and a piece of green paper now? Oh, you guys need green. Okay, I'll bring you some green. Green too.
Let me see here. That didn't go. There we go. There we go. So I always start the closing game with a few vacation pictures. Maybe you guys have been to this spot. This is on Tuesday, and you should really check out this place. No, okay, so that's just me goofing around. We're going to do closing games and surprises. This is something I've done for Embedded Linux Conference for many years, and this is a crowd that I've seen a lot of you before. Anyway, we like skill and games of both skill and luck, so-called. And the way that this game works, if you're not familiar with, I call the first one of this the red-green game. You have two cards in your hand, a red card and a green card. The answers will be either red or green, or sometimes both. Okay, and you'll see the options. So it's basically a multiple choice game. And so what we're going to do is we're going to have everybody stand up. So go ahead and stand on up. This is an exercise game. You've been sitting a long time. And what we'll do is we'll do a round. If you get the question wrong, you sit down. And then as soon as we have as soon as we have less contestants than we have prizes, we'll have those people come up and get your prize. And the way the prizes, sometimes we have you draw or anything. This is strictly first come, first served. Oh, and I should say, yeah, it's, so the prizes is stuff. This is technical and nerd trivia. The most important thing about this game is it is not fair. Okay, so I don't want to hear any whining about I do want to shout out one prize here. We've got a Qualcomm board, very generously donated. I think that's the most expensive thing we've got. So this runs Linux. Woo! So thank you, Qualcomm, for that.
And some of the other prizes we have are also some embedded boards that were given out at previous events. So those are some boards from Libertech that are Amlogic based or Allwinner based. So we have a handful of those as well. And then we have a large bag of candy. So if you think you should have won because the game's not fair, you can have a piece of candy.
Okay. So let's get right into it. Okay, this is a warm-up question. You will not get eliminated if you get this wrong. What is going on here? Oh wait, oops. See, this happens every time I do a game. Yeah, what's the answer to this one? What is the latest released kernel version available from Linus Torvalds? Is it green 6.15 RC7 or red 6.14.6? Okay, this one I gave it away, right? It's 6.14.6. Okay, so that's a released kernel. A release candidate is not a release. Okay, it's actually in their name. That's what the RC stands for. And I don't know if you noticed, but RC7 doesn't exist. We're on RC6 this week. So anyway, so that's the type of shenanigans you can expect from my questions. This is a France question coming up. So everyone who's from France should know this like the back of their hand. The Minitel service provided the residents of France access to information and the ability to purchase items beginning in the early 1980s, much like the World Wide Web does today. But when was the Minitel required? I guess with the World Wide Web, you don't need... Okay, and so go ahead and raise your things. From now on, after this round, I'm going to hold your things down because we have a lot of people during this game who kind of look at their neighbors. And so at the end of my reading the question, I'll say, I'll tell you when to raise your cards. If you said red, you were correct. Okay, that was after. So if you're green, please sit down. Okay, so let's see. Here's one that's an interesting one. Linux has landed on Mars, but not on the moon. Is that true or false? Think about that for a sec. Okay, answers up. True or false? Linux has landed on Mars, but not on the moon. And the answer is, that is true. Okay, oh, wow, okay. Sony had a lunar rover that was on the moon just a year ago. It was NutX. I'm sorry. It was too small. It only had 2 mega RAM. They asked me if I could get Linux on it, and I said, nah, not in this decade. But yeah, so Linux has never been on the moon. It's been around the moon. It's flown a couple of NASA missions and satellites and stuff. Speaking of planets, on what planet does Rey from Star Wars grow up? Is it Tatooine or Jakku? Okay, answers up. You gotta make your choice. The correct answer is Jakku. Okay, so if you were green, sit down. How are we doing? Oh, we got way too many people still. Tatooine was where Anakin and Luke Skywalker were raised. Luke Skywalker was raised on Tatooine. Okay, this one's interesting. The youngest person to have a patch accepted to the Linux kernel was how old? Were they younger than 7 or older than 7 years old? What's the youngest kernel developer? And, okay, everybody up who's still standing? Okay, the answer is they were 4. So, if you've never gotten a patch in the kernel, I got bad news for you. You're behind a 4-year-old. How are we doing on people? We got about, okay, one more round. Okay, oh, okay, this is an easy one. Okay, and this will teach you a lesson. Never come to one of my sessions with the kernel not in your page cache, because I timed this. It takes a lot longer if you have a cold cache. You don't have the kernel to do this grep. It's an easy grep to do, but is the answer, okay, how many files in the 6.15 RC6 kernel have SPDX license ID headers? Okay, it's not all of them, but is it 56,000 or 73,000? You got to pick. This is one of those, you just got to take a guess. If you, like me, are interested in this topic, yeah, you would know that it's actually pretty good. We're at 73,000. Okay, so how are we doing? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Should we go? We'll do one more question. Oh, and this one's not bad. The very first stored program machine was a loom that used punched wooden cards to automatically weave fabric designs. Was this machine invented in France? This machine was invented in France. True or false? The first stored program machine. This is a computer topic. Easy. Okay, what do we got? Okay, everybody up? Okay, the answer is actually true. And I won't try to pronounce that name, but it was invented in France. So nice history there. Okay, you guys are all winners. Come on down. Oh, okay. Well, do you want to do it? I've got we could do one more. Yeah, we can do it more. Okay, so the way this is going to work is you get the first thing you hand. Or I don't know. Okay, you get that.
This game is not fair.
This game is not fair. I'm sorry, I know. We'll let you swap. Yeah, you lose. It's a single elimination game. Okay, everybody back up again. We'll do one more round. Okay. According to Linus Torvalds, he wasn't sure he was a good programmer until he wrote a second open source program after the Linux kernel. Linux kernel was not enough for him to break through kind of imposter syndrome. So the program that he wrote that assured him of his qualifications, was it Subsurface or Git? And this should not be too surprising. It was Git. It was not Subsurface. Although he was, okay, if you don't know, Linus wrote 3 earth-shattering programs: the Linux kernel, Git, and Subsurface, which is a dive logging program. Oh, was it C++? Oh, Subsurface? Oh. Yeah. That's why we'll never have C++ in the kernel. Okay, what continent has the high? Okay, and then for this one, I combined Europe and Asia into a single continent. None of this mountains make a continent divide. What?
How is concentration defined?
The highest concentration of Linux. Oh, that's a good question. highest percentage of land dwellers? It's user of Linux. Highest percentage of people on this continent that use Linux. Is it North America, Eurasia, or none of the above? Okay, yeah, everybody up. If you guessed that this was a trick question, you're right. It's Antarctica. As primarily a science base, 11% of the people in Antarctica use Linux, which is higher than any other continent. But that's only out of like 800 people, so. Okay. So, okay, the first embedded recipes was held in this country. I had to put this one in. Was it the Netherlands or France? Okay, and the answer there is it was France. That one should have been easy because I think it started in Paris, right? Okay, so sorry if I eliminated you with that one. Okay, here's another easy one. First electronic computer produced in France was the Gamma 3 electronic calculator from the Machines Bull Company. Okay, what year was it produced? Was it 1952 or 1957? Okay, everybody got their answer? Okay, it was 52. So, okay. Okay, in what year did Linux take over all of the top spots? Okay, it had been creeping its way up, but in one of these years, either 2015 or 2018, it achieved supercomputer world domination with occupying every slot in the top 500 supercomputers in the world, that's pretty amazing. It's like we haven't achieved 100% in embedded yet. Okay, was it 2015 green or 2018 red? And this was 2018. So, okay. Okay, and this was one of my favorites. Okay, so does the UK military actually have a program called Skynet? Does that true, green, or false, red? Does the UK military have a program called Skynet? And the answer is true. What could possibly go wrong with a satellite system called Skynet? Okay, how many we got? We have enough for prizes, I think. Okay, so by my count, come on down. If you're still standing, come on down. Wait, did you win before? Oh, okay. You can take candy.
You can definitely take candy, and you can just throw your board into the crowd if you want. This game is not fair.
This game is not fair. Yeah. Okay, the game is not fair. I'm letting them choose. Okay. Okay, so that was the skill game. I'm going to zoom past the rest of these answers, and we're going to get to the luck game. We'll do one round of the luck game. Okay, don't look at these. Oh, I got to back up. This one is my favorite. I love this one. Okay, we're just doing this one for fun. There's no question. Okay, which of the following quotes did Rusty Russell have as an email signature? These quotes are priceless. One, green quote, there are those who do and those who hang on, and you don't see too many doers quoting their contemporaries. Larry McVoy. So that's a quote that Rusty put in his email signature. You have to kind of think through that, but it's hilarious. And then the other one is, anyone who quotes me in their SIG is an idiot. Rusty Russell. So he had that in his thing. The answer is both of those are from Rusty. Okay, so sorry, I had to stop and just do that one. Okay, oh, we're going to miss a bunch of those. Okay, let's do the last game. Is going to be rock, paper, scissors. How this works is we're all going to, same type of single elimination. I'm going to throw a sign. Actually, my presentation is going to throw a sign. It'll either be rock, paper, or scissors. I think you know the rules. Rock beats scissors. Scissors beats paper. Paper, for some reason, beats rock. And then if you beat the presenter. So if whatever you have wins against the presenter, if you tie, that's a loss. If you lose, that's a loss. Okay, so everybody up. Okay, so yeah, again, and this is important. So I'm going to say ready, set, okay, and then I'll say go, and you have to throw whatever sign. Pick your sign ahead of time. You know, scissors, paper, rock. Put that in the air, and then I'll show you what the presenter is, and you'd get to decide if you stay in the game. Okay, so ready, set, throw. Okay, presenter was paper. So stay in the game if you're scissors. Yeah, this one's brutal. 2/3 every round. Usually, I mixed it up. People know that I always do rock the first couple times, but not this time. Okay, ready, set, throw. Okay. You're going to love this. It's paper again. Oh, I enjoy this too much. Okay, oh, yeah, wow. Okay, how are we doing? We got 7. Okay, we're going to have to do one more round. So, ready, set, throw. And the presenter is scissors. So if you're rock... Wait, how many we got? Oh, was this like perfect? 1, 2, 3, 4, 5. Perfect enough. Come on down. Okay. Okay, can we swap the presentation or just get the other slide up? Yeah, okay. I've got to, without you realizing that I'm in Windows, I'm going to switch presentation. Okay, and now for some final words, I'm going to turn the time back over to Kevin.
Okay, you can switch back now. Oh, it's going. It must be a Windows issue.
Probably. Let me see. Let's try this. Try that. There it goes.
There we go. Okay, just a couple final notes and final thank yous before we say goodbye. I just want to remind for all the speakers, right when we finish up here, please come to the front. We're going to take a group picture of all the speakers. And also for the speakers, don't forget to take your drawing. So Frank, there should be a drawing at least of all the speakers. Please grab that. And there was before the event, there was a sign up for a key signing event. If you signed up for that and you're participating in that, just please hang out here. We'll do that right after the photograph as well. So that's that. And then I just wanted to say, obviously, another big thank you to all of our sponsors for helping make this event possible. I don't know if you noticed in Tim's slide when he showed all these lists of consulting companies that are contributing upstream, it looked a lot like the list that's on this that's on our sponsors flyer. So not only are these companies contributing to upstream and contributing to the community, they're contributing to helping make events like this possible. So just another big thank you for all the sponsors. So with that, we will wrap up the event. And if you have feedback, if you have ideas, if there are things you liked, there are things you don't like, please send us feedback. the email's on the website, but it's also here. And the social media, if you want to say some things about the event, hopefully just the nice things you put on social media. The bad things, you send them to the email. Actually, you say whatever you want, I don't care. But yeah, please spread the word, and thank you for coming to Nice. Thank you for making this event a really special event. It happens because of all of you, for all of our speakers, and for all the discussion that's happening around the cool topics. So thank you for coming to Embedded Recipes 2025. And if you want candy, there's candy for everybody. So. Yeah, please get some candy if you want some candy. Speakers. Yeah, come on up on stage. We'll do a. Check. Just a reminder for all the speakers, please come up to the stage. We'll take a picture with all the speakers. Thank you. Thank you. We're missing Anton.
Ouais, je voulais juste voir avec toi, c'est quoi Kernel CI, qu'est-ce que ça devient? Est-ce que vous cherchez toujours des labs? Moi, j'essaie de faire revivre le lab Kernel CI qu'on avait chez NXP. J'ai à faire qu'à débouler entre l'IT qui bloque tout. Et maintenant, savoir si ça vaut le coup que je me batte pour essayer de refaire.
Je crois que maintenant c'est le moment de le faire parce qu'en fait c'est le nouveau, le next gen si tu veux, c'est prêt. Il y a beaucoup d'autres labs qui commencent à basculer, y compris le nôtre. Parce que nous on est en train de refaire avec parce qu'il faut des nouveaux clés, les nouveaux API et tout ça. Donc je crois que c'est le moment de le faire. TI est en train de le faire. Oui, enfin. Les labs peuvent faire comme ils veulent, en gros, mais oui, c'est là-bas, c'est bien à faire.
Ouais, c'est surtout ça que je voulais voir, si ça vaut le coup, parce que là, ça fait littéralement 1 an, je crois que j'essaye de dire, les gars, on en est où à chaque fois? Ah, l'IT, elle n'a pas revu l'architecture, le firewall. Bref.
Test. Oh, okay. So if you are here for key signing, we had 20 people who registered beforehand. Preferably they have printed out their printouts. If not, I got a copy. So if you need a copy, please come to me and get yourself one. Kannst du verteilen? Okay. Alexa will distribute them. Yeah, just give them out. Yeah, and for everyone else who didn't pre-register, maybe we have some left. If not, you can still sign other people so they get into the kernel web of trust. But yeah, for signing yourself, you will need to have paper slips. So why we are doing that? So there is a kernel web of trust. There is a repository on kernel.org. And if you are in that repository, it's easier for other kernel developers to check that your patch really is from you. And if you sign pull requests, this can be verified. Yeah. So how does it work? If someone doesn't already know, you have your government issued ID with you, for example, your passport. And here on this list, there are a list of identities and your fingerprint. If you didn't print this out yourself, please check that your fingerprint is correct. And I will read out the hash. Of course, you can't hash in your mind, so please verify at home that everything is correct before signing other people. Yeah, and you can download the list, the handout, to verify other people. This is the hash of it. There is also a PGP file, and yeah, this hash should be the hash that you have on your paper that you either computed yourself. If you didn't compute it yourself, you can hash the file and verify it at home. Yeah, sorry, it's a bit chaotic. Next time, hopefully, we will announce it long enough in advance so everyone can just have it with them, and then we can just, yeah, do this checklist. Yeah, the slides will be uploaded. So the nice thing about the checklist is that you can just verify everything at once instead of having to fetch keys one by one. So how does it work? I will read now, or I will display the hash if you haven't checked it. So that's the hash. I hope everyone has verified that the hash is correct, that they computed it themselves, or they go at home and verify it. Everyone has looked at their own hash, or their own fingerprint ID. And if that's correct, the way this works is try to get in pairs, look at the other person's entry, let them check their fingerprint, and if it's correct, they do a check mark, and if the ID is okay, like the passwords that you see, do a check mark at the ID, and then when you go home and have access to your own key, you can sign it. Okay? If you have any questions, please come to me. Yeah, it would be nice if we had 2 lines, and then yeah, if you reach the end of the line, you can switch to the other side. So make 2 parallel lines facing each other. Yeah, get yourself one. You can sign other people. If you have paper slips, you can also distribute them. Right. 2 lines facing each other, please.
So these are all from here or in the kernel.org? These ones.
These are the people that pre-registered. So instead of getting the paper slip, we just printed them all in one line.
But I mean, these keys are there or in kernel.org?
So some of them are already in kernel.org. I'm already in the repository. Some others are not there yet. But there is a command in the slides which you can use and give it the file. So you can, this is a text file. You can put these check marks in the text file, and then you give it to, yeah, I should have explained it better. So in the Debian signing party repository, you have a tool that takes the text file and the TDP file, and then it generates the signing request for you.
Let me take some of my... So this is you, the first one?
Yeah, this is me. I can show you my stuff. Yeah, I will just show you my passport. It's easier. It's a fresh one. It's an Egyptian passport. I am an Egyptian citizen. Yeah. So Ahmed Khatun, that's my name. It's better than the old passport. The old passport is very old, and I look a bit different. Yeah. Okay. I would have thought you have a longer name and you just do abbreviate it.
Yeah, okay. So this is me.
Okay. Okay, great. Yeah, so I will... Yeah, so yeah, I will do that as well. And I can do it, where's your, is that yours? Or Anil's, that's one, yeah. You can just fingerprint, yeah, that's my fingerprint. I gave you the printout, that's right, and the ID is, I think, okay. Yeah, thank you. Cheers.